the kernel will decide, oh, Opti can still execute stuff, switch back into Opti, and our TA will continue running there. The whole behavior is specified in the Global Platform T, or by the Global Platform T committee, and there are specifications for the client API and for the internal API. So the client API is the API you use from the Linux environment to communicate with Opti or trusted applications, and the internal API is what's used by the trusted applications to communicate with the Opti core. The Opti core provides services such as cryptographic services, it needs to allocate memory, it needs to free memory, all the usual primitives you know from operating systems. And then there are also Opti-specific extensions. So that's something I'm going to touch on later. We can take a brief look at an example scheduling flow. I hope it's big enough. We start with Linux on the left-hand side, and then we call into Opti. Opti then decides which TA you want to run. You usually specify that via UUID. The Opti TA will run. Eventually, it may encounter a timer interrupt when it's running long enough. The timer interrupt will mean that we return to the Opti core. Opti will return back to Linux. We will execute whatever Linux wants to execute after the timer interrupt has run. Maybe another task is scheduled, we run that task, and then the scheduler decides, okay, we can switch back into Opti. So we switch back, run the trusted application. The trusted application continues running until it is finished with its tasks, and it returns back the data that we requested in the first place, and we return all of it back to Linux. Extensions, what does extensions mean? So the theory is that with the GPD-T specification, you can write your trusted application for any trusted execution environment out there if you strictly adhere only to the specification. But in practice, Ts may provide additional capabilities on top of the specifications made by the Global Platform Committee. So for Opti, there's some internal API which is not specified in the specification by the Global Platform Committee, which is cache maintenance routines, because we are on ARM32 bits and not everything is cache coherent necessarily, or on ARM64 as well. We also have some additional memory mapping routines which extend upon the usual malloc by also providing explicit functionality to zero out the buffers beforehand or to allocate zeroed out buffers. There are some helpers to convert TUUIDs from strings and back, which is quite convenient and often used inside of TAs. And we also have the functionality to invoke supplicant plugins on the Linux side, which means that a trusted application can decide that it wants to communicate some kind of data back to the Linux side, which then executes inside of the supplicant. And then there are also additional defines for crypto definitions, so concatenated key derivations functions, HMAC key derivations functions, and so on. There are quite a lot more. There's also support for ED 25515, which is not specified or was not specified in early global platform definitions. There are some definitions for driver support because Opti supports I2C drivers. I'm going to talk about that later. And there's also support to define an explicit storage target because Opti does not do storage on its own. It always relies on Linux for storage. So if we want to store data on the Opti side, we encrypt the data with an Opti and then send it off to Linux to either be stored in the Linux file system, which would be the ReFS driver, or store it on the replay protected memory blocks partition, either via the supplicant or via kernel transport. And the global platform definition by the committee does not specify that there's an explicit storage target. So you don't know what's the target going to be, and it's very useful if you can specify that for each individual trusted application. So the next question is, what is this T supplicant I was talking about in the first, or in the slide before? It's a re-service for T functionality. So since we are running Opti usually on a small memory area, not every trusted application is necessarily compiled into the Opti binary. You can choose to do that and disable TA loading completely, but the supplicant provides functionality to load the TA applications from Linux, from the Linux file system. It also provides the persistent storage functionality I talked about beforehand, so we can store encrypted files from Opti within the Linux file system. And if we have a RPMB partition, we can additionally also ensure that nobody can do rollback attacks on the Linux file system data that is stored there by incrementing a counter within the RPMB partition. If we do have an RPMB partition, the supplicant also implements the RPMB routing for OPT. But with newer kernels, you can also use the direct in-kernel routing, so you don't have to go through user space. The kernel will try to probe an RPMB device from the OPT kernel driver and then tries to go there directly. That was implemented to support functionality such as a firmware TPM. It also has the support to dynamically load additional libraries as plugins for T services. That's what I was alluding to in the previous slide, where a trusted application could, for example, have additional logging facilities which are executed as a plugin on the Linux side to log additional data instead of going through the usual, I can only log to a console. You could do more sophisticated data transport over this plugin API. There's also a TI socket API where you do a TLS transport with an OPT, but then the data is shuffled out over the supplicant interface, so you can communicate with external servers from a trusted application without writing the Linux side to pump the buffers between OPT and your server or the network interface. This is all part of the T-client repository, and there are several libraries in there. There's the T-client library you usually use to link against if you run an application within Linux that wants to communicate with OPT. There's a PKCS11 library, which also requires a trusted application on the OPT side. There's the libse T-client, which is for secure elements. This is used for this is both a testing facility and a provisioning facility, so you can test whether your transport to a secure element that communicates with OPT works, and you can also test the test keys on the device and eventually provision it with production keys to use it in a real deployed environment. And there is the libt ACL for access control lists. This is, or it's not really access control as an access control by the Linux definitions where we have extended attributes. It's more like we can check which group or user tries to use the PKCS11 TA and then give them access to a specific slot inside of the PKCS11 TA, which makes the usage of pins unnecessary in that case, which can be quite convenient for embedded systems deployments. Next up are the tests. OPT provides a very comprehensive test suite that is covering almost anything and is also often used for device verification of correct operation. This also requires additional configurations that are default enabled within OPT. So you have to enable some features to run the tests, and you also have to have enough memory. We had a customer once where we had a task to slim down OPT. So OPT on that system usually used 30 megabytes of RAM and 2 megabytes of shared memory. And then we had a task, and my colleague slimmed it down to 2 megabytes of RAM. But with that amount of memory assigned to OPT, you're no longer able to run the tests. And the customer had specified that they only accept a OPT modification if the tests run successfully. So we had to roll back all of that. So this also supports the official global platform tests. You have to be, as far as I remember it, you have to be a member, and then you get additional definitions, and they can be plugged into the tests, and then you also run the whole global platform compliancy test suite. Which is useful if you want to certify your OPT as a T, but this is already done by us as maintainers of the platform. There's the additional configuration options for OPT. So you need TA loading because the tests build their own trusted applications to exercise the storage functionality and so on. You need enough memory, obviously, and you also need a rich execution environment file system for storage tests. For this specific product, we wanted to disable that because we knew we were only ever going to use RPMB for storage of PKCS11 data, but this was not possible in that case. Another question that's often coming up is that secure by default? And the answer is no, but you can secure it. This, however, requires specific SOC information that is usually under NDA for many out there and is often very use case specific. So if you have a Opti system where you only ever run the PKCS11 TA to store secrets in the secure world, you're pretty much fine. You don't need to interface with any external hardware or drivers. So there are a lot of things to take care of. I've added the list here, and I also gave a talk at FOSDEM 2020, so it's more in-depth and describes what needs to happen for Opti to be secured. Let's start with some of the features. So one of the features I found very interesting is that we have real T drivers, and these are able to handle interrupts in the secure world. So some manufacturers out there have decided there's some hardware that can only ever be accessed from the secure world, and thus you have to handle interrupts in the secure world as well. And how we handle that with Opti is that we go into the interrupt handler, and all we do is arc the interrupt and then punt back to Linux and notify Linux that we want to be run again. Because the problem we run into is there needs to be some accounting on when Opti is run from the Linux side as well. Otherwise, the kernel will get confused because the CPU never does run anything any longer if you are too long inside of an interrupt handler with interrupts disabled. And this also requires that you assign a PPI interrupt number in the Opti device tree nodes. So what will happen is we run the short interrupt handler, then we fire off a PPI. Linux will be scheduled after we re-enable the interrupts, and then it will go back to Opti to handle the bottom half of the driver. So this means we will have this secure interrupt in the middle on the Opti core. We will call into the driver, run the driver interrupt routine, trigger the PPI within Linux. Linux sees, oh, we got an Opti PPI, what happens? And the only case we currently handle inside of the driver is the bottom half handling, which just basically says, please schedule the Opti core, and then we can handle the bottom half of the driver. That will be done, and then once we are done, we return back to Linux. I found this very interesting because it tries to take into account that we do not really have a scheduling facility within Opti, and tries to pull in the Linux environment for the scheduling as well, and tries to make it so that we are cooperatively working instead of running without any interfacing on the Linux side. An additional feature is also we have secure data path and heap support. So newer Linux kernels have support for the protected heap. This is since kernel 6.18. And this is very useful for protected video playback. This could also be used for something like a trusted user interface, where you want to be very sure that a certain part of your display displays the correct thing, and then you handle the heap file descriptor over to your display hardware, and that will display what's supposed to be displayed, and your TA handles all of the important or secure stuff that needs to be displayed. The Opti TAs that interface with the special memory area we have on the right-hand side here with the secure data path area needs a special flag, so not every Opti TA can automatically access this data area. And you also need to decide on how this protection is going to look like on your platform side. This is again platform specific because every vendor implements a different DDR firewall, a different way how to assign XE bus masters and security properties for each bus master, so there's no one-size-fits-all implementation for that. We also have function tracing support for running TAs, which is very useful if you're not running in a QEMU emulated environment where you can just expect what's currently executing on your virtualized CPU. It's also useful to debug on a live target because your live SoC may behave very differently from a QEMU system. These files will automatically be created in Linux and are compressed if the functionality is enabled. And you need to do the decoding, so the decompression, and then also the symbolization of the data via two scripts that are included inside of the Opti repository. The configuration options are CFG ftrace, which just enables function tracing, and then you also need the TAM count, which uses the architected counters of the ARMv8 platform to extract the timing data for each function, but also introduces overhead, obviously, for your TA running. So it's not representative of what your TA or how fast your TA is running in a real environment without CFG TAM count, but you can get rough estimates for how long each function is executing to identify bottlenecks. We also have the Opti device bus, where the Linux kernel can try to probe devices within Opti. As I've said before, there are some devices which are secure world only and cannot be accessed from the Linux side at all. There are some hardware random number generators, for example, where the vendor decided, okay, this is secure world only. And then you need to probe on the Linux side whether the respective trusted application which provides the RNG data to Linux is available and use that as an interface. There's also support for RTCs, there's support for trusted keys, which uses Opti as the backend storage for keys stored inside of Linux keyrings. There's SCMI, and there's also some firmware management capabilities that are associated with this Opti device bus for Broadcom devices. I've never seen that live. I've not worked with Broadcom devices, but yeah. Apparently, they need to go through the secure world for these firmware interfaces. One thing that I've often used is the Opti PKCS11TA. This just provides a PKCS11 library implementation on the Linux side and then uses a Opti trusted application to store your private keys inside of Opti instead of handing them to Linux. The backend storage is done by the T, obviously, and it's very usable in OpenSSL via the PKCS11 provider library. You only need to specify a PKCS11 string instead of a file. It's very straightforward, very easy. This used to be more complicated with OpenSSL engines, but with a new provider interface within OpenSSL, it's much more straightforward. And then we have the usual, you have a PKCS11 device, it has different slots where you can assign different properties to the slots, and you can also change user groups to access these slots if you don't want to initialize any pins. There's documentation for that inside of the Opti documentation on Read the Docs. There's also the feature of the attestation pseudo-TA, which is just a pseudo-TA interface to write a trusted application that is able to verify that you are running a trusted Opti instance. So this attestation PTA provides the functionality to retrieve a public key, which, if it is not present, is generated on the first call into it. And it also returns the hash of the secure header for a TA or library that you want to verify to ensure that you are that you are verifying the correct TA. And then you can hash both the TA code memory and sign that with the public key, or hash the Opti core code memory and sign that with the private key in Opti and then verify it with the public key with the exported public key. This was originally a contribution for the Verizon Opti attestation. They also provide the trusted application within their repository, which interfaces with the pseudo-trusted application to provide a full Opti attestation system. There's also support for the NXP SE050 crypto backend, which is very interesting because this is a secure element that's connected over I2C. So how this works is that you usually set up a session with the SE50, which is AES encrypted, before you even start into the Linux kernel. You do this session setup via an internal native I2C driver with an Opti, but then afterwards you can run into issues where the Linux kernel wants to access the I2C driver and Opti also wants to access the I2C driver, or there are pending transactions and so on. So what happens afterwards is that after Linux has started, you hand over the communication to Linux instead of going directly through your own I2C native driver. So there's a special RPC that you do, or that is done by the crypto backend if it wants to communicate over I2C. And then the Opti kernel driver within Linux will see, oh, it wants to do I2C communication with this adapter, with this data, and then schedules that on the Linux side. So we don't run into concurrency issues where both Opti and the Linux kernel would try to access the I2C hardware. And instead, the Linux kernel will access the I2C hardware. And that's also the reason why we need to set up an encrypted channel, obviously, beforehand. Otherwise, we just would hand plain text data to the Linux kernel, which would be a security disclosure when communicating with the secure element. We also have support for non-secure virtualization. This was an external contribution for Xen virtualization. This basically provides an independent view of Opti TAs when you come from a DOM U inside of Xen. So This is useful if you, for example, want to have virtual machines within Xen, but each virtual machine has a different view of the PKCS11TA, for example. So each virtual machine can store its own secrets within the PKCS11TA. There's also a preliminary patch set for KVM that somebody posted on the TFA Discord. I looked at it and it looks fine, but apparently they did not really have a use case for that to upstream it. It's inside of the Discord. I didn't have the time to search for the link on the Discord, but if you're interested in that, please take a look. Now we take a very brief look at the firmware framework A definition, which was basically done because we have this trusted hypervisor mode that is not really existing on ARMv8.2, which is many embedded SoCs out there, but it does exist for ARMv8.4 when you have feed SEL2 enabled. This means then you have a trusted hypervisor mode in addition to the trusted OS and trusted applications. So if we then fill in with the usual components we would run inside of each exception level, the normal world just basically stays the same. We have applications Linux and the Linux hip stub, but then the trusted world becomes different. The reference implementation for SEL2 is Hafnium, and then you could run multiple Opti instances or other secure partitions inside or on top of Hafnium. Yes. This is all specified inside of the FFA specification. The SEL2 component is usually called a secure partition manager, and each view or each of the virtualized environment is called a secure partition. So you have a partition 1 in this case, which just contains Opti and its TAs, and there's also a partition 2, which doesn't even use SEL1, it just uses SEL0. You also need a secure partition manager controller. This is the one that sets up the secure partitions when first started. You need a secure partition manager dispatcher. So this is usually the firmware that is running in EL3. And you have direct or indirect messaging with RxTX buffers, or as we've already known from Opti, which just uses the register interface within the SMC calling convention specification. The contrast to using Opti directly is that FFA is discoverable, so you can query FFA for what secure partitions are available, which is very different from just trying to reach Opti and then you may get an error back from TFA or it may just work. There's also support for asynchronous and synchronous messages. There's a specification for how interrupt management is supposed to be done if you have SEL2, because which partition is assigned, which interrupt has to be handled beforehand. There's support for status reporting from the partitions itself. There's notification support, so even partitions can notify each other. So you could have Opti using a different secure partition service, which is a crypto backend, for example. This is also supported. Yeah. Do we really need this? No. So since we don't really, or since hardware for that is coming up, you don't need ARMv8.4 feed SEL2 hardware to test out FFA. You can run Opti with SPMC at SEL1, and then Opti can run secure partitions in SEL2. So this can be run on ARMv8.2 hardware if you want to try it out. This also means that your TFA needs to be the secure partition manager dispatcher, and Opti will take the part of the controller in the FFA specification. This also means that the Opti core is only reachable via FFA, because TFA will refuse to do any other handling than FFA if you enable the FFA transport. And then Opti supports both an ELF format that they already use for the TAs and a flat format for the secure partitions. And these secure partitions need to be defined inside of manifests and are started at the very end of the Opti startup. So these are defined, fixed before you start your Opti. But what if I don't even have Opti? Yeah, that's also supported. You can run both the secure partition, the dispatcher and the controller inside of EL3. And then your secure partitions run inside of SEL1. Those are then loaded by the TFA. So the TFA, again, needs a manifest of what to load, and then it's included inside of the BL2 stage for TFA. And then you have a setup where you are not even using Opti, but you can try this out on systems where you only have the TFA. Yeah, let's do a short recap. I did an introduction. I talked about a lot of features like the driver interface, SDP, protected heap, ftrace, Opti device bus, PKCS11. I dove a bit into the FFA specification. Yeah, and that's pretty much it. If you do have questions, please don't hesitate to ask. Perfect.
Great talk. I know Leonardo doesn't work on it, but any words about Opti on RISC-V?
Yeah, so upstream we have contributions from Opti on RISC-V. I don't know how far along that is and if there is hardware that's supported except for virtualized environments. So that's all what I've seen so far, but in theory it could be supported. I don't know what the specifications for communication between normal world and secure world looks like for RISC-V. I've not dove into that specification, but apparently somebody has started to work on it.
Thanks.
Thanks. I'm not familiar with Opti, and now it's much clearer. Can you talk about the last few options for FFA? You mentioned a few ways to get partitions. Which one would you pick? How do you decide? Like, this one looks the simplest, so it sounds like the right one.
Yeah.
How do you make a difference?
Yeah, so it depends on what does your hardware support. Obviously, if you want to use FFA because you have a use case where, for example, where you want to virtualize secure partitions for individual virtual machines on the Linux side, and you have the SEL2 feature, for best isolation, you probably want to use Hafnium. But if you do not have that feature, you have to look at what's supported by the respective implementation. So Opti supports different parts of the FFA specifications than the TFA controller and dispatcher does, so you have to decide based on the supported functionality there. Both Opti and TFA have a description on what is supported and what's not supported. So I would use that feature set and look at what's required for my use case to decide on which to use.
And so what's lacking with this option where you don't have Opti? What's lacking? Why would you not use that if you have features?
Oh, yeah, here your controller and dispatcher run in the same exception level. So there could be bugs there. And if the controller is compromised, then the dispatcher is compromised as well, which can be bad for your security properties, obviously.
Hi, great talks. One question, is there any planned support for PQC, especially in the PKCS11 TA?
So I think the current specification of the global platform from the Global Platform T Committee contains PQC. We've looked into that, but it's a lot of effort. And I know that currently we get a lot of AI bug reports which are valid. So these need to be fixed first before we can dive into feature development again. But yes, we would like to support PQC, obviously.
Thank you very much for the talk. You've talked about Opti, and all this is, of course, free software. Do you have examples of free software trusted applications that are running Opti?
Free software trusted application. No need to think. So it's a bit difficult. So since Opti is under a BSD2 or 3-clause license, vendors can decide to not disclose the Opti source code, and then you need to do some reverse engineering. But there are basically every ARMv8 platform out there is able to run Opti, and we have support for many, many platforms. But then the security of locking down Opti enough to work is a whole different matter, and is usually not done for open source platforms. It's only done for production devices or product devices. So yes, you can run Opti on many devices out there, but it's not necessarily secure. We also have support for Raspberry Pi, obviously. It's not going to be secure because the Raspberry Pi is lacking the necessary hardware to protect the memory area and assign IDs for the DMA masters, so they don't access the secure memory. But it's a great platform to get started if you don't want to work on a virtualized environment.
Thank you.
Hello. Who is going to put everything on execution? I mean, I know that, for example, you would have some support for some microcontrollers for doing this, but I wonder if what is the recommendation from the Opti software? Is to put that in the firmware from vendors, or is to put in a bootloader for doing that? Who's going to put that on?
So you're asking how Opti is put into the trusted OS world, or how the boot up functionality works? Or?
What's the recommendation for the bootstrap of everything? You know, you will have different levels of firmware, ROM, then.
Yeah, unfortunately, this is also very SOC specific. So for NXP devices, I know that the TFA will look at a specific load address where the Opti binary has been preloaded and then relocated and jump into it. But the usual flow that was first envisioned by ARM for that was you put the Opti binary inside of your TFA binary, and then BL2 will just copy it and jump to it directly. This doesn't work for most devices because you don't have enough SRAM for that. So you have to do the DRAM initialization beforehand. So starting up Opti is a whole different can of worms for each individual platform, unfortunately.
Thank you.
I have a very basic question. So you showed how Opti actually runs as a sort of, it sounds like it's in a Linux task, right, or a Linux context. If you've got 10 CPUs, how do you know that only one of them is calling into Opti?
Oh, you can have multiple CPUs called into Opti. That's not a problem if your TAs. So your TA can decide whether it can be single invocation or it supports multiple invocations by different CPUs. But since we on the Linux side have to decide to call into Opti, we always know that we have put a core to Opti, and that it will eventually, hopefully, unless there's bugs, return back to us.
Thank you, great talk. Do you have any information about an SCMI server supported in Opti?
On SCMI drivers?
SCMI server, Opti has an SCMI server.
So Opti has an SCMI server, yes. Usually as SCMI is implemented on TFA in EL3 for many devices I've encountered out there. The Opti SCMI server is used for the STM32 MP1 and MP2 devices. So they've decided to implement SCMI on the Opti secure side, which makes it easy to also have Opti access devices because clocks can't be turned off unless Opti also agrees to turn off a clock and knows that it's in use by one of the devices. I don't know of any other platform that has decided to use SCMI and Opti for that, but so far I've only seen SCMI implementations for STM32.
Okay, thank you.
Sure.
Thank you for the talk. Would it be possible, in your opinion, or if you know it, to run different trusted OSs with Hafnium? So, for example, Opti and Trusty, for example. For
this is explicitly supported. So you could run, so one of the use cases I could envision for FFA is you have a device, but you also support other vendors running virtual machines with their own operating or a trusted operating system as a secure partition. So if you want to, this is explicitly supported by FFA. So you could have your device, which is running Opti with your PCS11 TA, and then your vendor could provide you with the virtual machine and the binary that is supposed to run inside of the secure partition. You include that in the manifest, and then it will start up a different trusted OS as well as a separate secure partition. Yeah.
Thank you.
Okay, looks like we're out of questions. Thank you.
Yeah, thanks.
No, it was the hub. I have, I think, the same computer than him, so. Hello, everybody. I'm gonna start the next talk about a distributed phone CI for Postmarket OS. First of all, a small introduction about me. I'm Pablo Correa Gomez, probably online. You can find me as Pablo Yoyoista. I'm a Postmarket OS core contributor, which is basically the group in charge of strategic planning and governance in the project. I've started contributing to a project to Postmarket OS back in 2021, mostly doing code contributions of all different kinds. Since then, I've been shifting my focus more towards governance, project management, community management, so all the stuff that engineers don't generally want to do, or things that are not so fun. You want to talk about something that's usually not code in the project, you'll probably end up crossing through me at some point. Most of my work is basically volunteer work in Postmarket OS. So I make a living like with some other software, and all of my work in Postmarket OS is a volunteer. Previously, I have also been part of the GNOME document viewer maintenance and like porting to GTK4, and also I've been a director at the GNOME Foundation Board of Directors. One thing that's me as a person is actually quite important is that technology should serve people. So I'd love to be here to actually solve human problems, and not tech is really fun, but to actually use it to solve like problems in people's lives. There you have my contact if you ever want to talk about anything related to a project. So then I'm going to start the presentation with some discussion about what is the project, how it has been developing, key ideas, and then we'll go to be able to understand why we are trying to do the work that we are trying to do on the hardware CI. So first, a question. Who has heard about Postmarket OS here, just to have a rough idea? Okay, maybe half of it? Okay, thank you. But then I'll go a little bit faster through this section. But generally, Postmarket OS has as its mission to develop free software to extend the life of consumer electronics with the goals of sustainability and giving back users control. So in a way, this is a pretty much political project where we aim to solve those issues. Technically, basically, Postmarket OS is a distribution. It's based on Alpine Linux. And its main goal is to run, or its main target has been historically to basically run on phones. But to do that, we basically use mainline Linux. So there's no Android, none of the downstream stuff. Everything goes mainline. And generally, the goal is to push upstream as many things as possible, because that's what makes sharing and the idea of FOSS better. Going a bit more into detail, what do we do exactly in terms of devices? So we have around, like these numbers are still a bit old, but we have something like 500 device boards, so 500 different ARM boards that run on this. There's more than 100 in stable release. We have a wiki with a lot of information that has even more devices that nobody bothered to port, but that people actually, well, I did something cool on this device, so they put up there. Yeah, so that's basically an overall on numbers. I also have here that through 2024, the PostMarketOS community sent around like 200 patches to the Linux kernel. I think I haven't run the numbers for last year, but they're probably a bit bigger. So devices, but what exactly are the devices that PostMarketOS supports? So one of the things, I mean, regular distributions these days don't really bring something that's completely different. Okay, you have a different package manager, you are doing something slightly different, but like the whole ecosystem has shrunk, like increasing consistency quite a bit. So what makes PostMarketOS a bit special and different to most other people or most other distributions is that it's basically a platform that works across anything. So we've got phones, which are the main target, and like they run the exact same operating system, basically the exact same code that you can run in your tablets, that you can run in your Chromebooks. PostMarketOS, technically the tooling is built around the flexibility that you need in order to boot very, very different hardware. That means, so we started with phones that are these very weird devices that have each vendor have their own flashing method back in 2017. They have different conditions, they boot in different ways. So basically, the flexibility in the tooling need to be there. And that means, well, it also works on tablets that have the same problems. But somebody around 2019, 2020 started, oh, well, we can maybe try running on Chromebooks, and all the logic and all the craziness to support these weird booting machines and to have different kernels is in there. So, well, then you go Chromebooks, and then, well, in the end, decided, why not? If we can run on weird hardware, we can also run on normal hardware, right? So we have support for normal laptops. Like this presentation is basically running on PostMarketOS. Where, of course, PostMarketOS doesn't make as much of a difference because what the goal of the project is, and what makes different is these other weird devices, let's say. In terms of a bit of governance, we are a growing and like positive community. We try to make everybody feel welcome, have a code of conduct, try to enforce it as best as we can. We focus on collaborating with other communities, so like and sharing knowledge. We don't just want to be alone in this ecosystem. So we have good relationship with like a lot of the UIs that build project for us. We have regular calls with them. We have regular relationship with Mobian, Foch, Dom, KDE. The concept of we do some work and it only works in PostMarketOS is not so attractive for us. And like we try to endorse this upstream first approach. As of growing, we've been like, we're 8 maintainers in December 2023. A couple of years, we are 29 today. The project was founded in 2017, so it took 6 years to get to 8, and it's taken like 3 years to get to close to 30. And yeah, basically these ideas are tied to our mission on sustainability, user ownership, and like support a better society. We've also been building our organization the last couple of years. So we've been collecting donations since 2023. And we have a small but steadily growing income. This basically allows us to support critical projects. So for example, Hardware CI would not have been possible without the donations that we've been receiving. We've received our first grant as a collective project this year, have transparent financials and regular reports about everything we do. And on the governance side, we are trying to move from this collective BDFL model. Like I said, I'm a core contributor basically just because I was there early enough, and we are trying to move away to have a more democratic decision-making process. We have a small distributor that's selling now second-hand devices in the US, and we are in the process of creating a legal entity enabled to be able to represent us in front of grants to take legal ownership of resources and so on. And then we are in the process of renaming the project. It's taken longer than expected, but hopefully we're just waiting for the trademark lawyers. So with all this context, we can talk about, like, this context is, okay, what the project is about, how did we come here, how have we been growing? And as part of this, we've had a very interesting socio-technical challenge, which is phones are very complex devices. Compare, for example, if you want to do some testing, I was talking with people from other ecosystems lately, and their problems related to testing and verification of updates. They basically work on laptops, they boot their new kernel, they check a couple of videos online, they connect to their Wi-Fi, which is your regular workflow, maybe they just do a call with their headphones, and that's it. You know, like, you know that basically everything works. Most things are shared with all the other ecosystem. Phones are a lot less tested upstream, and their use cases are a lot different. So if you actually want to test comprehensively what you are doing on a phone, you don't only just have to turn it up and check a YouTube video, but you actually want to go outside and see if when you get that your modem doesn't die when you move connection from this tower to that tower. You have to make 3 calls in a row to make sure that the model doesn't crash in between. So this whole testing process can be very hard if done manually. In addition, our project, how I have described, have a strong focus on the mainland and second-hand market. We very rarely get support from manufacturers, which makes the whole testing a bit more complex. And the project has grown in breadth. So we have so many devices, and like testing them all and the exponential possibilities that happen with that, it just gets very hard. At the same time, we are a volunteer community, and this is one of the regular problems at FOSS. Everybody wants to do functionality, everybody wants to make sure that your device works well, but nobody really wants to maintain stuff, right? And nobody wants to actually spend a day checking whether the Wi-Fi connects, like you turn on and off your Wi-Fi, and your Wi-Fi keeps connecting after 10 tries. So as a consequence of this situation, we have a general lack of reliability in our project. Things work, and they work most of the time, but they don't work all the time, which, of course, when we all have phones in our pockets, you don't want to miss a call from your doctor because, well, my modem crashed. So it's very important that it works all the time. And we haven't been able to get there. At the same time, that has also caused some maintainer burnout, which is something very sad. I mean, people burn out in free software communities, and when that happens, it's always very sad, because you lose a friend, you lose a team member, somebody like actually that felt very nice contributing to your project. Stop feeling like that. So faced with those problems, we've dreamt. And the dream is like, can we just have hardware testing? So like, we put the phones somewhere, you test all those features, and the maintainers don't have to go and boot their phones manually, right? Yeah, so that was the dream. The question is, does it have to be a dream? Can we actually solve this problem? So going more a bit into details, our requirements to solve these problems is basically we want to ensure the reliability of a specific functionality on specific devices, because the code shared with the complete ecosystem is a lot less, and because the hardware is a lot more complex, so that is harder to do. So we want to ensure that reliability. We want to reduce the friction for contributors, to allow them to not have to do all the work manually and reduce these chances of maintainer burnout. Long term, since we are a community of volunteers, even if we end up professionalizing in the future, the amount of phones and the amount of vendors that exist is very, very broad. So in order for this to be successful, it's very important for us that we can enable a long-term crowdsourced solution, so that we don't just have a farm with 100 devices, because, I mean, there's 100 devices maybe covers 3, 4, 5% of the phones out there. So we need something that can be distributed, and that different people, different companies, different volunteers can have stuff in different places. We did an initial attempt. So that was a dream, can we do this? So we did an initial attempt in 2022. We received an NLNet and NGA Zero PET grant. We tried a mostly custom system. Unfortunately, you can't see the links there, but like you have them in the slides. And well, it got to a proof of concept level, but it never really took up. So it never reached the minimum viable product level. We couldn't really deploy this, which was pretty sad. At the same time, we are a group of volunteers. We understand that we are a young community. We understand things sometimes go wrong. So failure is also a success. We don't have to always nail everything on the first try. But through this process, we learned quite a lot of things, is that CA architecture of hardware is really hard. So the fact that there wasn't really a system before that could support our requirements is for a reason. And yeah, we couldn't find that system. But like, yeah, yet spending a lot of effort adapting something for our needs, given the complexity of the situation, would be a lot better than just than trying to do everything ourselves. Even if there's also a lot of features we don't need, better to try something with somebody else. Try to start simple, focus on maximum impact with minimum changes, so how can we get to something that is actually functional? And this also that this needs a coordinated long-term effort. So this is not a 6-month project that you solve with a grant, which is slightly unfortunate, but that's how life is sometimes. So since they are based on some of these lessons, we changed the way we do projects. We've basically started making sure that every project has some kind of project management, somebody that's responsible to push for this, to make sure things work, to make sure like the goals that's set at the beginning and finalized at the end. And like, yeah, to basically improve on the communication inside the team and outside the team, to make sure that even if you're a community of volunteers, anybody that wants to be involved can be involved. People know on what we're spending the money, people know our goals, which is also a way to keep yourself accountable, right? So if you want to do this and everybody knows you want to do this and you don't do it, it looks a bit weirder. So you have sometimes a bit more motivation to actually do the work. So we tried again. We picked up the project again at the end of 2024, and we tried a bit of a new approach. So first, try to find something that could potentially fulfill our requirements, even if it didn't back then. Then try to limit the complexity. So really try to do something simple that just works, even if it covers a minimum amount of the testing that we would like to see. And then try to involve our community. So after a lot of time, thought, and work, we basically solved this thing in 3 ways. We are using CA-tron as our test orchestrator, let's say. We have a custom phone harness that we have developed, and we have we've developed a better, easier onboarding and more documentation and processes to make sure that this is not just something that a couple of us did, but this is something that can scale to the general community. So CA-tron, what is CA-tron? CA-tron is a plug-and-play CA system whose main design goals are to be low maintenance, have a declarative configuration, and saying defaults. This has quite some consequences that fit well into what we want. So you can, in principle, give this to volunteers and reduce the barrier of entry to test changes. And it also should, in principle, allow a more crowdfunded approach. A bit on the architecture, you can see there basically what is CA-tron is only the gateways of the desktop there in the middle. That's basically what CA-tron is. So it boots to a computer, it connects to power delivery units, and it controls the DATs, which are the device under test. And then it basically talks to your current CA system. We looked at other problems, we looked at other possibilities like Lava and LabGrid, for example. With LabGrid, we had this problem that it lacks some of the integration that CA-tron has, and it would fit, so setting up the system would be more complex than what we need to do with CA-tron. And specifically for our needs, that would be a bit of a blocker, and Lava is a bit more designed for big corporate systems, and we are a bunch of FOSS volunteers, even if we are building an organization. Maybe one day we can have a lab with 50 devices, but again, even if we had, that would still not fulfill the complete requirements. Yeah, so what did we do to adapt C8RON for Postmarket OS? So at the beginning of 2025, we contracted Martin Goukala. So he is the main developer of C8RON. He liked our project. We have some discussions. He gave us a demo, and they said, OK, let's go ahead. We paid him to do some work. So back then, there were some documentation in C8RON. It was still in its early stages. Now it's online on a pretty website. The job and the way to run jobs is much better documented. He had a new template to fulfill our goals. Basically, C8RON came and was developed through the Steam Deck project at Valve with Martin as a contractor. So they basically want to test Mesa and want to test maybe new kernel drivers, but mostly the user space stuff. We want to test the complete boot process. So like, it's not weird that you do a rebase of your kernel on top of 7.1 RC and it just stops booting. And we need to be able to test that. So he did some changes to be able to adapt that. He also wrote a driver for the 4 harness that got merged upstream. So now if you get the device that we use as the power controller, it just works. On my side, I worked on the integration with Postmarket OS. So boot deploy is a small program we have to basically make sure that these 20 different ways of flashing your device and of setting up the boot partition works. So basically, now it's integrated, and we have a couple of phones running there. So if somebody does a change in that project and you have any other phone, it's right now tested on the OnePlus 6. So you can make sure that your changes as a contributor don't actually break other phones that you don't have, which helps quite a lot. Yeah, I also did quite some integration in our code repository, in our main integration repository. There's now proper integrated documentation on our side. Yeah, general problem to scaling the C8RON, the Postmarket OS support, is that not that many people want to look at CI. I think CI engineers it's not the dream job of probably anybody here. So yeah, that's still a bit of a challenge, but we've made great progress. I'm not a C8RON maintainer. I've done a few contributions, so I also wanted to share a bit of my experience as a user. I have to say that after a year, more or less, working on this, I'm pretty happy it does a good work at fulfilling their goals. So like those goals we talked about, they pretty well reach them. Once the setup works, so once you get a setup and it works, you add a new device, whatever, it's unlikely to break, and it's unlikely to break also by design, which is actually something very nice. Still has many rough edges and documentation gaps, so it takes quite a while to get onboarded. So it took me like, I don't know, 3 days hackathon to finish the complete setup for one of my devices, and like another people from my team that tried the next day. He had similar problems since I had already bumped into a lot of those blockers. We kind of solved the problem in like an afternoon for him, but it does require time to get onboarded. Basically, that's a place where probably fixing the documentation gaps would help a lot, and fixing a lot of the paper cuts in terms of user experience for the software would also help. It's also improved in the last year, to be honest. A lot of the work they've done and some of the documentation they've improved, I think it's been helping quite a lot to onboard new people. I have to give a big shout out to Martin. His support has been invaluable. And yeah, as a first project, the GitLab integration is just amazing. So the same CA pipeline we have to build our packages, it also actually tests things on the phones. And it's completely transparent. You just get a GitLab runner that's actually your phone, and it runs whatever you ask it on whatever you want to run on the phone straight ahead. And this is like very, very nice integration where most users just don't have to care, and they can just run things as desired on the phone. I've talked about C8RON, so this is basically the orchestrator, but one of the problems that we have with phones is that phones have batteries, right? If you want to have a phone under test for the next 2 years, the most likely thing to happen is that the battery will swallow and that your phone will catch fire one day. Of course, this is unacceptable for a crowd-funded farm. You can't also expect people to exchange their batteries every 2 years, which I'm aware some companies, for example, do. That's something we just can't have in this kind of volunteer setup. So basically, we need a control board to be able to replace the battery and control the device, power it on and off, maybe touch some buttons, get logs out. Yeah, so basically, in addition to that, since we have a varied set of devices, we need some board that can adjust the battery of the voltage on software, because, well, different devices have different voltages on their batteries, and they're powered in different ways. We need some UART and USRC to get logs. It should be possible to fit on a credit card size. It should be pretty cheap, because we're basically funded by donations, and one of the things there were some potential other options that were in the market before this board, but yeah, their price was basically prohibitive. If you have to pay 500 euros for each of those boards, then you basically run out of donations in the first month. Yeah, and of course, since we are going to develop, it has to be open hardware. So yeah, actually, it took a lot of effort to find somebody up to this task. I have the board here, so the project was finally actually successful. In the end, we tried to pay people to work on this. We couldn't really find somebody. We don't know if it's because we work too much on the software space and don't have, or the low-level space, but there's nobody with power electronics experience or whatever. In the end, 2 volunteers took up the design, Fiso and Encorna. One is from our team, the other one is a friend of Federico. They volunteered their time for more than 6 months. They had an initial design with a back converter. So yeah, doing some power electronics. The problem is that the device, part of the requirements, we need to go down to 3.3 volts and be able to provide up to 5 amps because, well, especially during boot, batteries, phones can request a lot of current from the battery. Finding a back converter for that seemed to not be easy to find, and after design, they just couldn't be manufactured because the component they had chosen ran out and they couldn't find a replacement. So after a couple of months of trying, we had to go back to square one, and then they tried a second attempt, doing something a bit more fancy. So they basically used a power delivery sync controller, and use a PPS power supply. So basically, that way, you basically outsource the power electronics to some fancy charger you find, and this actually worked pretty well. So they had an initial iteration manufacturing where they confused some maxes and whatever, so it didn't really work. You have the picture there with some hacked up cables. But then the second run was already functional, and it's actually currently running in production in Martin's lab. So, and it served to actually develop the production firmware, which is, I mean, having something functional with 2 revisions in hardware, it's not super common. So, actually, huge thanks to them too. And then the version 3.3, it was already provided to most of our team members. Anybody that wanted to have a look has one, and we'll probably do more runs in the future. So, okay, we have CA-tron, we have our phone harness. Basically, the way this works is that CA-tron has a driver for this phone harness. The device is connected to them. And then CA-tron can basically power cycle the device. It can turn it off completely. It can turn it on. The devices need to have Touchhang, which is a U-boot distribution installed that basically boots to fast boot mode. So whenever it can do also UEFI, so you can basically boot the device either through UEFI or as a regular Android boot with fastboot, which gives that quite some flexibility in terms of how we do stuff. And yes, there's basically direct GitLab integration. It's a bit complex, unfortunately. So we generate the jobs dynamically. Somebody in our integration repository that's called PMA boards updates a kernel for which a device has hardware CI, and then automatically the CI will generate dynamically a definition for those jobs and will actually boot test the kernel. Right now, there's a very basic set of tests for some devices, and we're going to be talking a bit more about this in the future, later in the presentation. This is a small video where you can actually see the whole thing in practice. I didn't actually want to risk doing a real demo. But I mean, that's a regular GitLab CI job. Probably most of you can recognize it. As you can see, it actually starts getting logs. It boots a device. You can see a small U-boot logo up there. And yeah, it's sending the kernel through fastboot. And hey, there you go. Those are the tags. So basically, the whole integration is pretty transparent. The other thing that we've done for this project has been try to create easy onboarding and documentation. So part of the work of actually getting this whole setup is actually removing the batteries. So for the phones that we support, we've tried to get some good pictures, the person that does the work for the first time, to record the whole thing, document how you do the stuff, document the whole Catron integration on our side, and make sure that anybody that wants to look at has a good entry point, and you can understand how the whole thing works. This is something that previously to this project we found pretty hard, so we couldn't find that many documentation about other existing systems, about how the whole thing is supposed to work. How do you integrate this into your project? So we've basically tried to solve that, and we are getting there. Basically because we've seen other people. So I basically reproduced Martin's setup, and other people have been able to reproduce my setup with very little help from our side, which is basically how it should be. So now we have the devices, we can boot them through GitLab, we can do the whole thing, but yeah, what test do we run, right? So we have the setup. What do we do with this now? That's a bit of the question. So basically, we've split the test in three kinds. Kernel tests, which is basically this very low level. You make sure that your drivers are proved, that whatever devices that are expected to be there are there, that they work basically. So you send them something and they respond. We're using something like bootrr for that, and basically this is done from a custom init.rumfs, so you don't have to flash anything to the device. We also have the aim to develop boot tests and system tests. Unfortunately, we don't have those things integrated, so that's more like a thought. The idea with boot tests would be do some kind of smoke testing, identical to the user boot procedure, because due to being able to support so many devices, this is something that breaks a lot more often than we would wish. And system tests basically a complete end-to-end integration suite. So this dream of actually you can just test your modem and test your phone and test your calls from a lab, greatly reducing the issues with reliability and the manual test requirements for users. So moving forward, so basically this is what we have done already, things that we want to do in the future. So we want to really reproduce the setup in more devices. Right now we've tested the OnePlus 6 and 6T, Pixel 3a, Ratchet Dragon Q6a, Fairphone 4, but we really want to be able to reproduce this on more devices and potentially try with some tablets, potentially try with some Chromebooks. It's basically ready for greater adoption. We are basically starting a process for community members to get phone harnesses. If you are interested in getting one, you think this project is cool, so basically this thing, feel free to reach out, and we'll see whether we can accommodate that or we can do some agreement where we can do them. I mean, in the end, if you want them, you can just print them yourselves. Order them on GLC, PCB, or whatever. It's open hardware. Of course, we want more docs, also including Catron and fixing some of the documentation gaps in there. That including the fixing the UX at first boot, so to make it easier to get onboarded with Catron and tests. Because right now we have the whole thing, but we aren't really testing anything. So yeah, that are the things that we know we want to do, but there are things we actually don't know how to really solve. So for the test, is how do we actually scale this up? Which is the best way to actually run and validate kernels in specific SoCs, in specific devices where you are not the manufacturer? Is there anything already for that? Can we hook this up into kernel CI? yeah, so those are all questions in our mind that we don't have resolved. Anybody has feedback afterwards, I will be lovely to hear about it. What already exists for this kind of integration tests, so for like validating hardware and software at a higher level, like can you do calls, connect to Wi-Fi and so on? Is there something in the FOSS space? We haven't really been able to answer that question yet. What is the reliability of these crowd-funded devices? So we have the structure that should support having a crowd-funded farm. Will this actually work in practice? Of course, we don't know because we haven't been running this in production for so long. Which is the test coverage that you need to actually make an impact? So we think we can solve it with this, but like, can we actually? Do we need to get to 80% code coverage to actually get something useful, or will we start getting something useful from the very beginning? Yeah, can we donate devices to upstream projects? So our upstream projects, like the kernel CI project, thinking people like Pipewire, libcamera, are people interested in running our hardware? And is it going to help other FOSS communities? Because like hardware testing is something that maybe is done at manufacturers, maybe it's done at some very big FOSS companies, but it's really not done at the FOSS community levels. Are there other communities going to be interested? We think yes, and we've already gotten some feedback on that. But of course, this is not something we have fully tested yet. Yeah, so basically that's it about the talk. You can find more info about our project governance. We have a very active blog. If you like what you're doing, we are a community project. All this thing has been bought from donations. You can always donate. You can find that in Mastodon, and we will have a conference in Aachen in September. So if anybody wants to show up, please go check the link and register. You need to register for free, but you need to register. And yeah, thank you for listening, and thank you also especially to Kevin for inviting us to talk at the conference.
What is your security model? So if I'm a malicious contributor, there are ways to permanently mess up your phone, like maybe blow some fuses or something like that. How do you trust me?
Right now, we run them manually. So we have a button where we click for those things. Otherwise, yes, generally breaking the devices is, you can totally do that. The most likely chance that will happen if you do that is that you will get banned. But yes, somebody could do right now, somebody could do a targeted attack to do that. It would have to pass through the manual review and somebody to click the button of yes, run this on hardware. That is as of on the devices. In terms of like the farms, CA-tron has very strong isolation from the devices, so it's very hard to actually access the network in my home, even if you have complete access to the device. But in terms of the device itself, breaking it, if you had full access and we didn't have manual triaging, wouldn't be super hard. In the future, I mean, one thing that CA-tron has is like you can basically add trusted people to different groups, and then they are able to actually run this thing. So something similar to how freedesktop.org uses for their CI, where basically you get added to a specific group on GitLab, and then unless you're in this group, basically you can't run any CI jobs. Something like that is most likely to be available for us in the future. So that, I mean, if you are a community member, you specifically are, and you want to run something, you will just be able to. If you are not, we first have to trust you.
Thanks.
So you mentioned modems related issue quite a few times. How do you test them?
So I didn't add it to the presentation. I should have had a backup slide for that. Right now, there has been a proof of concept by one of the community members where he hooked up some headphones to basically the phone and played a call through zip on, so basically run some script. So you get the device, in CA-tron you can boot whatever you want. So you can boot the distribution, run some scripts, and actually do a call directly from Modem Manager. That's actually relatively trivial, and play some sound on the call. And then you can have some virtual number, which are pretty cheap, and actually do the real call to a virtual number. And well, if you receive the audio back from that call, then you know it works. So that's a way to do the whole integration testing. Of course, this is very complex. And we know also some people that have been looking at having Faraday cages at their homes and setting up complete 4G networks. Not exactly in our project, but the people from Foch already have something like that for testing emergency calls and testing, I'm not sure exactly how you call it, when you receive an SMS from the government because there was an earthquake. So that is the other way to test it, to actually do the calls and actually test the real stuff.
Can you test degraded networks, or degraded Wi-Fi? Because the telephones behave strangely when they have poor network, poor Wi-Fi, and they struggle to get a good signal. Do you have any harness that can simulate these and stress the network part of the phones?
For that, you would need, again, a Faraday cage with a software-defined radio. We know this is possible. We know people that have this. We don't have the whole thing right now ourselves. In terms of Wi-Fi, the CH-RON gateways do have support for specific Wi-Fi that is basically connected to nothing, just to the gateway itself, so the gateway can basically simulate this kind of work. So that would be potentially the way to do it with Wi-Fi.
Okay. I was thinking the Linaro OneLab LAA harness. I don't know if they have any technologies that can do this kind of simulations. Maybe the Linaro people can be put in communication.
I see some of them saying no in front of here, so. But thank you for the idea.
So just to see if I got it right, this is a decentralized CI, and if I want to join it, I need a server with a CI-tron instance on it, so it can be called from the outside, and I would obviously need some of your hardware boards there to control the phone, and that's it.
Yes, so you basically need, right now, the 3 that we have runs on Raspberry Pis. So you just need a Raspberry Pi, a couple of USB ports, some of this hardware, and then you need a token from our instance. So basically that we trust you to run stuff for us, and we will give you a token, and then you can basically enroll your runners. I mean, CH-RON does it automatically. So yeah, that's basically what you would need.
I get that your test board is kind of standardized for you, but how hard is to connect it to each phone? Because I guess every phone has its difficulty to tear it apart and to connect it electrically.
So the first time you do it with a device that is nobody has done it before and there are no pictures, it can be a bit hard. Honestly, I don't have that much electronics experience. I went to the house of a friend that's a corporate hacker, and we got it done in an evening while chatting and having coffee. So it's not that hard. You basically need to open the phone, remove the battery. I'm not sure if you can see it. Well, this is an example from a Fairphone. There you can see on the right, so batteries usually have some kind of integrated power management controller, and then you basically remove that from the battery, connect that to your phone, solder some wires, and that's it. You usually also need to find the actual operating voltage of your battery, because it can be quite different between devices. So yeah, you need to actually figure that out by measuring the battery and so on and so forth. Once that is done and you have a configuration file, the next person just have to disassemble the battery, get some pictures, and solder the wires, and then use the configuration for your device that has already been tested. So doing it the second time is a lot easier than doing it the first time. Yeah. Does that answer the question? Yeah, okay.
Thank you for your talk. I have a question about this. You mentioned that you get some legal stuff to get a legal entity or something like this. My question is about the most difficult part of this post-market OS, I believe, is GPU, like 3D, basically GPU drivers and everything. Especially for all devices, we have imagination, which is, we have lack of open source anything, basically. With this legal stuff, could you somehow make imagination to publish more open source drivers, for especially for old hardware, where still nice hardware, but we have no drivers?
I think in that regard, the greatest benefit of a legal entity is that people can do reverse engineer, assign the copyright to the legal entity, and then don't care about the legal liability, especially outside the European Union. In terms of actually GPUs, to be honest, Mesa is probably the best tested project I know. Like, the GPUs is the thing we have the least problems with. Maybe that's a surprise to everybody working on like laptops and so on, where that's the thing that breaks. This is the thing that everybody takes care of and never breaks for us, to be honest. So yeah, but in that regards, for reverse engineering, it will help remove legal liability from contributors.
Yeah, but basically with imagination as a problem, there is nobody, it seems, willing to actually submit this SGX or GX drivers, because there is now an open source something for exactly one device, but not for the tons of them from old market.
Yeah, I mean, I have to say that most of our community has the most experience with Qualcomm, so we, like, if somebody wants to look at a device with an imagination GPU, they are free to do so. We don't have as much experience with it, to be honest, because, well, Qualcomm has a bit more of an upstream approach, and that greatly benefits us. And then, like, yeah, the community builds around where the most support there is.
Okay, thank you. And one really short question. For Chromebooks, do you use a special firmware like Mr. Chromebox or something different
No.
to run, or just original one?
The original.
There's one more question here.
Yeah, thanks for the talk. This is more generic to post-market OS than the CI itself. As I tried post-market OS in the past on my OnePlus 3, what struck me is that there is a lack of consistency for end user, especially into the mobile interface for applications, because most of them are desktop applications. What do you think will need to happen into from post-market OS point of view for that to be solved? Do you think you will start to impose some guidelines or something like that?
In a way, if you talk specifically about applications, I think that's basically an upstream. I think something that has to be fixed upstream. So I end up contributing to GNOME upstream and becoming a maintainer because, well, I need a PDF that worked on my phone, and like I've not been the only one doing that. But like this is a bit more of an upstream problem that we have actively contributed to, and that upstream is actively interested in fixing both Plasma Mobile, GNOME, Phosh. They actually want to solve that problem. So it's basically a matter of collaborating with other projects to make that real.
Okay.
Thank you.
Thank you very much.
Okay, hi everyone. We're just getting started, okay. Hello everyone, welcome to our talk about RP Message KMS, DRM framework for display sharing in heterogeneous SOCs. Little bit about our company first. We are with Texas Instrument. We have an upstream first mindset, and this is a list of projects that we have contributed to. Something about us, I am Beleshwar. I'm a software engineer at TI, mainly working with IPC stack and now getting started with multimedia as well. I also have with me Devarsh. He's also an experienced multimedia engineer at TI. Okay, so let's come directly to the problem statement. A single line problem statement is we have a single display controller and it has to be driven by a safety context and a non-safety context. On the left-hand side, you can see, one second. Yeah, so on the left-hand side, this is driven, this is an automotive cluster example. This is driven by the real-time OS, which is running in the ASIL-D context. So here we have some telltale signs like speed warning, engine fault, oil pressure, which are very important for the system. We cannot have this going wrong if something crashes. But on the right-hand side, we do have GUI stuff, like navigation, cluster HMI, settings and diagnostics. All these things are good to have. These are also needed in GUI applications, but these are not fatal. If this goes wrong, there is nothing wrong with the system. We can still go on. Right? So the main thing is both of these things are running on a single physical display controller. So that's a problem statement, and here are some practical examples, like you have an automotive cluster display, for industrial HMI, in medical instruments. So let's talk about, we have two display sharing models to enable these type of sharing. I'll talk about the first one, which is the generic one, which is platform agnostic and can be adopted by any vendor who is following the IPC protocol that we'll be discussing. So here on the right-hand side, you can see the display controller is entirely in control of the MCU, which is running in the safety island. So the MCU has full access to the display register space, which controls the programming of the display controller. And the MPU, which has access to the GPU for all the rich GUI stuff, it doesn't directly have access to the display controller. What it does is basically transfers the frame buffers, the GPU rendered frame buffers over IPC to the MCU. And IPC here refers to inter-processor communication, which is happening via the standard RP message VirtIO stack and shared memory. Yeah, so for every frame the GPU is rendering, we are sending them over the wire to the MCU, which is then programming the display controller in its own accord. So there are some existing downstream solutions about this. One is the VDRM. So this is an example of the TI OMAP SoC, where you, on the left-hand side, you have Cortex A15 application core running Linux, and on the right-hand side, you have the Cortex M4, the image processing unit, which is running the Vision SDK stack application. So you can see the display output is entirely controlled by the firmware running on the M4 core. And on the Linux side, we do have a downstream driver called as VDRM, which is talking with the compositors, and it's exposing two devices actually. One is the standard DRI card device to do all the display, like integrate with the DRM framework, and then it also exposes another VDRM controller device, which is just a character device, which exposes the frame buffers over to user space, and user space basically reads this frame buffer addresses and sends them over to the remote core via IPC, but that's user space IPC. Now there are various problems, limitations with this approach. One is, the first thing is, you switch from user space to kernel space so you have a latency over there. And then so the IPC mechanism is happening in the application layer. So it just invokes a dependency on the application. So other vendors who wants to do display sharing, they will have to, do this type of mechanism in their application layer, which is creating a dependency on the application layer, not on the kernel. And then the last one is this is a downstream VDRM driver, so it doesn't have any integration with the DRM framework. And we do have a new approach where we'll get rid of all these limitations over here. So here we have, the ART5, which is doing the safety critical tasks, and here is the A53, which is the application processor running Linux and talking with the GPU. And the hardware is, again, entirely in control of the R5. But what we are doing here is we have a RP message KMS generic driver. So that driver understands KMS and it also understands RP message. So we are actually doing RP message IPC in the kernel layer now. So we are getting rid of the overhead of switching from kernel space to user space and getting rid of the dependency on the application as well. So we do have a RP message KMS a helper library kind of thing, which is just a group of functions which can be used by all the display sharing models. One of our model is the generic display sharing, which is the UC1, and the driver for that is RP message KMS generic. And you can see it for every data it wants to send, it has some RP message protocol messages, which it sends over to the remote proc via RP message, and the remote proc can decode the messages by its RP message implementation. And then it can just program the display controller based on what it received. And on the vsync, vblank notifications, it can also return a message back to Linux saying that we are ready for the next frame buffer. So key things here are, we only have one device, which is the standard DRI card. There is no controller hacky device that we had in the downstream solution. And all of this is happening at boot time resource population. So this is a runtime thing. It is not tied to just one firmware. OK, so let's talk about the stack of how this works. So on the top, very top, we have the RP message KMS driver that we was talking about in the kernel. And that is registered on the RP message bus. So there are 3 buses important in the IPC stack. One is the platform bus at the lower level, the Virtio bus, and the RP message bus. The platform bus has the remote proc drivers, which is responsible to turn on to the remote processor, control its power, clocks. And then you have the Virtio RP message bus registered on the Virtio driver, which takes care of, it's a low-level helper which takes care of sending data over the wire, creating channels, creating endpoints. And then on the top, you have the RP message bus, which is of interest to us because this is where we write our driver and we register it on the RP message bus. So all the things that you handle with KMS can be written in the driver that will be registered in the RP message bus. And when the firmware announces the RP message KMS UC1, so this is a name service or a RP message channel, this driver gets probed and we have our next flow that we can talk about. So this happens at the boot flow. On the right-hand side, you have the RTOS firmware, and this is the common RP message Virtio transport. On the left-hand side, we have the Linux driver. So whenever at boot time, when remote proc is probed and it announces the name service saying I support KMS via RP message, our Linux driver will get probed from the RP message bus. And what we'll do is we'll send a get topology message to the remote proc because we want to understand what is the topology of the display that is controlled by the remote proc. And the firmware will give a response back saying what video ports it controls, what video planes it controls, what are the connectors, and what is the topology. And once we receive the topology back from the firmware, we'll create, on the Linux side, we'll create virtual connectors, virtual planes, and virtual CRTCs and to integrate with the DRM framework. So this is happening at boot flow, only at once, whenever the system is booting. Now, what happens when you actually send data over, like whenever you're rendering some data through GPU or the compositor? This is the data flow diagram. Again, on the right-hand side, we have the display firmware, display hardware, and the left, there we have the RTOS, which is controlling the display hardware entirely. Here we have the kernel driver, and here we have the compositor, which is generating the data. So for every data it is generating, we get the atomic commit callbacks in the kernel, which gets translated to update plane messages that we have. So if the compositor is writing to multiple planes, we have the update plane message for each of the planes. So the update plane message just has the frame buffer address, the geometry, the plane formats, and all of that. So for each of the plane, we are sending an update plane message to the remote core saying that this is how you should program the plane, and this is the data that we are sending. And finally, we are sending one commit message to the remote core, and when the remote core receives this, it will create a single display context synchronizing all the planes it is controlling, and then it will program the DSS with the single display context. And once the DSS driver, the hardware starts scanning the frames, on the next vsync, the remote core will send a response, a vsync response back to the Linux saying that, hey, I'm ready for the next I'm ready to scan the next frame buffer, you can send me the next one. And then the flow would be the same. We'll send an atomic update from the user space, and then we'll send an update plain message, and finally we'll send the commit message, which will do this in a repetitive loop. So some highlights over here are, this is a zero copy handoff. We're not sending actual frame buffers over the wire. We are just, the frame buffers are stored in the CMA buffer, which is shared between the multiple remote cores. And we are just passing addresses, like the pointers to those buffers over the wire. One thing to note here is we are giving pointers to physical addresses. So if your hardware supports, if the remote processor has an MMU in your hardware, then you could actually send virtual addresses over the wire. Then the remote core can translate the virtual address to physical address, and that would be the best solution. And all of this is, and the Linux side, we have the virtual encoders that is created once we get the response back from RTOS at boot time. And yeah, we're not sending the data over the wire, we're just sending pointers. So these are some logs to look at. When you see, this is happening at boot time, whenever we do mode test output. So we see the virtual encoder, virtual connector, and the CRTC is being created. And this is from the driver logs. So whenever the first log is coming, when the firmware is announcing the name service, saying that I support RP message KMS. And then we can see the last log where it says that, so it got the data from the firmware saying it supports one plane, which is of the 1920 1080p format at 60 FPS frequency. So this was about the UC1, which is the generic display controller model, sharing model, which can be adopted by all the vendors following the IPC protocol. Now we'll move on to the second use case, which I'll invite Devers to talk about.
Yeah, thanks, Bileshwar. Yeah, so UC1 was all about MCU owning the full DSS or the display controller register space. But I think some SoCs, such as the TA SoCs, they have the partitioning feature in the display where it has multiple interrupt regions, multiple register spaces for each host. So you can basically like have a single display controller being programmed by multiple host entities. So this one, the advantage is like there's no IPC required for the data flow with this model. So here, like we have the same heterogeneous system, but in this case, MPU is also accessing the display controller for some display context, and the MCU is also accessing the display controller. So we had some existing downstream solutions. I think there was one talk we gave in 2024 USS where we explained the downstream solutions, and we had also posted a patch upstream. We got some feedback. So based on that, we came up with this new generic scheme. So just a quick recap of the static partitioning model that we have in the hardware, right? So you have like multiple interrupt regions. You have one interrupt region controlled by the RTOS core, then you have another interrupt region controlled by the Linux core, and Linux cannot access the RTOS interrupt region. Similarly, this is a display controller, so you have like various display resources like video planes and the video ports, and these can be assigned to the specific host entity. So for in this example, Linux is owning this video pipeline, then it is firewalled to access the resources which are owned by the RTOS. Like it just owns this video pipeline, it cannot access the video ports of this display pipe and also the resources of this pipe. And it can still have the read-only access in case it wants to see what the resolution RTOS had programmed. So this is the hardware model that we have. And so there are like two use cases we support, right? One is like you have a full display pipeline owned by the Linux, like you have one panel, let's say a DisplayPort panel, which is fully controlled by Linux right through the whole pipeline. And then you have another panel, let's say a HDMI panel, which is controlled by the RTOS, the full display pipeline, right? So in the existing solution, what we use is like, we had the firmware with the static partitioning information, and then we have that device tree attributes where we say like, okay, the TIDSS driver is being used in the shared mode context. And these are the video ports that we have, like video port 1, that is this one. and video port 2, that is S2. And out of these 2 video ports, we have like Linux owning the first one, and the next one is Linux is not owning, but it can still use the planes to display the context, but the video port registers are not owned by the Linux. Then you have the register space, like we have multiple register space for each host. So which register space Linux is using and which video planes Linux is owning. So video ports, as a rule of thumb, right, the video ports or the CRTCs, they can be used in the shared mode, but the video pipelines, it can only be owned fully by one entity. And then we have the interrupts, like we have unique interrupts going to each host. So which interrupt line is going to Linux, that's what we give here. Then we have another use case where Linux is only accessing like one video pipe and rest of the display is fully in control of the RTOS. So that it's a little bit more simple, like you just say which video port the Linux is sharing with the RTOS, and Linux is not owning that. So we set it 0 here, and the rest of the information is similar to what we provided in the earlier case. Yeah, so this is the new framework that we came up with, like it's in conjunction of the RPMessage KMS helper library, which Beleshwar described. So here there is no RPMessage KMS generic, so we are just using the RPMessage KMS as a helper library, and it has some functions which we can use to create virtual connectors. It has some standard lifecycle IPC messages, like to notify on the suspend and the resume. So here you have the R5 core running the RTOS, and it has the same RPMessage service, and it owns the video ports. And on the Linux side, we use the standard TI-DSS driver, the TI's DRM display driver. It registers directly as a platform device, but it also has access to the RPMessage KMS library, using which it registers also on the RPMessage bus. And it uses a different message. It's called get partition. So with get partition, we are querying to RTOS, like what is the partitioning structure, like what resources are owned by the RTOS, what resources are owned by the Linux, what resources are in the shared mode. So we get this context using this get partition message, which is a 0x40 message ID. And based on that, Linux will be programming its own resources, and RTOS will be programming its own resources. So here there is advantage here compared to UC1, like we are not using any IPC for the data flow. It's just at the probe time we query like, hey, what is the partition information, and RTOS just informs us, and then we are done with that. Like after that, there is no IPC for transferring the frame buffer addresses and all. Only IPC we use will be the suspend resume notification that we would be sharing, which will be using the RPMessage helper library functions. Yeah, so this is the flow. Like if you have like 2 video ports that are controlled by the, like one from the Linux, one from the RTOS, right? So the Linux one, we would be like, if the Linux is owning the video port, then Linux will be instantiating that video port using the same flow as any standard DRM driver. It will query the edit. It will instantiate the connector, CRTC, and encoder topology as any general DRM driver. But if it sees that the RTOS is owning that video port, then it will just query the partitioning information from the RTOS and create virtual connectors and coders using the RPMessage KMS helper. And it will use the register space and the interrupts which it's assigned to its own from the partitioning information. Yeah, so I think this slide also shows the same, like we skip some of the standard functions of the DRM if RTOS is owning the video port, and we go directly creating the virtual connector, and then we iterate over each of the video ports based on the partitioning information that is received. Yeah, so the basic architecture, right? I think one thing we need to do is like we have this display context like for all the display controller resources that are present in the display controller, like how many video ports you have, or how many CRTCs you have, and how many video planes you have. So what we want to do is like we want to run one function which truncates this based on the topology that RTOS is sharing with the Linux. So let's say if RTOS is owning the video port 2, overlay 2, and the other resources, then we will just remove this from our structure by calling this API. So this is the main API that we are using. And the rest, this model, I think up to the RP message bus, it is same as what the UC1 we have. But here we have only the TI-DSS driver that is resting as a both on the platform bus and the RP and also on the RP message bus. So during the init, it registers on the RP message bus, and after that, when the name service announcement happens, then we call the get partition information. But it's the TI-DSS driver only which is in control of the display controller. So here is the boot flow. I think this flow is generic flow, like you register the display driver, then when the U-boot comes up, the U-boot loads the remote firmware, and the remote firmware does the name service announcement. And when the name service announcement happens, we trigger the RP message probe from inside the TI-DSS driver itself. And based on the partition information, we program the display registers accordingly. And the data flow is different from the UC1. Here you can see that on every atomic commit, we are seeing that if it's RTOS own video port, then we skip programming the video port and we simply program the planes that are owned by the Linux. But if it's a Linux owned video port, then we would be programming the video port registers as well. So in this case, we are just this case is the scenario where Linux is just owning the video pipeline. So here it's just programming the video pipeline registers and skipping the video port, and the RTOS is programming the video port registers. And we have unique interrupt line for the Linux host, so we don't need an IPC here also. We just get an interrupt when the RTOS is done with displaying the video frame. Now here's an interesting one, like suspend resume scenario. So let's say you have heterogeneous system running, and let's say there is a suspend triggered from the Linux user space. So in this case, the display context from the Linux will be going off, right? So the resources owned by Linux, they would be sitting idle. So in this case, like RTOS, what it can do is like it can program those registers that were owned by the Linux, program that plane which was owned by the Linux, and display some screensaver or some application and reuse those resources when the Linux is not using those, right? So in this case, whenever, let's say, user triggers a freeze, then the suspend call gets triggered, and here we send a IPC message to the RTOS that, hey, Linux is going to the suspend. You can reprogram the display if you want, and once the RTOS acts it, then we go to the suspend, and when the Linux is going to resume, it again sends a message. Then RTOS can do the cleanup and restore the display context and reprogram the display registers with the frame buffer address which was owned by the Linux, and then it can trigger the resume done act message to the Linux. Yeah. Okay, so I think we are done with the data flows. Here are the RP message IDs that we are using. I think up to the get partition, before the get partition, all these messages are the UC1 generic messages. Like if you have a simple display, then you can use the get display info. If you have a single display with simple display topology, and if you have like multiple displays, then you can use the get topology call to query from the RTOS, like what is how many display connectors you have and what are the resources instantiated with that display. Then we have the update plane and the commit messages and the vsync messages coming from the firmware to the Linux, and the suspend resume messages that we discussed, and also the error message is also there, like from if firmware want to share any error message to Linux, then it can share using this. And then after the 0x, starting from 0x40 range, we have the vendor specific messages, like for example, TI supports this heterogeneous partitioning, then it has this get partition TI message using which it can query the partitioning information. So here, as you can see, right, unlike UC1, it's the TI-DSS driver itself we are using, and if we just do a mode test output, then it shows the connector as a virtual one because the video port is owned by the RTOS in this case, and it shows like what resolution and refresh rate it is configured with. And this is some logs taken after the boot up. So you can see like on the probe for the TI-DSS, it sees that, okay, it is running in the shared mode context, so it calls the get partition call, and it receives the partitioning information from the RTOS, like what register space it owns, what video port it owns, what video planes it owns, and displays it. Yeah, so these are some of the structures that we are using in our driver. These are the UC1 structures. So as you can see, like we are using the topology structure and display infrastructure for the simple displays. Then in the update plane callback that we are doing the IPC, we are sharing the frame buffer metadata that we receive from the GPU, right? What is a frame buffer address? What are the width, height, stride, and what are the coordinates? Like if you want to do scaling and cropping, then you can use this coordinates to pass this metadata for the source rectangle and the render rectangle. Then there is a commit message where there is output mask which specifies like if you have multiple displays connected, then which display you are asking to commit. Then you have the fence IDs to which the RTOS can reply to with a unique identifier to convey that, okay, this particular commit has succeeded. And yeah, this is a topology response, like how many displays connected, how many planes connected, which RTOS can convey using this structure. And if the RTOS firmware also supports suspend resume functionality where RTOS can own the resources when the Linux is suspended, because RTOS will never be suspending, like it's always on core. So in that case, it can we can use this lifecycle messages for the suspend and resume. And here are the UC2 specific case, like we are just adding some fields in the existing TI-DSS device, like what video port Linux owns, what RTOS owns, and what is the partition response that we get. So we are using this structure which the RTOS has to fill, like what are the video ports which are being used in the shared mode or in the owned mode, and out of those video ports which are being owned by the Linux, and what is the metadata related to those video ports, like how many video planes you have and what are the max resolution supported. Yeah, so now the device tree looks simple. So there is only this TI-DSS shared mode attribute that we are using right now. I think we are also trying to see if we can use a separate compatible for conveying that we are using this in the shared mode. Then the power domain, we specify to the device manager that the power domain for DS is being used in the shared mode. So when the Linux, even though if Linux is suspending, since the power domain is in the shared mode, the RTOS still holds a reference to the display power domain, so it doesn't switch off. And then you have the interrupt ID, and then if the RTOS supports the suspend resume takeover functionality, then you can specify this additional attribute as well. So this also we are working with the firmware to see if we can get rid of some of these attributes as well and simplify further. Yeah, so the files, they look like this right now. Like we have the RP message KMS directory. This is all generic drivers, like it can work with any display controller which has this heterogeneous, present in a heterogeneous system. And we have some new files in the TI-DSS driver which register on the RP message bus and use the and has the link to the generic header files that are shared between UC1 and UC2. So if you want to just enable a UC1, then you can just set this flag in the def config to enable the RP message KMS. And if you want to use the UC2, then you have to enable this kconfig in the def config. Yeah, so these are the references we have. This is a talk we gave with the static partitioning scheme in the EOSS 2024, and this was the RFC that was proposed using the static partitioning scheme, and where we received some feedback if we can generalize that. So compared to what we had proposed, I think there are advantages here, like the Linux side is simple now, like I don't need to specify the partitioning information in the device tree anymore. But there are like some additional work on the firmware side to instantiate RP message and convey that information to the Linux. So yeah, I mean, but it still overall is a good story to simplify, like I don't need to change anything on the Linux for different partitioning context and which we can use. So yeah, thanks to Texas Instruments and Embedded Recipes, and we have a demo running in the demo booth for both of this UC1 and UC2. So feel free to take a look, and if you have any questions, then feel free to ask. And yeah, I'm open for questions. Thank you.
So instead of going for this RP message KMS approach, why can't you just expose Word GPU to the host? I mean, I see that, so the problem you're trying to solve is that Linux cannot access the display controller, right? And you want the RTOS or the safety island or whatever, the secure element to access it, and that should act as a proxy, right? And if you expose Virtio GPU device to the, the Linux or whatever operating system, then you are actually you're actually solving the same problem, right? And then the beauty of this approach is that you don't need to write a new front-end driver on the Linux because you already have a GPU driver. You just need to write the back-end driver on your RTOS. And I think it will solve most of the issue that you are talking here.
Yeah. So we did this comparison of Virtio and RP message, and only Virtio is actually good in almost all the cases. There was just one use case where we had, so we have a SoC which just has one single remote processor, and Virtio actually uses, so you cannot multiplex on the same memory, but so for every device you need a separate set of V-rings. So our remote processor is doing multiple other things as well. So it's so this display sharing is one part. It's also doing device management things, and it's also running IPC, generic IPC tasks. All of it is multiplexed over a small memory section, just 2 V-rings with RP message. But with Virtio, you'll need a separate set of V-rings for display sharing and separate set of V-rings for normal IPC, normal device manager, and that we analyzed the memory constraint, but it was, we just have one single processor and the memory was huge for it. If you use Virtio, that's why we wanted to go with
I'm not too sure about that. I think it should still be possible to expose 2 Virtio devices from a single physical device, because I think your remote proc itself is a Virtio device, right? So it's an RP message Virtio device, and your concern is that how can I expose one more Virtio GPU device over this physical device? I think it should still be doable.
No, we can expose, but the memory footprint would be more. Because for Virtio, a Virtio device will be having separate set of V-rings, and the RP message Virtio device, separate set of V-rings.
Yeah, but the V-ring is not going to occupy tons of memory, right? It's you're just going to transfer the frame buffer, right, between your remote proc and this, and I don't think that's going to occupy too much of memory.
No, we just the addresses, yeah.
Maybe, I mean, you just an idea.
Sure,
so
yeah.
you can just
Yeah, I think there were 2 things to it, like the firmwares that we support, right? They already supporting some service which are RP message based, so it's easier for the firmware to just instate another name service just for the KMS because it's already having the RP message channel using the same one here. And the other is like we wanted to integrate with our vendor specific partitioning scheme that we have. And since it's only dealing with the life cycle messages and not the actual buffers we are transferring. So I think we discussed the Virtio maintainer or OpenAMP call as well. I think he was also convinced that if it's just a life cycle message and not the V-rings being used to transfer the actual data, then RP message is a more simpler solution for customers to adopt. So that's what we discussed with the display maintainer and also with the Virtio one. But yeah, I think that's some overlap with Virtio, so we'll see if something that can be done. Yeah.
Sure.
Thanks.
Hi. So back on slide 23, when you had the shared partitioning flow, how do you prevent? Is it this one? No, sorry, 22. One before. Yeah. So in this case, where you have Linux is programming the plane setup directly into DispC, and the RTOS is programming the Go bit on the CRTC, and there's no communication between them. How do you prevent that from effectively tearing updates, right? Because the RTOS could set Go whilst Linux is in the middle of updating multiple registers and you have incoherent configuration, or how is there a synchronization model you had in mind, or is that something?
Yeah, so there are like hardware we support the shadow registers. So unless and until all the video planes from all the entities are programmed, and when there is a VFP, then only those shadow registers become active and synchronize the video ports together. So even if like Linux is, let's say, programming the video pipeline with all the attributes, but Linux is also receiving the same interrupts, RTOS is also receiving the same synchronization interrupts from the display controller. And when all the video plane are programmed by the host entities, then only, even though you program the VP bit, it takes into the execution part only after a certain point, the VFP, when all the video planes context is consumed by the video port. So we have this shadow register mechanism in the display controller, which synchronizes all the video planes together on the VFP, and then it takes into the effect, and on the next VSync it starts displaying.
So effectively, each plane has its own Go bit to let you know when it's safe to update shadow, or?
No, the Go bit is specific to the single video port, but the video planes, like you can have multiple video planes from different host entities getting programmed, and those we are programming after the VSync is received from the previous frame. So those registers are programmed, then on the RTOS it sets the Go bit, but the actual Go happens only at the VFP of the current frame, like when the current frame is almost getting displayed and there is a VFP sync signal. At that time, until that, so you have that window until the VFP for all the hosts to program the video registers, and at the VFP, the actual Go will happen, even though RTOS has set earlier.
Right. So, yeah, that makes sense. But then, in the positive direction, how do you expect the RTOS to know to assert the Go bit? So, user space would do an atomic commit and leave that there, but until RTOS decides to set Go to latch the configuration, that's just not going to take any effect, right? So do you see that user space should also be separately pushing something to RTOS to let it know that a new frame is available, or do you expect that RTOS would just be doing this every single frame anyway?
Yeah, RTOS will be doing it every single frame, but since we have this one big window for the full frame where all the host entities can program the video registers, and even though RTOS, like it sets the Go bit, it will take into place on the VFP, and until that VFP occurs, like it has that window for the other entities to program. If some entities have missed that window, then those video planes are not synchronized and you will miss the display context for those frames. But yeah, and with this shadow mechanism and this VSync synchronization, so the IPC is only, there is no IPC actually in this UC2. We are just using the interrupts to synchronize between Linux and RTOS once we get the partition info.
Yeah, it makes sense. I guess the issue I see is just that, the display controller could assert Go whilst Linux has programmed one plane but not another plane. So as you say, you end up only displaying half the desired configuration, so it's not really atomic anymore.
So yeah, user space has to program within that one frame window when it receives the VSync. If it misses, then it misses to get a part of display on that frame for that particular frame of the missed window.
Okay, thank you. Thank you both.
Yeah, thank you. Yeah.
Check again. Okay. Good morning. My name is Francesco. First time presenting, but don't be gentle on this. So my presentation will probably have too much words, too many errors, not enough figures, but let's ignore that. So I'm presenting today about one of my most recent works about DRM-based in-kernel boot splash. Something about me, I'm from Italy. I have worked in the automotive field for an automotive tire run in the last 10 years, more or less, okay. I do Yocto, I do hardware bring-ups, I hope not to do many bugs, many problems. My motto is today's workaround is tomorrow's problems. Yeah. So, what's a splash or splash screen? It's something graphical, showing before a system is ready. Actually, can be a plain color, a static image, an animation, sound, videos, and so on. Even a blank screen, maybe on older devices, the user is expecting to see something when they turn on their device. And if something appears right away, they won't be bothered to say, okay, this device is not ready. Yeah, it's ready. It's showing me something. This, for example, is my kid's toy camera. Okay, it shows the welcome screen in about half a second. That's acceptable, and then it's ready for acquisition maybe after 5 seconds, more or less, but it's ready. Okay, so my kids say, okay, this is on. This work is part of a broad initiative, not cited here, by Tim Bird, okay, about the boot time special interest group. Tim has, let's say, mentioned this work, so I will mention Tim's work. We are working on boot time, let's say, investigation in the kernel and user space and bootloaders and so on. And splash screen is one, it's not really a solution, okay? It's probably a way to make the system appear ready, okay? So, but for the end user, it's still ready, okay? So boot time is more or less reduced in this way. For a splash screen, there are many solutions. These are some solutions. I probably forgot something, okay? Bootloader based. So U-Boot has had the config video option for quite a long time. Platform support, so drivers for actual graphic cards or IPs and so on is mixed, as far as I know. Yeah, the thing here is what happens when the kernel actually wants to jump in. We have tiering, we have flashes, we have, so visual artifacts that the user experience probably is degraded, okay? The same probably is there for Barebox. I'm a Barebox fan, but I don't use Barebox every day. I found the splash option, okay? It appears to be more or less the same thing, so graphical image on the screen at boot. The same thing for Barebox applies. So what happens when the kernel wants to jump in, okay, and resets, for example, the graphic controller? Then we have kernel-based solutions. The first one, albeit probably not really a splash screen, is the historical logo, okay? So the penguins on top, in the top left corner. They were made more or less configurable recently, pretty recently. So last year, end of last year, by Vincent. I won't try to pronounce his last name. Sorry, Vincent. It depends on the frame buffer subsystem that is, okay, side note, I'm not really a graphic developer. I'm not a DRM expert, okay? So probably I will make mistakes. Please correct me so I can learn something new. So config logo depends on the frame buffer. Is only 216 or 224 colors, so not really suitable for modern systems, probably. IFI systems does expose the logo we see, for example, on laptop startups. Okay, so we have an area provided through an ICPI table called the BGRT table that carries from the UEFI bootloader to the user, even the user space. We'll see it in a moment. The graphics from the OEM, okay, that can be then reworked by the bootloader and so on. There is an FEFB driver inside the kernel that exposes let's say the frame buffer provided by the UEFI bootloader, and then is able to draw the image from the UEFI, from the ACPI BGRT table there, okay. Again, depends on the frame buffer subsystem, okay, so probably not much future-proof. There were a couple of other attempts in the past. Another one based on FBdev, FBcon by Max Stott, okay, in 2017. It encountered some opposition, mainly because it was based on this FBdev, FBcon subsystem. Then we had a work similar to mine, let's say, to my proposal. When the DRM client API was proposed, I will come to that in a moment. Attached to the initial patch set, there was a splash screen client, okay. It was marked as an example. It did not reach mainline. The same patch set carried a update to the to-do for the DRM subsystem, marking the splash screen as not supported, okay, so this was clearly an example. Still interesting though. Then we have user space-based solution that are probably used by most of the system today. Plymouth probably is the most used one, supported by all the major distributions, well integrated with systemd. It runs from the initramfs, as far as I know, at integrated teaming support, Lux encryption unlocking support, support for the aforementioned IFI provided splash, so it can read through a sysfs the BGRT table provided image and show it on the screen, maybe with an added logo and so on. It has a huge number of quirks for all known platforms on Earth, so obscure laptops models that expose wrong UEFI data through this BGRT table. For my use case that we'll see in a moment, it was too heavy on the dependency side. So libdev, Pango, Cairo, and so on, so it's pretty heavy. psplash provided by the Open Embedded Core. is very simple, based on the frame buffer interface, but DRM port has existed for quite some time. Very few dependencies, to be honest, just libc, pretty light, pretty much integrated in the Yocto subsystem, okay? Yeah, so but the basic flavor, let's say, it's based again on frame buffer devices. Other solutions, I found Platch, I think it's pronounced, by Pengutronics. I developed a number of solutions along the years. My colleagues did so as well, based on some on GStreamer, some on custom brewed VPU interfacing things, and so on, okay? The more the complexity is, the more the solution in this field becomes, let's say, custom. Yet another solution. So I'm pretty surprised that this is the first XKCD comic today, okay? So yeah, yet another solution, yet another standard, yeah, probably. The proposal we are talking about today is an in-kernel Splash client based on the DRM client API, able to display either the BMP image supplied by the IFI BGRT ACPI table, okay, a bitmap image, load this firmware. I work mainly on ARM platforms, okay, so without all the UEFI stack, so for me the BGRT table is not there, and I need to load the image as a firmware. Or a simple colored background, because we said that most of the users are pretty satisfied for consumer devices, maybe, with a color, okay? So the device is alive, at least, okay? Why in kernel can run even before the initramfs is unpacked or without an initramfs. In the embedded field, in my experience, initramfs is there sometimes it's not. Can reuse kernel code, we'll see the APIs in a moment. Complexity, on the other hand, can grow pretty quickly. If we are talking about animations, videos, sounds, and so on, it's probably unmanageable, because APIs don't exist for the in-kernel users to these subsystems. I think, for example, of GPUs, VPUs with maybe firmwares and drivers and so on. Oops. The true reason behind the proposal was, let's say, strange panel, okay? Scale is in milliseconds, okay? So I encountered a panel needing more than 1 second of valid LVDS data to be fed to it before being ready to receive a backlight. And I had a note in the datasheet stating that permanent damage can happen to the device if the backlight is applied before the 1 and second. With a time budget from battery on to display of 2.5 seconds, that was pretty difficult to do in at least from a user space. I implemented a solution with some pre-init execution of something displaying a black screen for all the DRM chain to start and the connectors and coders to properly initialize the device. I'm not satisfied today with the solution. Couple of side notes about the DRM client API. It has existed for quite a long time. It's meant to provide in-kernel users basic DRM access, so think about libDRM, but for in-kernel users, okay? First user was the frame buffer device emulation that is currently using this client API. In 2024, a new client appeared, the log client. This is a KMS message displaying system based on this, let's say, write only, okay? So it is not able to receive input, so it's not a replacement for FBCon. It can only display messages, but probably for most embedded devices is sufficient, okay? The DRM draw is probably something that can be used along this DRM client. was developed as part of the DRM Panic infrastructure. DRM Panic is not really a DRM client, okay? It's implemented slightly differently. But most of the functions developed for the DRM Panic client, so the blue screen or black screen of that for Linux, so fill functions, bleed functions, and so on, can be reused by clients, okay? How the proposed client will work, okay? Is registered when a DRM device is registered, then listens for outplug events, okay? And then reacts through 3 different contexts, let's say. So the outplug event is managed in the DRM driver context, okay? So let's say in the outplug callback. Then the firmware load and the image, if our firmware load needs to happen. So if we are loading a BMP from a file system or from the in-kernel firmware storage, let's say. These operations happen in a dedicated thread, okay? And so does the bitmap conversion, okay? So a bitmap file is loaded and then converted, if the need arises, to the format, to a format that the kernel is able to display, okay? So, or better, the graphic output is able to display. Yeah, we have some diagrams. Let's leave it to the slides, but more or less the buffers are located in the outplug context, then firmware load context, the BM file is loaded and let's say parsed, but the actual conversion happens in the render thread context, okay? There we draw the background always, so the colored background with a configurable color, and then we bleed the image on top, okay? The image source is selectable, so UEFI BGRT table can be enabled or disabled, BMP image from the file system, or better from the firmware storage, or the simple plain color is enough, probably enough for some systems. Current status is not compiling, unsurprisingly, okay? I sent the 3rd version of the patch as an RFC just before the event, so on May the 10th. Many thanks to the reviewer for the first 2 versions, okay? Because I received some very positive feedbacks, okay? Some opposition, yes, but positive. Yeah, thank you. It is not compiling in a specific setup where the DRM client infrastructure is a module, but the AFI BGRT table is compiled in, okay? But yeah, the system is working, okay? More or less. Showcase here, okay? So it's working, works on my PC, actually. No, works on a number of embedded platforms, works on QEMU, okay? Some open points still remains, so rotation is still not managed. I'm not sure it can be, okay, because it will take some time. Then I encountered this tiled screen setup that seems to be only on some Intel platforms when multiple screens are sharing the same buffer at the kernel level to compose a single image starting from different buffers. I didn't really find documentation for it. Limited testing, okay. More than that, I need your feedback on is there interest for such a client? For example, the BMP image format the right one? Yes, it's simple to parse. It's part of the ACPI BGRT specification, but it's enough. It's the right one. I am forgetting something. It may be, okay. Yeah, so if you have comments, ideas, critics, you can find me during lunch, after lunch, or on the mailing list. Thank you.
For 1 or 2 questions before lunch.
I hoped lunch would save me from questions, but...
Sorry.
Right, so I think the general problem you're trying to solve is very valid, and we've all had like pain with boot splash at some point in our embedded Linux life, I guess. But one thing I'm really sort of uncomfortable with your proposal is the file format. So the thing is, there is a notorious rule in the kernel that we shouldn't have parsers in there. And you could say, okay, yeah, BMP is it's simple, right? Like it's safe to parse it, right? And then somebody comes along and says, oh, but actually I want PNG, or then I want JPEG and something. And so it's a kind of like a rabbit hole you fall into, and eventually, you know, we end up having like a full image parsing library in the kernel, which is definitely something we want to avoid because of like security concerns and things like this. So I think this sort of file format thing is kind of problematic, and personally I would be much happier with just the raw like pixels, which would be just data. So that would be, I don't know if you got feedback already about this part, but to me it feels like you're opening a door that might lead to some pretty bad consequences down the line.
Yeah, actually yes. First version of the RFC patch, if I am not wrong, was based on raw files. Okay, they are probably even faster because I can have a raw file tied specifically for a platform, so in its specific format, avoid mode setting at all, avoid things like that. Problem is that would add complexity, let's say, to the build side of things, okay? Yes, it's for embedded system, but then I received feedback about this kind of Splash client being suitable also for desktops, for example, or laptops, to avoid let's say, the couple of seconds of black between the UEFI and the Plymouth, typically, that is running on the system. This probably would allow manufacturers or integrators to have a smooth transition, at least between kernel and Plymouth. Then I switched to BMP, a limited, let's say, subset of the BMP huge file format, so RGB24 and RGB, no, only the 24 bits, okay, because that is, and in my memory was, but while doing the presentation, I discovered that the UEFI is specifying also the 32 bits per pixel format, okay? Because that was the format used by UEFI BGRT, okay, to be honest. And that's simple enough. Probably, if I remember correctly, there are some sort of compressed formats inside the BMP that these are not supported. So it's like having, let's say, a raw file, okay, with an header on top. I did not really introduce a parsing library because it was already there for the IFI FB driver. Okay. Yes, I'm completely in agreement with you. Please no PNG or JPEG or because that would add complexity and probably would defeat the initial purpose of the client: simple, fast, light, and so on. I would need compression, because if I am putting the firmware inside my kernel image, okay, for big screens, for example, 4K screen, the image itself can be pretty big, okay? So if I have a small logo in the middle and then a colored background, that's easy, okay? I have a small image and then colored background. If I have a full screen image in BMP format, I can grow to several megabytes. That have to be loaded from the storage, I mean, eMMC, UFS, you name it. Yeah, so this is one of the open points. On Phoronix, I think someone suggested the PPM file format probably is even worse, in my opinion, because it's even less compressed. There exists probably some sort of compressed format, but yeah.
Yeah, just to add two things. So the first one would be that there's also like frame buffer formats like RGP565 that you wouldn't find in usual file formats, even BMP, right? So you would need some raw thing. And then about compression, you could definitely use the existing compression stuff that we have, which doesn't require like parsing, right? So you could use LZMA, whatever we already have. You might even be able to hardware accelerate it, so that would be great.
Yeah, well, on the compression side, on the file formats, if I understood your question, I am converting images from one format to the other using the DRM Draw APIs. So conversion is already supported. Yeah.
No, but like that's too slow. Like you cannot expect to runtime convert an image to another format for the frame buffer. So you really need to store it like in a.
Yeah, theoretically it works. Let's say, okay. In practice, yeah, it defeats probably the purpose. On the compressed format, I wanted to stick to, let's say, old plain firmware interfaces. So if the kernel image is compressed, the firmware is compressed, okay? If the firmware is on a file system, I can use support for compressed firmware already in the kernel. I believed last year in December that I can put compressed file inside the in-kernel firmware storage. That's not the case, okay? It's on my to-do list to investigate in that regard, to be able to, let's say, not overcomplicate things inside the client. Client today is 800 lines. I wanted to reuse as much as possible APIs from other subsystems. So, yeah.
Thank you.
Thank you.
Okay, let's go have lunch. We'll meet back here and restart things at 1:30. See you soon.
It was fun. Thank you. Thank you for the opportunity. Thank you.
it's HDMI.
HDMI direct?
I think that's what I get is the most more reliable, right?
Okay, welcome back. People are trickling in from lunch. Hope you enjoyed your lunch. Just one quick announcement. We've had a couple of things get lost and found. So up here on the stage, I cannot confirm or deny whether somebody left the hotel room key for the Radisson. So if you're missing your hotel room key, and then there's like a USB. I don't know if one of the speakers maybe left, but a USB like pointer, mouse clicker, laser pointer thing. Also, I found on the floor up here. So if you're missing stuff, and if you find stuff, let's just bring it up here. We'll have a little lost and found corner here. And with that, let's launch it off with Andre. Go ahead.
Thanks. Yep. Yeah, hello. Thanks for coming after lunch. So, my name is Andre. I'm with ARM. And today I'm going to talk to you about live firmware activation. So first, the agenda. The most important stuff first. What the hell is this about, actually? And then I will briefly talk about some components that are involved in that order. So about me, I'm in the Linux ARM kernel team with ARM, like for 12 years now. I'm also doing firmware stuff, so on trusted firmware, where I'm also a maintainer and working with TFRM team. And on the side, it's more a side job, I'm also the Allwinner platform maintainer for U-Boot. Yeah, so LFA, sorry to give you another three-letter acronym, right? So it's not one of those, especially not the legacy Fighting Alliance. LFA stands for Live Firmware Activation. It's an ARM spec, so rather innocent, and it describes discovery and activation of updated firmware components, which is quite a mouthful. What it actually wants to say is it allows firmware update without a reboot. So that's pretty cool, right? I'll give you a second to put up your wait what phase. And it is somewhat interesting and wacky. But what it does, because it's a spec, it describes just an interface, right? And if you have crossed paths with ARM specs before, then you know all the interesting part is actually implementation defined, right? So they leave it up to you to solve the hard problems, and the spec is rather innocently describing what it's expected, what you do. So what it basically does is you see there is a so-called LFA agent, which is some kind of miniature thing, that lives in trusted firmware or in EL3 runtime, whatever you use for that. Typically, it's TFA BL31. And there's some user, which is typically the kernel, but it could be anything running at lower yields, and that requests a firmware to be activated, as we call it. And this is then left up to the agent to deal with how it exactly happens, so where to get the firmware image and how to prepare the firmware image and how to make it happen that basically is kind of a seamless update happening. In its core, it's just those SMCCC compliant functions. So you start with LFA version, which, how the name applies, just gives you the version number. But it's also your anchor for detecting whether you have that, because it's SMCCC, so if you call an unknown function ID, you get -1 back. That's what the spec says, right? So you just can probe for this. You don't need to look at device tree or ACPI to know whether you have it. You just call that SMCCC thing, and then you know whether you have it or not. Then you can query what kind of features you have implemented. Then you say, and you ask for how many firmware components you actually support. And then you call this LFA get inventory on each one of them and get some information back. And once you've set your mind and said, okay, I want to update this one, this is a two-step process. So first you call LFA prime, which does basically longer running stuff. So typically that's like if you need to copy this stuff or load it from some storage, copy it, or you do authentication first. So that is what takes longer, that you should do in the prime. And then there's the activate, which is just the final step to actually do the switch over. And that's supposed to do, to be very quick. And this is the very brief period of downtime from the kernel point of view, which you experience, because everything's happening there in the firmware. For that, depending on the firmware component that you update, you might need this, what's called CPU rendezvous, which means that every core should go into the firmware. This is done for two reasons. Depends on the firmware, type of firmware that you want to update. It might need, the firmware for reinitialization, it might need to touch every core. Because, for instance, you want to apply errata workarounds, or you want to set up per CPU stacks or something, then this firmware image, of course, needs to run on every core. So every core needs to be accounted for and needs to be running. And the other reason is that it's really hard to guarantee that while you're doing this update, there's no one asking for an actual firmware service, and you don't want to really do this. Because as you can imagine, if you're just in a process and there's a request coming in to do something, and we try to block this from the kernel, but it's pretty hard because, for instance, SMCCC, once discovered, it's available, right? So for instance, there's hardware random number generator as an SMCCC service, and this kernel does this somewhere in the background. There's a timer, and when it runs out, it just goes ahead and queries a new hardware random number, and you cannot really block this off. You don't want to kind of, it's not kind of isolatable, and so yeah, that's why we have this CPU rendezvous. It's not for every kind of firmware, right? So there's, for instance, the firmware images is very generic, so it's not restricted to what's running on the core, on your main cores. It could be some SCP, it could be some BMC, whatever. So it's all, and for them you might not need the rendezvous, so it's optional, but you need to take care of that. Also to note that the spec is not concerned about the image updates itself, but just the activation. So that's left as an implementation defined or for something else. So the LFA agent, it's a SMC handler component in trusted firmware BL31. It handles those SMC function IDs, and it does all the usual boilerplate for dealing with SMC calls. And tracks the state. As I said, you need to first prime and then activate, so it takes care of that. And it takes care of the CPU rendezvous. And it expects the updated image to be available, and it does that through platform hooks, right? So again, like all the interesting parts are left for the reader to implement, basically. So you are expected as a user of that to provide all the necessary bits. And the code is actually mainline since November. And for now, we support TFRMM as an example firmware. I will tell you in a bit what it is. So from the kernel side, so this is the agent side, and from the kernel side, you need some Linux kernel control. It's on the face of it, not too much, because all you need to do is kind of figure out what is available and then do the SMC call and say, please do it. But of course, devil is in the detail, and there's a lot of issues. Also, the kernel, at least the current support code that I wrote, just assumes that the updated image is already in place. You have updated it via whatever mechanism you already used to update it. But instead of rebooting, you now say, please activate. So that's kind of the idea. And again, the details are out of scope on how to do this. And there's a SysFS interface I came up with. And so this is how it looks like. So there's a directory LFA in sysfirmware. And for each firmware component that has been discovered, there's a directory, which is represented by the GUID. So please don't shoot the messenger GUID. I think in the end, it's the only viable way to differentiate the firmwares, because naming is not really consistent, and there will be always very platform and system-specific firmwares, so you cannot really anticipate and put a list in the kernel, really. So those GUIDs, and if you look in one of them, you have basically files which give you information, like those read-only files, whether there's an activation capable, whether you need CPU rendezvous and stuff. And then you have something where you just activate that. And this is how it looks like. So if you go into one, you see in this case that's the activation it's activation capable, which is obvious, but it's activation pending means, oh, there's an updated image available, and you can at any time now really do the activation. And this one requires CPU rendezvous. And then for convenience, I added a list. It's kind of a list of known GUIDs in the kernel, and that is and that associates names with it, just for convenience for people to see, who don't memorize that 6C07 is, of course, RMM. You have that. And if you want to do that, actually, then you see, you just echo 1 into the activate sysfs file, and then it magically does all the stuff for you and returns, and then you run with the updated firmware. So version 2 of the patches are on the list. There was not so much feedback as I was hoping for. At least there's one user already, one partner who's interested, and I convinced them to reply publicly on a list. So there was some feedback and some even external contributions, which I included into the V2. There's some interesting locking corner cases, especially around the CPU rendezvous and sysfs, and then suddenly firmwares might disappear during the update process, so some interesting stuff. And also important, this is just implementing some kind of low-level interface for userland. I don't expect eventually people to use that direct interface, but it's more some userland application, which, I'm happy to delegate the work to other people to write that, to use that low-level kernel interface to make it more manageable. Now some quickly for RMM live update. So this TFRMM is it's the ARM confidential compute blind hypervisor thing. So it's basically kind of a hypervisor proxy, if you can think. So KVM's doing all the policy work, and then says the RMM, please switch the vCPU, please map those memory for their guests. And this is a kind of very shim thing. And it's actually a nice target for this live update, because it does not carry much state, because all the state is handled by KVM, right? So in the non-secure kernel side. And there's actually all the blocks like the vCPU state and all the guest memory is kind of, the kernel cannot see it because it's just the idea of confidential thing, but it's still under control of the kernel. The kernel kind of logically owns the memory and just gives it to the RMM. So all the state is in this memory that's handled by the kernel, and if there's a new RMM, it would automatically on the next call get the same state, so you don't need to preserve that state above the update. There is, however, some state in there, and yeah, we see in a second how we deal with that. Also, the RMM is mostly like somewhat opti-like, where you relay just stuff and it does it. So the kernel calls into RMM and then it does something and it returns, so it doesn't run on its own. So that's why there's a little state there. So this is how the RMM looked like before. So there's a huge carve out, and you see it's very lofty, it's quite a space. And the actual preservable state is in this BSS thing. The rest is really small. And if you do a naive now AB slot thing, then you see that you have the problem that you have now the state that you need to preserve is actually living in the other slot, right? So you cannot, it's hard to preserve. You don't want to really copy this over. And the solution we came up with was basically moving this out and using something like a heap. It's very simple, it's not a proper heap. So you allocate that memory and all the state that needs to be preserved is actually put in that heap area. And now you can basically just switch the pointers to, you just need to provide a pointer to the thing, and that automatically reuses the state that needs to be preserved. And the rest is still left to the RMM, that's private data structures. Yeah, so conclusion is rebootless firmware updates are possible. So as I said, it's merged in trusted firmware. It's also merged in TFRMM, and we have, under some demo conditions, can show you how, while you're running confidential guess, the hypervisor is really updating. And then you continue running with that new RMM hypervisor. But it requires platform, system, and firmware-specific enablement. So there's all hooks are there in trusted firmware, but you need to put in your own code there and use that. As I said, TFA codes merged, TFRMMs there, Linux code is under discussion, and userland story is to be done, and any takers are welcome on this. And that's about it. Thank you very much.
Thank you. So this, we have, I forgot to mention, this afternoon we'll have again a mixture of short lightning talks and normal length talks, so keep the pace interesting for us. Okay.
All right. The colors are slightly weird on the screen. I'm not sure if it's a laptop issue. Let's see if it works on the next slides. Anyway, we're not going to talk about displays today. It's about cameras, so I'm not responsible for fixing that. We have 40 minutes, so a bit less, because hopefully I'll be able to take a few questions to talk about the past, present, and future of camera support in Linux. So let's get started with that. For those who don't know me, my name is Laurent Pinchard. I'm the CEO of IDs on Board. I've worked on video for Linux for longer than I can remember, and I've always found cameras to be fun to work on. Bit of a weird kind of masochism, if you ask me, but I'm sure that all of you have your special area of interest like that. So my company, we said that we make cameras work. We help our customers integrate cameras, develop our camera drivers, ISP support, work on a Leap Camera project. We'll talk about all those technologies later. The things we're going to discuss today, so this is the title of the talk, the past, the present, and the future. Going to try to refine a bit that, because that's a very long amount of time. I want to tell people that if there's anything unclear, you can interrupt me, ask questions during the talk. There's hopefully going to be time to ask questions at the end. So if you have a longer question, let's wait until the end. But if there's anything that needs to be clarified immediately, that may be useful to the audience. And if you're a bit shy, I have brought some licorice, so you get a free one if you ask a question, either in the middle of the talk, at the end, or if you're really shy, you can come in and talk to me and get free candies, even if you don't have questions. Right, so let's go to the introduction, and I mentioned we're going to start with the past, so let's going to define what we're not going to talk about today. While preparing this talk, I realized that the first long-distance image transmission ever occurring in the world was in 1906, which So the image was transmitted over more than 1,000 kilometers in France, if I remember correctly, which is very surprising. But the first, and in 1921, the system got improved to have the first digital image transmission. We're not going to talk about that. Obviously, those things didn't run Linux, so nobody's interested, right? If you're interested in that, actually, lots of interesting history and Wikipedia pages to spend time on. Still out of scope, more recent, the first CCD image sensor was invented in the 1960s, at the very end of the 1960s. The first portable digital camera, yes, it has a tape, was in 1975. Not entirely sure if it's really the first, and it's the first one I could find, but you know how people tend to invent the same thing around the same time, so maybe someone raced by about a few months or a year. And then the invention of the pin photodiode, the NMOS, paved the way for CMOS, and the first CMOS sensor, so the latter day in 1992. We get closer to Linux now. But still, that's also lots of interesting history, good material for a trivia game, but not really for this talk. Getting closer, that was my first webcam. It's fairly bulky, obviously, a big camcorder, analog output, a TV capture card. That's how I got interested in cameras on Linux, because I was running that on Windows, and when I was 19 or 20, wanted to transition to Linux. There was no driver, and well, you know the story. You scratch your own itch, and you make that happen. The vFile2 API was merged in a very old version of the kernel, pre-Git, so that's really ancient history. So anything predating video for Linux really is out of scope. Getting there, closer, webcam history would also be interesting. USB webcams are a bit boring in a way because they just work, except when they don't. There are few people in this room, I think, whose job is to make sure that everybody else believes that USB cameras just work. Does anyone know what the picture on the top left is? Coffee pot, yeah. So that's the first webcam that was pointed at a coffee pot in university in the US, and it has been live on the internet for a really long time. It got decommissioned, unfortunately, at some point. But yeah, again, lots of interesting readouts. And we're getting to the modern days. So that's something I'm particularly interested in and plays a big part in my personal history. That was the Nokia N900, the first phone that really ran Linux as a commercial product, even if it quickly got discontinued. The first ISP driver that we merged in the kernel as part of that development in 2639. So those are great days. That's when we developed the Media Controller API, the vFile2 subdev API. We upstream all that. And that's where I'm going to define the starting point of history. So before 2011, there was no history. We're going to still restrict the scope on the hardware side. I said webcam, even obviously webcams, there are recent webcams today, but that's not really of interest to us today. So we'll focus on systems that combine a raw camera sensor with an image signal processor, an ISP, and where both are exposed to Linux. So if everything is hidden by a firmware that exposes the combination as a webcam, and that's typically what you have in a USB webcam, you have a raw sensor and an ISP inside, but you don't have access to those pieces. That's out of scope for today. We're going to focus on systems where Linux has to control all of that. It's not limited to embedded systems or IoT or edge devices or however they will be called in a few years. The vocabulary changes all the time. Many laptops, tablets, phones also integrate this kind of architecture. Laptops used to have USB webcams internally, and you buy a new laptop and you think you have the same, but actually in lots of cases you have a raw camera sensor and an ISP that Linux has to control. I mentioned the Media Controller API, so the kind of device we're interested in may be exposed in a media graph as something like that. So you have on your left-hand side your camera sensor on the top, connected over, in virtually all cases, MIPI CSI2 to a CSI2 receiver. You have an ISP connected to that. You may have a memory-to-memory ISP on the right-hand side, or memory, that's what we call an offline ISP, an inline ISP on the left-hand side. That's connected directly to the stream coming from your camera sensor. So we're going to focus on those kind of devices. So let's see what's happened in the whole history of camera support in Linux. As I said, before 2011, that's ancient history. We're starting with the MC So Media Controller API, V4L2 SubDev API. And I've divided the talk in 4 different periods: the Middle Ages, the modern period, the present, and the future. Present is now, 2026. This talk is going to be obsolete in a few months. So, the past. Called that Middle Ages to start with, but actually I decided to nickname that period the Great Depression. So starting in 2011, just after, or roughly at the same time as we upstreamed the Media Controller and the V4L2 SubDev API, there was an episode called the Burning Platform Memo, which I assume some of you have heard of. That was an internal memo at Nokia that got leaked and compared the company as a burning oil platform. And that's when the company decided to ditch Linux development, ditch Linux phones, and adopt Windows phones. That was definitely the technology of the future and would make them very successful. We had plans at Nokia when we upstreamed those APIs, when we upstreamed the first kernel driver for the OMAP3 ISP, we had plans to work on a user space component as well. And because the project got canceled, that plan never materialized. So for 7 years, nothing happened. And I found that quite depressing. When I say nothing happened, we still had APIs. So Media Controller, V4L2 SubDev, they're well documented in the kernel. They were used by drivers, a single ISP driver, but other drivers for camera pipelines that don't include an ISP. I did there for reference also a link to a guide that explains how to use those APIs. So anything from 2011 to 2018 is well described in there. Patches are welcome to update that to the more recent period. And in 2018 came a new hope. That's when, so the Great Depression lasted until what I call the Great Tokyo Meeting, because it happened in Tokyo, and it was a great meeting. And that's when we decided that we had to do something in user space, really. So we gathered people, gathered companies who were willing to participate and fund a project, and we started a project called LibCamera. A few years ago, I would have asked who has heard about LibCamera, and a few people who have raised their hand. Nowadays, if I ask, everybody has heard about LibCamera, right? Yes? Who hasn't? Wow, okay. Oh, yeah, Daniel, you don't know anything about Linux anyway, right? So by that time, Linux had gained a second ISP driver in the kernel, in staging, though, and as most staging drivers of staging quality. So LibCamera, not going to describe that in details because you all know about it. It's the mesa of the camera world. Open source camera stack and framework and user space to control the ISP, the raw camera sensor, exposing APIs to applications, integrating with Pipewire, GStreamer, Android, and much more in the future, of course. So if that was the end of the Great Depression, what comes after is something that I have nicknamed the Streams Age. That's a period of 5 years. Actually 4.5 because it doesn't align right on the 1st of January. And that's when we started a big effort, kernel space and user space, to develop more ISP drivers, integrate that in LibCamera, and realize that there were actually lots of shortcomings in Linux. Things that were not well supported, needs of more recent hardware, or use cases we hadn't really considered. And that led to the development of what we've named the Streams API. So that was merged in 2023. What's the Streams API? So 4 years of development, 4.5, 16 versions, which according to the people who have worked on that is really a lot, and nobody wants to have to post patches until V16, but that's far from the record on the Linux media mailing list of V28 for patch series. Kudos to those people who really don't give up. So 3 developers took turn driving that project and championing that. And what it does is that it adds a few new concepts in a media controller, in the V4L2 SubDevs. So on the right-hand side, you have a diagram of what we call a subdev. I'm going to go in a bit more details because if you've heard of LibCamera and V4L2 as concepts, you may not know about the details of the APIs. So the media controller models the hardware as a graph of connected entities. They have pads and there are links between the pads. It's just a graph, basically. And before the advent of streams, a link between two pads would carry one stream of data implicitly. But we do have hardware. We have hardware buses such as CSI2 where you can actually multiplex those streams and over a single physical link. Or we have devices such as crossbar switches in this case where any input can be connected to any output and configure the routing of the data internally is important. We don't have really good support for that. So we added a concept quoting the documentation. A stream is a stream of content. It took a lot of time to write that. We actually couldn't find a better definition. So talking about pixel data, metadata, a unit of data type that's carried over a link. And it flows through the media pipeline from source, typically for cameras and image sensor, of course, towards the final sync, which can be a receiver, demultiplexer, or other devices. So the streams extend the pad model. Now pads can carry multiple streams, and where you were able with a V4 to set the API to configure formats, crop rectangles, properties on pads. Now you can configure them on pads for a specific stream. So it's really expanding that. And there are new IOCTLs to be able to control the routing of the data internally inside subdevs. So really API extensions that help a lot to support new classes of devices. And as I said, CSI2 is a major use case for that because it carries multiple streams identified by virtual channels, data types. So that's very important to properly support CSI2 when you have multiple streams. So what happens during the stream age? We also have more ISPs. It's great. So during that period of 4.5 years, OMA3 ISP, Atom ISP2, those two were merged before. So we had five more ISPs being merged during those 4.5 years. That's nice, except it's not that nice because if you look at the details, the first one developed by Nokia, I mentioned we never developed any user space for that, any open source user space, so it can be used as a kernel driver, but it's very hard to use. The Atom ISP2 that in staging, of staging quality, it actually got dropped from the kernel at some point because a bit rutting got restored. There's been efforts to try to clean that up, but it's really side projects. It's very old hardware, so it's more hobbyist kind of project, even though they're driven by experienced kernel developers. The RPU3 AMGUs on ISP from Intel, found on some Intel SoCs in laptops. It's in staging, still of better quality, but still in staging. The RKISP1 driver, which has been extended to support the IMX18 Plus from NXP, is better. That's a good one. And I'm not saying that because I'm working on it. Then you have driver macro chip ISP, a simple one, but it has all the control algorithms for the ASP in kernel space instead of user space, so it's less versatile. I'm not entirely sure why we merged it that way. Probably nobody noticed. The Star5 CAMSS ISP driver that was merged and then dropped because Star5 said, no, we're not going to release anything in user space for the time being. But they swore that whenever the product and the SoC would be of no commercial interest to them, that they would start upstreaming user space. We had some doubts. So dropped from the kernel, it's 7.1. There's an all-winner ISP driver that also doesn't have user space support in Leap Camera. So yes, more drivers, but still the situation is not great. So that ends the past. And we're going to move to the present, which is now. If it were just now, I would have really little to talk about. So I'm going to define the present arbitrarily from the end of the stream age. So in the end, in 2023 to now, so spanning about 3 years. So what happened there? Well, first of all, we're actively working on making sure that the present becomes a past, so we're going to have a new present next year. I'm going to submit a new talk about that, right? And we have a steady stream of image sensors being merged. I mean, ISPs are great and the more complex parts, but if you don't have image sensors, they use less. And I listed here everything has been merged during this period that I call the present. So a few drivers from Galaxy Core, from Sony, it's a big name obviously, OmniVision, more drivers from OmniVision, a couple from Samsung, Toshiba, 2 drivers for ST sensors. Most of those are what we call mode-based drivers, so they're hard-coded in the driver side, one or a small list of configurations with sizes and configuration of the sensor that you can then pick from in user space. But if you have use case that requires something a bit different that a sensor can provide, but it's not hard-coded in a driver, you can't use that. So those are things that we don't like much. in video for Linux, but the reality is that often those drivers are written by third parties that don't have access to documentation or no full documentation, no support from the vendor. So some of the things are reverse engineered, or they find some list of registers and values completely undocumented in obscure Git trees in a back alleys somewhere at 2 a.m. I don't want to get there, but yeah, we have drivers upstream from that. So that's why we've accepted drivers. The majority of sensor drivers in video for Linux are like that. Not all of them, though. Now, more interesting is that over the past few years, we've been actively engaging with sensor vendors. Instead of criticizing them for saying, you know, it's really bad that they don't upstream drivers, it's really bad that they don't provide documentation and support, say, how about we ask them? And so we went and talked to them, and actually quite a few said they were interested in talking with us. Not necessarily doing the work directly. You know, if you go to a company and say, you know, if you give me some documentation, I'm going to do your work for free. Are you interested? Surprisingly, quite a few of them say yes. So that's great. It means it can work. Not all of them agree, though. When I say that most of the drivers are developed and upstream by third-party contributors, not the sensor vendors, there's a notable exception from ST, the two drivers I mentioned before. So I want to publicly state that they've been doing a good job and what every vendor should do. So I think that calls for a round of applause for ST, right? Thank you. I don't know if Benjamin is in the room, but that's for you. But the other ones, we've been engaging with vendors who have been willing to provide documentation and support. One major vendor, who unfortunately can't name at the moment, we're actually working with them so that they can write drivers themselves, training their team internally to do the right thing. I'll try not to suspend the screen, that would be nice. Okay. And when they started writing code and hard coding modes in the driver, I said, you know, it would be nice if you didn't do that. And they say, oh, okay, we'll do it better. So I was a bit surprising that they were really willing and to do the right thing. As usual, when you engage with vendors behind the scene, you can go public immediately. It seems from an external point of view that nothing's happening. Oops. But results will come. So I think we'll start seeing results from that effort within this year, and it's going to increase after that. Of course, we need to increase and expand that outreach effort. We've had more trouble with vendors in Asian countries. Lots of image sensor vendors in Taiwan, of course, in China. And due to the language barrier and differences in the market, it's been more difficult for us to engage with them. So we'll have to figure out strategies and maybe find other people who would be better placed to do that. One of the questions is, if image sensor vendors are working on driver and they're willing to do it right and not hard-code modes in the driver, should we keep accepting mode-based drivers upstream, at least for sensors from those vendors? Or tell the third parties, well, if the vendor can do it and can provide you documentation, then do it right? I think we can maybe push for things to improve in the kernel. On the ISP side, quite a bit of community effort as well. Accelerating support for more ISPs with what I'm going to call good drivers. And when I say good drivers, it doesn't mean they're bug-free, but it means that they're using the most recent kernel APIs, the thing that we standardize, the thing that we're telling people that's how you should do it. We've merged the ARM Mali C55 ISP driver in 619. That's found in multiple SoC, but we've been working with the Renesas RZV2H board to test that. 2 more drives have been posted, one for an ISP coming from a company called Dreamchip. That's, assume most of you haven't heard of, but they just license IP core, so they're not really well known as such, but their customers are known, so that's also for Renesas SoC in an automotive platform. We've been working on a driver called RK-ISP2 for newer Rockchip SoCs. Spent lots of time, lots of marketing effort to find a good name, you know, for RK-ISP1, what could be the new driver. And so all those developments received direct support from the vendors. I'm also very happy to see that. That's a good trend. It doesn't mean that they've done the work themselves, but they've provided either technical support or documentation, sometimes working more closely with their teams, and we need more of that. Lib camera integration and support is also in scope for those projects when we work on kernel drivers for that and for those ISPs. So that means it gives you a full camera stack supporting those SoCs. There's also vendor efforts when it comes to the ISP. I'm going to mention Raspberry Pi. They've been the first vendor to actually open an ISP driver. Not sure why the screen keeps flickering. Is it on my side? So they've been the first vendor to develop drivers, not upstream them directly. The initial upstreaming effort for some code was, well, you know how upstreaming works. It can be a bit daunting for vendors who get pushed back. So at some point we started helping them and said, okay, keep doing the development and we'll help with the upstreaming. So we've upstreamed, the Raspberry Pi has developed, and we have upstream drivers for the Pi 5 ISP, which is an entirely different one compared to previous generation. AM Logic has also developed a driver for the ISP found in the C3 SoC. We've helped them, given them reviews, given them their directions, but they've done the work themselves. NXP is working on an ISP driver for the MX95 on a brand new ISP again. They're doing all the development internally. We've given them a few directions and talked with them a little bit, but they didn't even need hand-holding. So there's really, really lots of improvement in the process there, and we see much more contribution directly from the vendors, which makes me really happy. I think we're going in the right direction. And again, Lib camera support is included in all that. In a move that surprised lots of people, even Qualcomm published an ISP driver. It's fairly bare bone at the moment in the version that's on the list, but features will expand. So it's called the CAMSS ISP OPE. And I always thought that Qualcomm would be among the last to accept to open their camera stack, but I was very happy to be proven wrong by that. So I think it's fair to say that the situation is improving. We see more interest from vendors. It's growing significantly. We're not there yet. Definitely not there yet. Much more work is needed, much more outreach, assisting them, going to other vendors. There are vendors that have completely given up on. NVIDIA is one of them because they make so much money these days that they don't listen to anyone, and fine. And then you have lots of SoC vendors, actually, that have no upstream presence in Linux, like zero. So it's a bit hard to upstream an ISP driver if the SoC doesn't exist. In some cases, it's because they don't care about upstream. We've talked with people who said, well, it's not that we don't care about upstream, it's that we actively do not want to be upstream. Because we're selling this chip to only 4 customers in huge volumes. We support them directly. If we were to be upstream, then it means we would lose control over what we're doing, and it would be more difficult for us. Whether they're right or wrong, it's probably out of scope for today, but that was quite interesting to hear. So all of those I gave up on for the moment, but we'll have lots still of vendors and ISP that we can support. We also have a software ISP implementation in LibCamera, so that's an interesting one. It's a way to support platforms that don't have an ISP, but also platforms as a stopgap measure that have an ISP and where the vendors didn't want to open anything and lets people use the ISP with an open driver. That used to include Qualcomm, well, it still does on some SoCs, but hoping that's going to improve. We also do that for Intel laptops that use an IPU6, IPU7 ISP. And we found that it actually gives an incentive for the vendors to open things up, because the software implementation is of lower quality, it's slower, it's going to consume more battery. And so people will start saying, oh, you know, when I buy an Intel laptop with an integrated camera, that's quality of the image is really bad. Intel gives bad images. So that's, in a way, pushing the vendors. It also gives a base set of features, so it makes the discussion sometimes a bit easier internally for some vendors. They say, oh, well, they go to the IP owner internally and say, you don't want to exploit information about this thing, but there's an open software implementation that does the same, so maybe that's not a trade secret anymore. And we're focusing there to accelerate the algorithms with a GPU. We have a GPU-based implementation too, which is quite a bit faster, uses less power. Made me sad in a way, because the argument of saying an Intel laptop consumes so much battery and use the webcam is actually not completely true anymore. So it gives me less leverage to push the vendors to open the ISPs. But joke aside, that's still an interesting project with lots of use cases. So we need more. And by that I mean that, as before when I said that we identify shortcomings in the kernel APIs and we develop the Streams API, well, all of this also identified more shortcomings in kernel APIs. I've listed 5 of them there. Those are all APIs are under development. Patches have been posted. I'm going to go very briefly through them. We have the generic line-based metadata. Sensors can output metadata in addition to image data. And to be able to configure that and route the data correctly through the media graph, we need the ability to, we need API extensions really to be able to control that, define the formats for that metadata. So there is a patch series on the list, V12, 86 patches. It seems that every new version grows. It's a bit scary. That patch series also includes a concept called internal pads. Mentioned we have pads in entities, and you have IOCTLs to control, to configure them. But it turns out that it's not enough to model the internals of a camera sensor. So introducing internal pads that model the internal source of the data, of image data, that's a pixel array of embedded data, and then the routing inside. And so that gives us, you're using the existing vFold2 API and the IOCTLs with new internal pads, we can do much more. And we're also documenting what we call the raw sensor model. It may come as a surprise to people, but Video for Linux actually does not standardize anything for camera sensors, in the sense that we have an API, we have lots of IOCTLs that are documented, but what features of the camera sensor are controlled by what IOCTL is not really standardized. So we have lots of image sensor drivers in the kernel that expose the same feature through different IOCTLs, or different features through the same IOCTLs. You can imagine that writing generic user space code is very difficult with that. So with this effort, we're standardizing a model for raw camera sensors and explaining in detail how the different features have to be exposed to user space, which will make our life much, much easier in the camera. Multi-context support. The idea is that when you have a memory-to-memory ISP, in many systems, it's designed with a higher bandwidth that would be needed for one camera, so you can connect multiple cameras to the system and time multiplex your ISP. We do have support for that with the vFold2 MEM-to-MEM framework, but it's limited to devices that have a single video device. ISPs are more complex, they have multiple video devices, and so the MEM-to-MEM framework couldn't support that. So we developed, my colleague Jacopo developed a new extension called Multi-Context in Video for Linux. Patches are on the list, and we need that to support memory-to-memory ISPs properly. So we need more, we need faster. The project on that has been slow. And we really need to have more champions, people who will take ownership of areas and say, okay, I'm going to push that. It's not so much that there's lots of resistance and people don't want to merge patches, but those features are complex, and when you receive a large patch series for something that is complex and you need to spend time on understanding, then you don't always prioritize that when you're busy. So reviews come slowly. We need people who will push reviews, ping them, sit with them to explain things, maybe have a video call, explain things in detail to facilitate a patch review and really get that merged. I want to finish with a few words on the present. The present is market ready. We have products on the market that run mainline kernel with mainline drivers for ISPs, image sensors that run libcamera, and that actually work, at least as far as I'm aware. So there's a large user base and community. There's also a number of companies who can provide support. So it means at a time where cameras in Linux and ISPs in Linux were considered to be more of a hobbyist project is over. Last word here, wanted to mention that we have quite a bit of tooling as well in the libcamera project. This is the Camshark application that my colleague Stefan Klug will talk about in lightning talk just after mine. So I will not spoil that, but it's not just the framework, it's also the tooling around that, the debugging tools, the tuning tools. Right, we're getting to the last section of the talk, the future. The future starts now. It's also quite arbitrary. So 2026, could even say that the future starts actually today. It's mostly a divination exercise, obviously. Okay, skip to the next, okay, there we go. Because what I'm gonna tell you now is not things that I have researched and I can tell you with great confidence, but it ranges from being correct by sheer luck to being, well, completely incorrect. So use all this information at your own risk. What we could do is meet again next year to see where I was right and lucky and where I was wrong. So we have a bunch of new MIPI standards. In this context, new means they've been there for less than 5 years, let's say. I'm not even sure, actually, 3C is probably older than that. But most MIPI CSI2 camera systems support in Linux is based on D-PHY. It's one of the PHYs for the transport of on CSI2. But we have C-PHY that's seeing a rapid increase in adoption as well, where more SoCs using that. I3C can also be used with a much lower bandwidth, of course, to transmit pictures. We don't have any support for that in Linux. A-PHY is also quite interesting. That's not just a PHY, but a full serialization technology. It's relatively new, and we have also zero support for that in Linux, mostly because there are very few vendors shipping products with that, and the vendors that do are not very cooperative at the moment. So my prediction is that we'll see a rapid increase in C-PHY support, but when it comes to I3C or A-PHY for imaging, that's gonna be slower. We have an issue that my colleague Karen called the curse connectors. There is no standard, no industry standard when it comes to camera connectors. So you have people making development boards or whatever hardware, you have people making camera modules, they have to be connected, and nobody has thought, you know, it would be a good idea to standardize that so you could connect the camera module to a board. No, there's lots of different connectors. Fortunately, there's a de facto standard that's kind of emerging, which is the 22-pin connector from Raspberry Pi. You have more and more board vendors adopting that. So I think we'll see that trend continuing, but it's definitely not going to be universal because 22-pin carrying 4 lanes of CSI2 data means that you have 2 pins left as GPIOs, and if you want to implement support for flash and trigger and other features, that's not enough. It's very important in industrial use cases, so we see lots of boards for industrial use cases that have 24, 32 pins camera connectors, and they really can't go to 22. Be very careful about a pinout. If you design a board, we've seen that in a while, that has a compatible pinout, a compatible connector with Raspberry Pi, they have mirrored the pin numbers in the schematic compared to the manufacturer of the connector. So if you take the connector from the and the data sheet from the manufacturer and keep the same pinout, then you're going to have a mirrored connector compared to Raspberry Pi camera modules. Not nice. Curse connectors, but different concept, device tree. So because those camera modules are often pluggable in a board, not soldered on the board, it means that we usually handle them with DT overlays. But instead of having one overlay per camera module, we have one overlay per combination of camera module and baseboard. And that's lots and lots and lots of overlays. We actually don't really bother upstreaming them in most cases because of that. Hopefully that's going to be solved at some point. There's a great proposal called the connector abstraction for device tree by Luca from Bootlin. I really want to see that merge and being adopted everywhere because it's going to simplify our lives so much. So we'll see. Progress is a bit slow on that as far as I understand because it's a very complex feature, but I think everybody wants it, so I'm really hopeful. Serializers, we're going to see that more often as well. CSI2 is limited in range. You have serialization, deserialization, and technologies that can extend the range. That comes from the automotive market to start with, but it's not limited to that anymore. It can also be a good way to increase the number of cameras in a system, in a larger system. So technologies for that include GMSL, FPD-Link, MIPI A-PHY, as I mentioned, and the other ones are the proprietary technologies. GMSL and FPD-Link have support upstream, at least for some of the version and some of the chips. Fault tolerance will become important as well, as you have more cameras. Imagine lots of cameras in the car. At the moment, when the system boots and we probe everything, user space doesn't get to see anything until all cameras have probed. And if you have 12 cameras and someone has knocked your side mirror, then you're not going to get any camera available, which is absolutely awful. So we'll have to fix that at some point. So we need more kernel frameworks, more APIs there again. So I mentioned 5 things that are on the list and that we have trouble getting merged, and there's even more that we need. My prediction is that we'll require a proper job scheduler in Video for Linux, because time multiplexing an ISP, you have to schedule jobs there. Round robin is great until it's not good anymore, so we'll probably need some kind of scheduler there. Maybe we'll look at what DRM does for the DRM scheduler. We need to refactor the way vFault controls are handled and where they're stored, because I think they will need to be bundled with a vFault to set the state and the formats and the crop rectangle there to make things a bit more atomic, and that's going to pave the way to an atomic API towards user space, a bit like on the KMS side. And also the media graph will expand to cover multiple devices, so it's going to have a larger scope. So we really need more champions in Video for Linux. Last words, one on lib camera. Let's hope this comes back. We're doing major refactoring there to make things more modular, pipeline handlers and RPA modules, to facilitate integration of new platforms. And my prediction is that we'll start seeing heterogeneous pipelines as well, that will have a hardware ISP, but it will use also the GPU for pre or post processing, and maybe DSPs and NPUs as well. So there's going to be lots of fun, lots of things to explore. More collaboration with vendors. It's increasing, and I think will keep increasing. I do think that the outreach effort will expand, and we've heard vendors telling us, we're really wondering why we haven't started this 5 years ago. Well, we wonder as well. Emerging areas such as MIPI A-PHY, as I mentioned, that's going to require more time to establish communication with vendors there, because, as I said, at the moment, the few of them, they're very secretive, so that's going to take lots of time. And we'll end with a conclusion. That's how it's supposed to go. I think we have a much brighter future ahead of us than during the Great Depression. Having lots of drivers in mainline helps integrators. I don't think I have to convince any of you that mainline is great. It does help the vendors too, the ISP vendors, the image sensor vendors. I think that CRA will also be really good for us, because it will push vendor to go more upstream. Generic and modular frameworks, not just on the kernel, but in lib camera side, that's very, very useful. Have tremendous value, so having APIs that are more generic on the kernel side, I can expose things generically in user space, makes life much easier, even if it's a bit more work to design things. Mainline camera stacks, as I said, have shipped on device, and they will keep doing that, and it makes me really happy. And I'll finish by saying that the future of cameras on Linux is obviously in user space lib camera. So if you're interested in seeing a demo of all that, at the break, go up, and we'll be very happy to talk to you and show what it's about. Thank you very much.
Stefan, you can come up and set up, and we'll take a few questions when we get the next speaker set up. Questions?
Thanks, Kovaran, for this nice history topic. One obvious question. You mentioned that you need more people to maintain review code and so on, so on. So obvious question here is how any AI reviewers helpful or not, or how you consider them in your case?
Review means lots of different things, between telling people that they've messed up the indentation to telling them that the design is completely wrong. I do think that for those complex frameworks, it's more a design issue to start with. It's also about convincing car maintainers that we're doing it right. So it's about explaining things correctly to them. And so I don't think that AI would help much there. Maybe it could accelerate low-hanging fruits of review, but for the frameworks at least, not so much. Now when it comes to areas where you have, for instance, image sensors, if you have lots of drivers being upstreamed, there's lots of comments that are repeated over and over, and you could say that AI could possibly help, but my preferred approach for that would actually be to have a row sensor helper in the kernel. Image sensors today, for row sensors, they have to duplicate lots of code. There's lots of boilerplate code. And it takes time to review that. So instead of throwing AI at reviewing that, let's remove that and make sure that all the boilerplate goes in helpers and that driver is simpler to implement.
Thank you. And one quick question, and unfortunately you have no slides anymore. You listed those first drivers, ISP drivers, when we were upstreamed. What is the lib camera support for them? So MAP3, ISP, ATOM-SP, IPU3, and so on.
Right. So for the drivers I listed in the beginning, the ones where I said in the slide they don't have upstream support, they don't have user space support, it means there's nothing in lib camera. I'm not working on lib camera support for ATOM-SP2, for instance. I know that Hans de Hoede, who's cleaning up the driver, is focusing on the driver at the moment. Maybe lib camera will come later. Intel IPU3, we have support for that. So all the ones where I didn't say there's no user space support, we have lib camera support. And then the ones in the later slides, that have been merged later or that are on the list at the moment. Lib camera support is either merged or is developed in parallel and will be upstreamed as well. So we're not going to accept an ISP driver in the kernel if someone says, I want to upstream the driver, but I will never work on lib camera.
Thanks.
Have we written yet that we're not going to accept those drivers without the user space?
I don't know if it's written, but I think that we have an agreement, looking at Hans, in Video for Linux, that if you want to have an ISP driver, you need to have an open user space. The same way that if you want to merge a GPU driver in the kernel, you have to have an open user space.
Thank you for the talk. You mentioned NPUs, so what's the relationship between, for example, NPU supporting GStreamer that also supports lib camera or a lib camera pipeline, let's say?
Right, so the way I see NPUs used with lib camera, there are three options. One is actually something we could support today. So we have today in the Raspberry Pi support in lib camera a neural network to do auto-white balance. It's a tiny one, it's a really tiny model, and so it runs on the CPU, but it could potentially be accelerated by an NPU. So we could see NPUs being used inside lib camera to help with the ISP control algorithms or to help with face detection, for instance, and you would be able to focus on faces. So that's one usage. The second one would be NPU usage also inside lib camera to do image processing. Denoising is a very common case, but possibly even more than that. So that's about really processing the pixels and not just helping with the ISP control. The third use is outside of lib camera, and that's about taking images produced by lib camera, feeding them to an NPU to implement a use case that's user-specific. You may want to I mentioned a device, no, I don't think it was in this talk, but we've worked with a company making devices for that does face recognition for access control, and so they use NPUs, but that's outside of lib camera. So we help them getting images with the quality that the NPU needs, but the integration of the NPU was at a higher level.
Thank you.
All right. If there's no more question, anyone interested can come forward and get some candies. Thank you very much. Okay, apparently we have some technical issues, so if there are more questions or if anyone wants to discuss anything related to cameras. Sorry? Oh, that's the DC-10. It's a PCI card. It was a really great one because the capture bridge and the JPEG encoder on that PCI card had public data sheets. something that used to be the norm, but not anymore. And so I spent quite a few evenings with a multimeter trying to trace the traces in the PCB. Again, you didn't have 12 or 16 layers PCB back then, so it was much easier. And trying to reverse engineer things, seeing how they were connected, and yeah, that's great fun.
So not a question, a request. If you're interested by the connector work done by Luca, if you can join the upstream discussion, that would be very helpful, because we are struggling making progress with that with the DTC maintainers. So we're a bit struggling with exactly the same problems that you're facing, getting stuff accepted.
Such a surprise, right?
Exactly. So if anyone is interested, please join so that we can... Yeah. I don't know if it's increased the pressure, but get more momentum around this.
Can you maybe send me and Karen a mail with the latest version of the patch? Because I was looking it up and I wasn't sure if I was looking at the right one.
The step we're at right now is on the DTC mailing list. Because
on DTC mailing list?
Yep.
Okay. Let's try to have a look.
It's mostly Hervé who's doing that work. 77 patches. So.
Yeah, big series. Huh? Something's happening over there.
We actually have Frank here, who's also working on the DT connector stuff. He should be in the audience here. So it would be good if we can talk about this.
So let's get the people in the same room with lots of beers and... Usually when that happens, I tell Stefan, you should stop using a MacBook. But I'm not going to do that publicly on record, obviously. I don't want to. Oh, oops, sorry. Huh? Yeah, the noise on the side, I've had that as well.
And what is the progress on non-visual sensors? And to what extent can it be reused, for instance, for thermal cameras or other sensor types?
That's a good question. So non-visual sensors, well, thermal cameras, time-of-flight sensors, I assume as well, event-based sensors. I don't have a clear answer to that. When it comes to thermal sensors, for instance, I think Leap Camera could still be a good fit. Depends a bit what the sensor would output. But the more we depart from a visual image sensor, the more the API will be a mismatch. And so at some point we have to draw the line, otherwise we'll have something really hybrid Frankenstein API that's not going to be great. So we could discuss the detail for thermal sensors. I haven't looked at them personally. But things like event-based sensors, for instance, I don't see that support in Leap Camera at the moment.
Do you hear me, by the way? No. Okay, that's better. So welcome to my talk, Inspect Your Camera with Camshark. It's actually my talk in this round, so thanks for having me. I'm quite excited to doing that. 2 to 3 words about me. I'm Stefan Klug. I joined Ideas on Board like 2 years ago. Before that, I've been working in the machine vision industry for for exactly 10 years, so I've been doing MIPI cameras for quite a while. And before that, I was doing, well, software, as most of us did for quite a few years. I'm mostly into graphics. That's what I like, so cameras is just an extension of that. What we do today, the talk is all about Camshark. Maybe a quick question. Who knows Camshark in that room? At least a few of them. Yeah, that's cool. Thank you. We'll go down to why Camshark, roughly the features. It will be really from the top level. A bit of the internals, what we thought or what I thought when we started the development. A bit of setup and UI, so if you want to try it out, to what you have to do there. The plugin system, because it's quite nice if you want to hack on it. And then a bit of outlook, what I plan there. or what I would like to do and to implement. So first things first, why Camshark? You see it there. So my first task at Ideas on Board was basically make that thing look nice. I should work on algorithms. I should work on a nicer looking camera. And the terminal, well, it's great. It's a pity I can't see the slides here. That's why I have to look up there all the time. Sorry for that. So yeah, the terminal is great, but not really if you want to look at images. So if you want to do algorithm development, you can use the classic CAM application that comes with LibCamera. It's a console application. If there's a display connected to the device, yes, you see the image. But then you often want to do closer inspection on the image. So you want to do look at individual pixels. So you start to store that image or to save it to disk. If you're on NFS mounted devices, that's all fine. That works quite well. But still, you have to open the image or, in the worst case, transfer it over SD cards. So that's not really practical, and you don't have live access to all the controls in LibCamera. So it's a bit of pain working on that. Yeah, I wrote that there. We want to correlate image or metadata with the image data, and we want to measure things. And we also want it to work with devices that don't have a display attached, like customer devices, or the display driver is just not yet working. So first I started as design guidelines, then I realized we never did a design on that thing. We just started writing it thanks to Tomi, who basically did the first script, which had the first bits and pieces I needed there. So it's more of hacking guidelines. My target was that it's super easy to set up. I target on simplicity first, optimization second. So I didn't strive for fast images. I didn't strive for the perfect code there. I used Python to get running really, really fast. And it should be hackable in first place. As I wrote there, there's no need to squeeze out high frame rates. I wanted to look at the image data and not at the high speeds we could get there. And the other one that was very important for me, I wanted to have minimal resources or minimal requirements on the remote endpoint. It's a big pain if you got an embedded device and then you want to install something there and you're missing libraries, you're missing dependencies, your Python setup misses something, you're not connected to the internet, or you're on build root and need to rebuild everything. So that's a bit of a struggle, and I just wanted it to work. So the only requirements there is you need to have SSH access and you need to have Python with LibCamera bindings on that device. That's all there's needed, that's it. And the last point, I try to move fast on the repository. I try to pull in things. We should get even faster there, but so there might be things that are not working. Just tell me so we can fix them. So quick overview over the features. It is public on that URL. We can capture raw images. That is super important if you want to do tuning. It's a bit hidden. We will see that a bit later in the UI, but it can store DNG images. These contain all the EXIF data that is needed for later tuning, but regularly you just store PNGs, so that's simple features. We got all the information to all the LibCamera properties, to the informations, to the controls, to the metadata, all in one UI. That makes things very easy. We can interactively access all the controls of LibCamera. It's enumerated on the device side. We'll see that later. So that makes working with it quite easy. It already supports most of the pixel formats we have out there. A big shout out to Tomi, my colleague, who made the small utility library PixUtils, which converts all those formats into RGB and vice versa. So that helps a lot there and made developing Camshark quite easy. And then we got a plugin system that also helps a lot. We realize that right now because it adds more flexibility to the project, and maybe users out there might add more and nicer plugins. We already got 3 of them in the default setup. It's a graph view. We'll see that it's a histogram and a small presets plugin. So let's go a little bit deeper. This is the rough overview over how Camshark works. We got the Camshark main application on the left side, on the host side, and on the device side, the right side, that is the server application. I just said that I wanted it to be super easy to set up. So the thing the host application does, it takes the Camshark server packages as a package for the remote device, opens an SSH connection, copies it over to the device, starts the server on a specified port, and that port is forwarded through a SSH tunnel to the host device, so you don't need to set up you don't need more network setup than just SSH. That comes in very handy in our automation lab at Kieran's lab, because he jumps usually through multiple hosts on SSH, and direct connection to an IP would not be available. So routing everything through SSH adds a bit of overhead, but on the other hand, it just makes things super easy. Then there's one concept shown here that is very important to know and to understand. The people who have worked with libcamera know that for libcamera, for every frame, you need to queue in a request. You set all the controls on that request. You queue that into libcamera, and a while later, you get the request back with buffers attached and the metadata for these buffers. That is super cool if you want to do per frame control, but it's not so easy if you want to route that over Ethernet from a slow device onto your host machine. That adds delays, that adds overhead, so that's difficult to handle. So we did that a bit differently. You see on the right side, that is the camera loop that is only running on the device. So on the host side, we even don't know there is libcamera. There's nothing libcamera specific on the host side. As I said before, it should be fast and easy, so there's a lot of dicts in there. There's non-specific classes. It's maybe a bit of shady Python code, but it works quite well. On the right side, the camera loop runs super fast. It runs in real time. That's what we are showing in the demo upstairs. The display is running in real time, while Camshark is stuttering here and there because we don't care about the speed. So controls are only if you enter manual controls. They are sent to the device, and then as soon as the device is ready, metadata is sent back. Controls are sent back. That's not an error. We sent back the controls that were set on the corresponding request to know or to be able to check what was in there. And frames are sent back. They're sent uncompressed, just raw data, so it's slow. And if there's too much data, we just drop them. That's fine. One question, I'm at 10 minutes here. Do we have the full 15 minutes, even though we started too late? Okay, yeah. So how to get started? It should be a one-liner to install it. You got the typical uses there. And usage, that's the one line you need, basically Camshark and then the SSH access. We got some useful parameters, but that's details. I'll jump a bit quicker to finish up earlier. And that's the whole application. So yeah, a lot of controls up there. You got access to all the libcamera controls. You got access to metadata. And down there, you got a graph view with nice graphs with interesting things. And on the right, we have a small histogram. I need to ask again, is it 5 minutes still left? Because then I could go all of them, or should I? Just 1 minute. OK, that's close. OK, let's jump over that. That's boring. That's camera configuration. That is cool. You can enable capture script in the configuration, so you can actually set controls per frame and feed that into Camshark. On the remote side, you can control every frame, and what you get back is a graph view that shows you that. Every X on that graph is when a control was set. The lines on the graph is when the metadata came back to that frame or for that frame, so you can correlate if everything really, really works per frame. We want to add on top of that actual measurement on the device that would even further improve things. So I think now I have really to jump over. Well, that small one is also nice. If you work with capture scripts, you can just dump them in that presets directory, one script or one file to enable that, one file to disable a capture script, and you got a nice button in the UI to just run your specific tests using Camshark. That's a very nice, useful tool. Yeah, plugins, I think we have to skip that. We have a plugin API that is super cool. We got a one threading issue that exactly one function runs in the plugin thread, the rest in the main thread. You just need to know that if you ever want to write a plugin. And that's in the uploaded slides. If you want to write a plugin, that is a super small template. You can get started like in just dumping these few lines into your folder or into your directory, in your home directory, and you got a running plugin in Camshack, so it's really hackable. I think that's it. Oh, yeah, the Outlook. Thank you. That was short a little bit.
All right, Kurt's up next. Where's Kurt? Kurt's up next. Oh, there. Sorry. Yeah, no worries.
Okay. So, hello and welcome. So I want to talk about something completely different than cameras, which is real-time networking with PreemptRT or with mainline Linux. And so my name is Kurt. I'm one of the developers working for Linotronics. And basically, I want to get started by doing a small recap what real-time actually is, and then go into the networking part. And in the end, I want to talk about how can we validate everything which I just showed you. So what is real-time? So in a real-time system, we have to guarantee results within a certain time span. So a result does not only depend on the correctness, but it also depends on the time constraint when the result is actually available. And this means a result shouldn't be too early, and most importantly, it shouldn't be too late. So it's all about keeping our deadlines. That's the important part. Because a missed deadline, even if it's just a single missed deadline, can be fatal, and it can lead to a catastrophe, so to say. And there's a common misconception. So real time does not mean real fast. Real time just means as fast as specified. So it's really about keeping our deadlines and making sure that we have bounded latency. So it's not necessarily about speed. And Linux is a general purpose operating system. However, Linux can be turned into a hard real-time operating system simply by enabling one specific configuration option, which is called PreemptRT. And that is basically something that Linotronics has been developing over the last 20 years and got it into the mainline kernel in version 6.12, at least for the most prominent embedded architectures, which is x86, RISC-V, and ARM64. And recently, we also enabled this support for ARM32, so that has been merged into 7.1, and I guess that will be also backported into 6.18 and 6.12. So here's an example. So why do we need PreemptRT? Just a quick question. So who of you knows what cyclic test is? So I'd say that's maybe like half of the room. So for the others, cyclic test is a really small testing utility which is designed to test the responsiveness of a Linux real-time system. So basically what cyclic test is doing, it is setting up periodic tasks, and these tasks are just running, for example, like once per millisecond. And what these tasks are doing, they're just setting up a timer. So they're using Clock Nanosleep to set up a timer, and then they just measure the difference between when the timer should have fired and when the operating system was actually able to get the cyclic task onto the CPU. So basically, cyclic test is like constantly measuring the latency between the timer interrupt and then migrating the cyclic test task onto the CPU. So basically, it gives us like an idea how responsive the real-time system actually is. And the thing is, I did here a cyclic test measurement over a couple of hours for standard x86 embedded board, basically. Took 6.18, so LTS kernel, and basically ran the test twice. Once with preempt.RT enabled and once with preempt.RT disabled. So simply swapping that one configuration option. And as I said, so we care about the worst case times. And with RT, our worst case response time is 62 microseconds, which is, for that hardware platform, is okay. And simply by disabling preempt.RT, running the same test all over again for a couple of hours, putting the system under stress, we get a worst case response time of 1.2 milliseconds. And this is the problem, right? Because our cyclic test task is running with a cycle time of 1 millisecond, but if we have a worst case response time of 1.2 milliseconds, basically means we missed our deadline here. And this is why we need preempt.RT, and yeah, this is why we need it in the kernel. So let's talk about the networking part. And the thing is, real-time systems nowadays are interconnected, and they're usually interconnected with Ethernet. Yeah, because Ethernet is everywhere, it is cheap, it scales really nicely in terms of speed, and there are lots of use cases for real-time networking. So for example, there's the industrial automation where you have like protocols like Profinet or OPCOA, EtherCAT, so field buses, and these protocols, they all have real-time requirements on the networking part. But we have also Ethernet in cars, we have that in airplanes, and we have that basically everywhere. There are also interesting use cases in the audio land. So for example, the audio-video bridging, because if you think of like big concert halls, you will have like lots of speakers and microphones and amplifiers, and there's a good likelihood that all of these devices are interconnected with Ethernet basically, and that the audio and the video frames are all transmitted over Ethernet. And every Ethernet frame in that environment has a deadline associated to it, yeah? Because if an audio frame comes too late, you can hear that immediately, right? So, and the audio world has also interesting requirements. So for example, they need redundancy, they have really strict cycle time, so kind of interesting. Yeah, and this is why we need real-time or deterministic networking, and this is basically what the talk is about. So it's about real-time networking with RT. So how does it work? So in Linux, we have a network stack, basically, and the network stack is quite powerful. So we have lots of protocols in there, lots of features, and the applications basically just run as user space applications. They get access to the network stack using sockets, so they can basically enqueue and receive packets based on that. But the question is, what are the challenges that we have for the real-time networking part? And first of all, we have the latency problem. So for every Ethernet frame, we need to make sure that the time an Ethernet packet travels from the network card up to the application, and from the application down to a network card, we have to make sure that this time is actually short and also deterministic, right? So that we don't have any outliers in there. And then a lot of these real-time Ethernet protocols have like the requirements to send and receive a lot of small packets. So lots of these protocols have like the requirement to send even like 64-byte packets, which is quite or different from the traffic that we have in the internet, for example. And then we have to make sure, okay, when we send the packets, how can we make sure that the jitter on the wire is really deterministic, right? So there are applications which needs to send an Ethernet frame like once per millisecond. So how can we make sure that this is really precise? And the last point is also very important. So for example, if you think of edge gateways where you not only run your field bus or audio application, but also Docker, Podman, Kubernetes, web UIs, databases, and so on. Yeah, we have to make sure that these applications also work really well and don't disturb our real-time traffic. So let's get into it. So how does the receive path work? So what is going to happen if an Ethernet frame enters our hardware, basically the network card over here? And basically at some point the network card will raise a hard interrupt. And then we will jump into Linux kernel executing that hard interrupt service routine. And on preemptor-T, the actual service routine is not executed directly, but on preemptor-T, all the interrupts are threads, right? And this means here the hard interrupt handler will just look up the corresponding threaded interrupt handler and will schedule that onto the CPU. And in the threaded interrupt handler, this is where we actually get back into the network driver. So basically, this is the code which is executed when packet is going to be received. And the interrupt will basically, or the network driver will just schedule the packet processing. So you might have seen that in a network driver, there's like an API schedule, and an API schedule will basically raise a software queue. And this software queue is then responsible for the actual packet processing. And as soon as we leave the threaded interrupt handler, we will check if there's some software queue pending, and we will execute that immediately. So that means as soon as we leave the threaded interrupt handler, the netarc soft interrupt, which was scheduled by the NAPI schedule, will be executed directly in our context here. And this is where the actual packet processing is happening, right? So this is where the SKBs are allocated. This is where the protocol handlers are involved and so on. And in the end, the packets are going to be queued to the socket, and the application gets a notification that everything is ready. And the thing is, that works really nicely, but only 95% of the time. And as I said in the beginning, so real-time is about, we have to make sure that it always works, right? 100% of the time. So what's the issue with that? There are two issues, basically. The first one is called KSoftIQD. So if you boot up your Linux system, you might have seen that there's one daemon per CPU, which is called KSoftIQD. And this daemon takes over the SoftIQ processing under certain circumstances. So for example, if there's too many SoftIQs in the system. And this is problematic because if this daemon takes over our network processing, then basically all guarantees are lost. And this is because the KSoftIQD is per default not a real-time task. And there's a good reason for that. But this is something we have to avoid by all costs, because if we push a SoftIQ, which is supposed to process our real-time packets, into a non-real-time context, basically there are no guarantees anymore. And the second problem is the whole SoftIQ serialization. So on preemptor-T, the soft interrupt context is preemptible, right? However, soft interrupts are used for a lot of things in the Linux kernel. So it's not only used for networking, it's also used for timers, it's used for I/O, for example, it's used for tasklets and so on. So if you look in the kernel for local BH disable, you will see all the regions in the kernel which enforce the SoftIQ context. And this means if someone is, for example, like copying data from SD card, and our networking interrupt comes along, and the networking wants to do the packet processing, then we can preempt him on preemptor-T, so that is good. That means we're being scheduled. However, the whole SoftIQ processing is serialized with a single lock per CPU. And this means if the other guy is copying data from SD card and has the lock already, we have to wait. And if he's like running for 20 milliseconds, then we have to wait 20 milliseconds until the other guy is basically done. And this is a huge problem, actually, for the real-time networking part, because also the block and the networking, they don't have to do anything together, but they're serialized over a single lock, right? So what can we do? There are two solutions to that problem. The first one is CPU isolation. So what we can do is like take a set of CPUs, isolate them from the rest of the system. So for example, using isolate CPUs or C groups, and then basically pin the network load on there, but at the same time run all the other tasks in the system on the other CPUs. That is something we can do because the SoftIQ and also the serialization is basically done per CPU. The problem with that is if you tell a customer that they have to do CPU isolation, they're usually unhappy because they want to use all the CPUs that they have, right? So what Linotronics did basically is to lift that restriction. So Sebastian, the Preempt maintainer, went actually in and identified all the region which needed actually protection by the bottom half lock, so to say. So what he did is he went through all the code, networking, and all the other stakeholders in SoftIQ, identified the region which actually needed protection, and implemented a much more fine-grained locking approach. And by that, we could simply rip out the bottom half lock completely. And that has been merged in 6.18. So by that, we also don't have the requirement anymore to use CPU isolation, right? Because now the software IQs can preempt each other, but they can also execute in parallel. And this is basically, that had been a headache for a long time, and I'm really happy that this is in the kernel now. Okay, then let's talk about technologies that we can use for the networking. So as I said, we need to make sure that the latency is rather short, so from the network card up to the real-time applications. And what can we do about it? And the kernel has features, for example, like XDP. So this is a feature of the Linux networking stack. And XDP stands for the Express Data Path. And it's basically a high-performance networking path, and it's basically an in-kernel fast path. So with XDP, we can hook into the network driver, and we can inspect a packet as early as it arrives, right? Even before we pass that packet to network stack. And this works by writing BPF programs. So a user can basically write a BPF program, and this BPF program has to take the Ethernet frame and simply decide, okay, what to do with that packet. And this is executed directly at the driver level, so meaning the first point that we actually have the packet, right? And this is really useful because we can inspect the packet. For example, we can drop it immediately if we see it's not for us. But Linux also introduced a new socket type, which is called an AF-XDP socket. And with an AF-XDP socket, we can redirect a packet from the network driver directly to the application without even going to the network stack. Right? So we don't need to do SKB allocation, memory allocation, and so on. We can just redirect the packet up to the application. And this is really nice in order to lower the latency, right? But at the same time, we can also use zero copy with that. So for example, I have customers where we need to process like 200 packets per millisecond. So we need to send it, receive it all over again. Like we have 1 millisecond to do that. And with zero copy, it actually works quite nicely. So we only spend like a couple of microseconds actually in the networking part and have all the other time for doing some real work. And there's actually a third advantage of using XDP, because since XDP is a Linux feature, it can basically coexist with non-real-time applications on the same network interface. And this is because an XDP program can also say, pass that packet to the Linux network stack. And then all the other applications, like the non-real-time applications, they work exactly the same. And with that, we can run our field bus, for example, directly next to our Docker instances, and everything just works. And this is really nicely, and I think much better than using the traditional kernel bypass, which a lot of people are doing. And then there's another thing I would like to talk about, which might be useful for some applications, and that is busy polling. So what I just showed you in the beginning was the IRQ-driven data path, but actually it's also possible with Linux to run the network card in polling mode. And that can be really useful if you have like strict cyclic applications. So for example, like field buses like EtherCAT or Profinet, you need to run your packet processing like once per cycle. And you can simply do that directly from your application. Yeah, so you just have to configure the socket into polling mode. And then if you call like send to or receive from, you will directly end up in the NAPI poll of the NIC driver, which means you can run the whole packet processing from user space. And then you don't have to take care of the interrupt configuration, of the interrupt thread scheduling, and so on. And with that, we were able to achieve like really short cycle times, even below 50 microseconds. Okay, let's talk about the transmit path then. So far we talked about the receive path. On the transmit side, it's a little bit easier because if we want to transmit a packet, we can just call like send to or send message, and the packet will usually just be queued into the network card. However, there are some hardware features which help to improve the situation. So for example, there's like features like TX launch time where the hardware will take care of transmitting the packet at the correct point in time. And there are also some features from the TSN standards, like the time-aware shaper. I don't want to talk about it, but there's a good write-up from Intel at tsn.readthedocs.io. So in case you're interested in how to use that, that's the resource you can go. But let's talk about TX launch time a little bit in detail, because with TX launch time, we can not only specify the payload of the packet, but we can also specify a timestamp when the network card should transmit this packet, right? And this works because those network cards usually also have a clock involved. So they usually have support for the PTP protocol, which is the precision time protocol. It's like NTP, but designed for local area networks, so it's much more precise. And this means the network card itself has also an internal clock. And then you can just queue your packets ahead of time and calculate the TX timestamp, so when should the packet be transmitted on the wire. And if you have like an application like which needs to transmit a packet like once per millisecond, you can pre-calculate all your timestamps and send it down to the hardware. The only thing you have to take care of, you have to make sure that the time base you use is obviously the same time base as the network card. And if you use that, basically you are able to get into the nanosecond precision, right? And then it really doesn't matter when you queue the packets from Linux, because the network card will take care of the rest, basically. You just have to make sure it's in the future. And this works also for embedded network cards. So for example, the STM-MAC in the IMX8, IMX93, and so on, they all have support for this. So let's talk about testing. So how can we test what I just showed you? So basically the real-time testing. And actually there are lots of tools in order to test Linux and networking. However, there are not many tools focusing on the real-time part. And as I said, so on the real-time part, we are mostly interested in deadlines. So we have to make sure that our frames don't miss a deadline, and that's the important part. And basically, I had a customer who, had been using out-of-tree drivers for a very long time, meaning they had been writing their own network drivers because they said, okay, Linux is not capable of using real-time networking, so they have to use their own drivers. But basically, we went ahead and tried to write a tool in order to show them, no, we can actually do that. We have now all the technologies in the kernel, right? So we have XTP and TX launch time and everything, so we can do it. And this is why we wrote a tool which is called the RTC Test Bench. And the RTC Test Bench is basically doing exactly the same thing as cyclic test, but over the network. So basically what it's doing, you need two machines, so you set it up. The first machine is basically generating in a cyclic manner Ethernet frames, sending it over to the second machine. So both machines need to be connected over the network. And the second machine is just mirroring the packets back to the other machine, right? And we do that like constantly, like once per millisecond or whatever cycle time we have configured. And simply by doing that, we can take all kinds of statistics. So for example, we can calculate the round trip times. We can say, okay, how long does it take from here to here and the other way around? How long we can even like take hardware timestamps and see how long it does from the network card to the application and so on. This project is open source now, and I'm also happy that we have sponsors for that. So it's Phoenix Contact and Siemens, which are both product manufacturers, so they're building PLCs, and also Intel. Intel is basically building really good network hardware, right? So how does it work from a software point of view? So usually the test bench is just a normal application, just like cyclic test. And we basically create different traffic classes, for example, like real-time cyclic, but also non-real-time traffic in order to make sure we stress the network. And you can use XTP, right, as I just showed you. But I want to mention that we also do more or less required to run PTP in parallel, so the time synchronization protocol, so that we get both of these machines in sync, because this has the advantage that we can get their schedules aligned, but also to get the timestamping basically working, because we can take timestamps here, and therefore, if we want to correlate them, we need to make sure that both are taken on the same time. Yeah, how does it work? Basically, for test bench, you give it a configuration file that you need to write, and it basically looks like this. So you say the most important parameters are the cycle time, and you say, okay, at one point in your cycle, you want to do the RX packet processing, and at what point you want to do the TX time processing. And then you say, okay, what traffic classes, how many frames, the frame sizes, the VLANs, and whatever, right? And also if you want to use XDP or not, if you want to use busy polling, and so on. Yep, so as I said, so what we are mostly measuring is the round trip times, because simply by measuring the round trip times, we can immediately see if something goes wrong. So for example, if a frame comes too late, we see that immediately, right? Which basically means there's some issue somewhere, might be in the network, might be in the Linux kernel, might be somewhere else. And yeah, basically we also check for other things. And here on the right side, for example, you see some visualization of some Ethernet frames for different problems. And this was basically taken with a device from the Fraunhofer Institute, where you can just feed in an Ethernet stream and then visualize it over an oscilloscope. And we used that, for example, in the first image here, we used that to measure the interpacket gap. So for example, if you send a burst of frames, the interpacket gap is basically specified by the standard. So in gigabit, for example, it's 96 nanoseconds. So that's different between the packets here. And I guarantee you, if you run that on any kind of embedded hardware, you will not get 96 nanoseconds, because there might be a DMA controller involved or whatever. And sometimes you see spikes and things like that. So it's really interesting. And the second thing here is more a TSN feature. So yesterday, I think there was a talk from Butlin, and they said, okay, when we're on the wire, the packets needs to be transmitted from start to finish. And with frame preemption, this is what you see here, which is basically a feature that some Intel network cards, for example, support. You can basically interrupt the transmission of an Ethernet frame in the middle and squeeze in another Ethernet frame. So this is basically an iPerf frame here, the red one, so which is 1500 bytes usually. And here in the middle, we just have a Profinet frame on the wire. And this works because the network card supports it. So let's take a look at an example. So basically here I set up a cycle time of 1 millisecond. Used some older x86 machines, which are typical in a industrial PC, for example, and used Intel i226 network cards. So these are really nice because these are PCI Express network cards, and they have a lot of hardware features like PTP and TX launch time, and the Linux driver has also support for XDP and zero copy and everything. And basically I set up some traffic classes here. So for example, like 200 microseconds sending some real-time data, and then 800 microseconds sending some non-real-time data. And simply by doing this configuration, we can actually pre-calculate our round-trip times. This is because our operating system should be deterministic, right? Because we're using preempt.t. Our application should be deterministic and everything else. And simply by taking this configuration here, like the 1 millisecond cycle and the TX and RX offset, we can actually pre-calculate what our round-trip time should be. So if we go to the first cycle here, it's 1 millisecond. At the end of the cycle, we call TX. We take a timestamp for every packet. We transmit it to the other side, meaning to the second device. The second device is running the exactly same schedule. So basically at RX, they will receive the packet. At TX, they will send it back to us. And then at RX here, we get the packets back, right? And simply by doing that, we can pre-calculate our round-trip time, which here is 1.5 milliseconds. Yeah, and then we can let it run on the hardware and see what we get. So here I graphed the round-trip times basically for some of the traffic classes. And as you can see, so usually I graph the minimum, the maximum, and the average. The average is actually exactly at 1.5 milliseconds. That's what we expect. And the jitter is around plus minus 100 microseconds here, which is okay for that kind of hardware we're running on, right? And the important thing is if something goes wrong, like if we miss a frame or it comes too late or whatever, we will see that immediately simply by plotting the round trip time. Yeah, then you would immediately see like a spike. And the idea is basically the same thing as for the cyclic test. So you let it run for hours, you put your systems under stress, and then you make sure that everything works the way you expected. Yeah, and with that, I'm coming to an end. So Linux with PreemptIT, you can use that for the real-time and also for the real-time networking part. Works really nicely. We have all the features in the kernel that we need. So we have XDP, for example. We can use zero copy. We can use busy polling and so on. And depending on the use case, you can get even down to 50 microseconds. That is not enough for some use cases, but for a lot of use cases, that's definitely fine. And yeah, depending on the kernel version, you have to be aware of the software IQ processing, right? So this means, yeah, the newer the kernel is, the better. And if you want to know how to use XDP and how to set up all the network interfaces, the QDisks and everything else, yeah, you can take a look at the RTC test bench because it's all there. And with that, I'm basically at the end.
Hello. Can you go to slide 10, please? Yeah, regarding this bottom half log.
Yes.
So it's not less reliable that the usual RT preempt option, because it's not the same to know, okay, all of these interrupts can happen, and just the top half is going to be executed. Then you have the software queue program for any of those top halves. So it's not less reliable, meaning that depending on the traffic or the load of the system, that latency can increase or decrease significantly, more than with top halves. And regarding that protection with the CPU log, is that bound? Is the thing that happens inside the log is bound, or it depends on the load as well?
I'm not sure if I got the question right.
Sorry?
I'm not sure if I got your question.
Well, just asking about what is the variability. So, I mean, you need to validate this with hardware because it depends on the end of the load and the number of devices during interrupts. So there's not a magical thing. It depends on the system and depends also on the load, right?
Yes, it totally depends on the load, right? But the thing is, I mean, the software queues are used for a lot of stuff in the kernel, right?
Yeah.
So we'll always have like software queues, right? And usually if you run like a real-time system, you will have lots of other tasks running on your system. So it's quite likely that you run into this problem. But of course, it depends on the hardware and on the
but what
stuff
I
that
mean
we
is with the RTPM, you have a high priority task that can be with a higher priority than any IRQ, right? Top half. But in this case, you are involving software queues that are can be more heavy for processing, and at the end, this range. Okay.
Yeah, exactly.
Okay, thank you.
I'm just interested for when you're timing transmit, is that a hardware feature of the Ethernet controller?
For what?
When you're timing the transmit, you're setting the time for the transmit, the absolute time, right?
Wait. This one?
Yeah.
Yeah.
Is that a feature of the Ethernet network card? Or
Yes.
Is it? Okay.
Yes. It's a feature of the network card, and mostly the TSN network cards have that. So if you don't have that feature, I mean, you can emulate it in software, but it's not as precise, right?
what kind of setup do you support? Do you support asymmetrical setup for your test bench? Do you support asymmetrical, so one trusted Intel NIC and another one that you trust less? Is that supported? And where is the graphical user interface running? Can you run it on two boards that don't have any video output and check it out on another PC? Is that possible as well?
Yeah. So first of all, the two machines can be completely different, right? So you just have to make sure that they can cope with the load, right?
Yeah.
And basically you just need network access in order to get it running. So that means you can send the statistics to some other hosts or whatever, but you don't need a display or anything like that. So it's just a terminal application, right?
And so loopbacks works as well, right? Loopbacks on a single board. Is that possible?
It should be. I never tried it.
Okay.
Should be.
One last question. Do you have any example presets for workloads that you share with the software, or do you expect everyone to write its own script?
So basically we have quite a lot of pre-configured setups, and mostly for the Intel i210, i226, and for the STMIC, which are the most popular ones, so to say, but none for TI platforms, for example. So nothing on the CPSW or on the PRUs. But yeah, there's quite a lot of your examples.
Hello, on your left. Do you still have to use ISOL CPU if you run the busy loop, the busy waiting loop on one core? Do you use ISOL CPU for that?
For the busy polling, no, you don't have to.
But should you? Because like you are maybe going to starve the CPU doing this?
Yeah, so usually for the cyclic applications, they only run once per millisecond, and then they're only in the busy polling loop 10, 15 microseconds, right? And the rest of the time the CPU can do other stuff. So because we are not running, hogging the CPU, that is not what we do, right? We do the packet processing only once per cycle. And this means you can run that perfectly without ISOL CPUs, without no heads full, and so on.
Okay, thanks.
Just short remark, I think you missed to mention that there's threaded NAPIs by now, which is highly recommended in order to split your traffic, the real-time traffic from the non-real-time traffic in this bottom half handling. So that is something we definitely want to do, and you don't have to deal with the locking as well in this case.
Yeah. Yeah, I mean, so in the test bench, there are lots of examples using threaded NAPI for that reason, to avoid the whole NetSoftIQ thingy. But the problem is, so I had a discussion with Sebastian, actually, and he said, okay, we don't need it anymore because he mostly get rid all of the invocations where we actually call into KSoftIQD.
But it still needs that you have the traffic split for
Yes.
the core, the real network traffic.
Yeah,
That's
sure.
the point. Then we need back in the ISO CPU scenario,
Yeah.
that the non-real-time traffic is on a different core.
Yeah.
I have one question then too. There are still a lot of people using EtherCAT with the out-of-tree, older kernel, custom driver setup. Is there any reason to keep doing that anymore with all the features you mentioned, or what are the reasons that people are still using that out-of-tree stuff versus actually using mainline?
Yeah, that was actually that was one of the points I was trying to get across, is that we don't need all of these out-of-tree solutions anymore, especially with the bottom half rework that Sebastian did, right? And actually, there's a pull request for test bench which adds EtherCAT support, and then you can test it for yourself, right? But we did some measurements against some proprietary EtherCAT stacks from the same company, and they're still in certain scenarios faster. That is because for XTP, even in the busy polling mode, we still have to issue syscalls, right? And this takes some time, and the out-of-tree drivers have optimized some of that away, so they're able to get down to lower cycle times than with XTP.
Okay, thank you.
I can start now? Yeah, that's. So, hello everyone. I'm Mamta. I work at Leica Geosystems as an embedded engineer. So, we just had a very nice talk around real-time networking with Preempt RT. So now I would like to share a debugging story around it, where it was just a routine kernel upgrade, and it helped to find out issues with the reset naming, some timing issues, and some hidden assumptions that we had. So before starting the story, something about the platform where I observed it. So I was using this SoC from Intel. It's Altera Aria 10. It's Cortex A9 dual-core ARM 32-bit. And we have Ethernet MAC from Synopsys, Designware 1000. And we have a Mistral Phi, and there were different kernel versions involved in this story. But before that, you might be wondering why real-time kernel? So we do have real-time applications, and we do need deterministic timing in application for devices like laser scanning used for surveying and construction. So how it started, around 2 years back, or end of 2024, I was bumping up kernel from 6.1 to 6.6 with RT patches. I was moving to 6.6, and initially, I booted this kernel. Everything seemed fine. All the peripherals were working out of the box. But then the thing which I needed the most, SSH, to connect to this board remotely, it was very slow and unstable. Like, I cannot just say slow and unstable. I wanted to quantify it or to measure it, how slow. So I started pinging from the board. And when I booted with the Preempt RT kernel, like full preemption enabled, I was seeing 50% packet loss. And the latency was okay. But surprisingly, when I disabled preemption and booted non-RT kernel, everything was fine. I could reach to the board, SSH was fine. And then I started to dig deeper. So initially, it was working with the earlier kernel, but still I wanted to check some skew values in the DTS for the Phi. And for the Mac, I started testing with the ETH tool just to see if there are any CRC errors, or checking the registers with Phi tool, and also keeping in mind the behavior of RT and non-RT kernel, and some traces and logs, but to do something much more obvious, to find out what really changed between the two kernel. I was looking for something more in driver side, but I stumbled upon this one commit, because this was one of the changes between the two versions. And it says it was for 64-bit, but it was touching DTS for Aria 10 as well. And slightly more about this commit message. So they wanted to replace OCP reset line with the AHP, because AHP is the standard one, and it's used by the core driver also. And before I go much deeper around these resets, I'll take a step back and let's see how it looks on the hardware side. So on Aria 10, with this Ethernet MAC, we have two reset domains. So there is Emacs0 and Emacs0 OCP. So basically, these two resets are managed by Reset Manager and set in this pair 0 mode register. And they take care of two different parts of this entire core. So Emacs0 reset, which is quite important, and it takes care of TXRX FIFO inside the core. And we have OCP reset, which takes care of the ECC RAM, which is not that important, but also about bus interface, which is the connection from your eMAC controller to the SOC. And to make this Ethernet connection work correctly, we also need to set PHY mode before starting any of the transactions, and that is set by System Manager by setting the PHY mode bit. So as per the Intel TRM, it's advised that please make sure both these resets are released before any of the transactions begin. Then when I try to map it to Linux kernel and the driver and the DTS, so we have STM-MAC ETH reset, which is used by the core driver, and it takes care about the Emacs 0 module itself and its STM-MAC reset. Then there are two other definitions as well, AHP reset and the OCP reset. And the core driver, it uses the AHP reset, and OCP reset is actually needed by the glue driver. And this takes care of the OCP and AHP side so that your back can communicate with the SOC and later be in a stable condition to do DMA or any other transactions. And this OCP reset and eMAC reset, they both are needed to create a clear reset boundary. So coming back to the patch. So the idea was that we use AHP reset, make it uniform across all the SOC FPGA, all the SOCs from Intel, like Arria 10, and Agilex as well. It looked like, okay, just a change of reset name, and we already know the path which is taken by these resets. It looked quite normal, but since this was the only change made between the two kernels, so I decided let's revert it and check how it works. So when I switched to OCP reset, there was no packet loss. Everything worked perfectly, especially for RT kernel. SSH was fast, stable, right, and everything was stable right from the boot time, and I was happy. But so far from the story, understanding all the reset sequences and reverting this patch, I try to restructure this initialization path and understand what is really happening. So initially we have a bootloader which keeps the eMAC in reset. The clocks are enabled, and then we release the PHY out of reset. But when the kernel boots, we use the glue driver to probe. And then the PHY mode has to be set. And when this change was there with AHB and OCP reset and AHB replacing the OCP reset, there is like, if I call for the function reset control assert in setting the PHY mode, it was no op, no operations, and null. And when it's OCP reset, there was some proper timing for setting up the PHY mode correctly. And the Ethernet path was going well, and it has a timing window when I had this OCP reset. But with AHB and with RT kernel, it was a little tricky. So knowing like we need a correct reset name, and it is still being used inside the glue driver, and the glue driver from for SOC FPGA needs the correct reset name, I decided to send the patch upstream. And it was accepted, and someone also mentioned they had the similar issue. But still something was missing, actually, because in my story, I started with RT kernel and then non-RT kernel. And non-RT kernel was somehow getting away with this. And my first hypothesis was maybe non-RT kernel provides enough slack to allow Mac to settle better, and then we have a stable Ethernet connection. Cut to 2026, so beginning of this year, there were a few more patches from the maintainer, And the idea was to support both the reset lines because this STMAC OCP and AHP, on the software side, they do represent the same software reset. And following the discussion in the thread, there was a suggestion that it's better to switch to AHP reset, but step by step. And still, when I was reading this thread, I still had 2 more questions. So is it really the reset names that affect the setting of the phi mode, or it's the sequence actually that when this phi mode is being set? So to do that, to understand that well, I tried to do some more experiments around it and to understand what is happening with the sequencing. So I booted with the kernel, which has AHP only reset and nothing changed in the driver. And on the system where I didn't had a very good Ethernet connection, just after booting, I did bind and unbind of the driver, and SSH works fine. Second, I tried to keep EMAC in reset inside the U-boot by writing to this pair 0 mode register. In this case also, it was fair enough. And then the case where we still have AHP defined in DTS, but there is OCP reset inside the driver, and just added a small delay. This was also fine. So it kind of indicated that maybe it's just a timing and the sequence issue, but you also need to take care of the correct reset names in the driver itself. So not just the one line of change, that changing from OCP to AHP, but we can go further with AHP only reset, but the idea is to call this reset inside the set phi mode as well, inside the glue driver. And also clean up the fallback while probing it so that it's compatible with the older DTS if it's around, and also make sure it's deasserted. So what's known so far, this fallback mechanism, it's a suggestion, but it's still not in upstream, and it's still under discussion. So what is known so far and what really works? So if I remove this patch that I want to use OCP reset, and if I want to use this board with full preemption, the SSH is usually slow, and I observed it till 6.18, which was released in April with RT patches. And the idea behind AHP only is also a good direction, and I think it's a possible direction so that it will unify all the reset names around it. So this was a short debugging story, and this is a takeaway for everyone if you want to work with PreemptRT or you have this same EMAC controller or SOC, that sometimes PreemptRT can help you really to find out issues in your code. And also it can be used like a good stress tester if you are really aiming for a real-time application. So a reset name which looked very cosmetic, like it won't change anything, but it was really changing the ownership of the reset around it. And non-RT kernel usually lands in a safe window. Sometimes it allows the Mac a time to settle down, but RT kernel, being the deterministic in nature, it can expose this timing issue. And this is a little hard to do, but if a hardware has a reset boundary and needs a settling time, we need some explicit solution around it. So here are the links related to this thread, and yeah, I'm open for suggestions and questions if you have around it.
I think we have time for one question before the break, if there's any question. If not, we'll take a break until 4:15, so enjoy a little coffee. We'll come back for one more talk, one more lightning talk, and then our closing game. Check, check. Okay, welcome back. We're going to get started with our last couple talks. And let's jump right into it. I'll pass it off to Tomio.
I hope you find this interesting. Well, it's a bit of a status update and to show what has happened and what is going to happen, and a bit how it's structured because it's quite a diverse area. So I will give a very, very short introduction of why we have these MPU drivers, and then describe a bit how the stack looks today, what are we able to do now, just a bit about how to use it, and as well what is being worked on by me or other people. So about what we are talking about, we have these neural networks. You have some input data, and there will be operations on that data and some intermediate tensors as well, and it ends up with some output tensors, which will have data that was computed in that way and that we are going to use in some way. These operations is mostly convolutions, which end up being on the hardware being performed as matrix multiplications and some additions there. And what is important is that it can be a lot of multiplications and additions, so we want to run this very fast and efficiently. So we don't use too much power, we don't spend too much time, etc. So this is one example of a neural network, so you can see those hidden layers. These are these operations, and because of how the convolutions work, you can see how we are going to multiply several elements in one layer with several elements in the other, so it kind of explodes. If we were to do this with a GPU or a CPU, it will just take a long time, it will take a lot of energy. So we have some accelerators which have a totally different architecture, so we don't have to fetch instructions, fetch data into registers, etc. So that's the kind of accelerator that we will be working with. An example of one of them, this is from NVIDIA, which was open sourced by NVIDIA. It's a bit old, but illustrates what these accelerators do. And you can see the convolution core that makes those multiplications and additions in a specific order, in a specific way. You have other compute units beneath that. It's not really important what they do, but they also do computes. But you can see how all the rest is basically about moving data around in the right order, so we can feed these compute units because they are very, very fast compared with the speed at which memory works in our systems today. So otherwise it will be starved and it will take everything much longer. How is the software architecture structured? This is an example of a classical vendor stack. Of course, well, it's very abstract and simplified. It's much messier, of course. At the top, you have your application, and this will interact with some frameworks. TensorFlow Lite, for example, is one which is being actually used today, even if it's a bit outdated in terms of features. You have PyTorch, which on the edge you would use through Executorch, also from Meta. And something you find very often is that vendors write their own converter, which can use as their input models in one of these other frameworks, and they are not going to execute it via that framework for that model, but it converts it to an internal format, and then they have some other library which will execute that. That's because they realize that there are a lot of frameworks, they are changing often. It's hard for them because they are not upstreaming that code, right? So they have to maintain all of that. And for the customers, it's very cumbersome to have to deal with all these frameworks that there exist, but with all those changes for each vendor, because very often, even if TensorFlow Lite or PyTorch, Executorch are open source models which try to be good upstreams, the vendors will be hacking them, which anyway they are having to stabilize in a single version, so they will make changes to it, and it's much harder to update, so they stay in very old versions, like with the kernel or many other components. These frameworks have, most of it is hardware independent, and then there's some delegates or backends to make it easier for vendors to provide something that will accelerate on their own hardware. And these talk to a kernel driver, normally not directly. They will have some libraries to share code there because they also realize that it's very expensive for them to keep this in a shippable way and then updating it as well, right? So then afterwards you have this kernel driver, which normally doesn't have a stable API like mainline kernel has. So integrators have to match kernel driver versions with those libraries or delegates backends. And of course, those drivers out of those kernel drivers will be tied to a specific kernel version. So that also brings some challenges, as we know, and remember when we didn't have open source GPU drivers, right? And then, of course, that runs on the particular accelerator. So as I already mentioned, some of the challenges that the vendors have to give something to their customers in this kind of ecosystem, because of the frameworks being branched, those frameworks already had some dependencies on other components in the distro with some specific versions, which brings other libraries, etc., which can be a bit of a hell. And as I mentioned, with the kernel happens something similar that will have some dependency on a specific version of the kernel, would depend on internal APIs, which change among time. So it can be quite a challenge. It was illustrated yesterday on that talk that we had from this colleague from Toradex, how he had so much problems dealing with how to use the NPU on his system. So I don't think it's normal. It's normal today because we have to accept it. People just are used to that. But I think we could use NPUs in the same way that today we are using GPUs or USB devices, etc. It's a bit of an artificial problem. And well, that was an example of somebody trying to do something on a specific stack, but companies want to be able to choose the right hardware for their products. And that means that for the product lines, they can have several different vendors for their SoCs, for example. So it can end up something like that, right? You don't really have a single stack, which might be hard to work with. You end up having many of them. And well, this is a bit of an extreme case because you don't have, normally you won't have so many vendors for your product lines. But there are some projects which have to deal with this or will like to give support for so much hardware. They just find it impossible because of this problem, right? And that would be projects like, for example, Debian, Yocto. They are supposed to give support to all this hardware, but it's totally impossible that they are going to package all these forks of all the frameworks, all the kernel versions, and well, so this is bad, right? Now, how is mainline today? Even if some of this is in a review on the mailing list, one of these drivers, you have your application up there. I also added GStreamer because it's also being used to run inference on top of these frameworks that we have beneath. So for applications, it's easier. So the fact that we have now stable APIs and we have them in distros makes possible for us to share code at the application level with libraries such as GStreamer. I will be mentioning a bit later what can be done with GStreamer nowadays regarding inference. But again, as in the previous case, we will be using some standard API with some framework, kind of a standard, of course, as a standard as today can be, which can be TensorFlow Lite, PyTorch Executorch. Another example is Onyx Runtime. We would be using still, we are using still this same API split so that we can have a hardware-specific part, which is in the case of TensorFlow Lite, we have a delegate. Executorch has a backend, it's basically the same thing, and Onyx has this runtime execution provider. So these three boxes I just mentioned, these are, well, there's one which is already in Mesa, which is TensorFlow Lite, a delegate, and I have a branch, a merge request already with Executorch backend, and the Onyx runtime hasn't been started yet, but I will get to that at some point, I expect. This is in Mesa, and this is still hardware in the pendant. And that's because we are using this Gallium interface, which abstracts differences among hardware drivers, which are just below. We have FedNaviv for Vivante. We have the Rocket driver for the Rockchip MPUs. We have EthosU for the ARM EthosU. And we have Thames, which is not merged yet. It's work in progress that will give us access to the TI C7X DSP, which has an NPU accelerator inside as well. Then we get to the kernel, and we have the corresponding kernel driver for them. It's the normal split between user space and kernel space, like we have for GPUs. We have that as well for a codecs. LibCamera does something similar for cameras and ISPs. And you have the corresponding hardware at the bottom here. This allows us to scale much better like we are used to, like we would have expected, but unfortunately, with the vendor drivers, this is not happening today. GStreamer, what it does, so there's a series of new elements that they are being called collectively GStreamer Analytics. And they do some inference which is accelerated, can be accelerated by these drivers, and it's extensible. But you have already several models that you can use along with code to support those use cases for detecting objects in a given image, for image segmentation, figuring out which pixels correspond to those objects that are found. Pose estimation, there's several others already implemented. And you can run this inference because it's very hard for a single company to settle on a single framework. So Onyx, TensorFlow Lite, PyTorch executors, these are already there. So it matches what we have in Mesa or what we are planning to have in Mesa. So this would give us a complete solution just with mainline components. The idea is that you have this inference element, which just takes the outputs of a previous element. Those will be the input tensors that I mentioned before, can be camera frames, decoded video frames from a video codec. We'll see how it's important that we are able to interpret correctly with the other hardware on the system. And then this will have some output tensors that we can also use as the inputs for other elements. We cannot display that directly, send across the network. We can encode those frames with a hardware codec. This is an example that does something similar. For those not familiar with GStreamer, you just launch that pipeline. First element is video for Linux source. So you just say, where are you going to start getting frames? You have another element which will automatically figure out from video for Linux what are the parameters, and we'll also look at the next element, what it needs as its input, so it can scale, can convert to a different format. And you have this is the new element, Onyx inference, one of them. You just pass which model you want to use. It already knows that this is a segmentation with object detection and what kind of requirements has on its inputs and what kind of output it does, which goes to Tensor, the code bin, which knows about that, knows that that model is giving us this data and these output tensors, and I don't know what to do with that, especially because it knows that the next element is the segmentation overlay. So it's going to put an overlay on top of the image, and it's going to show you which areas are what, and we can just display it with a regular element existing one. And you can get something like that. We just did the other day. So thank you, Daniel, for this. It's a good example, I think, of what we will be able to do once we have more elements in mainland. These are things that weren't possible before because every vendor as well had their own GStreamer elements or something equivalent with their own dependency health. So I'm going to give you now a bit of a quick overview of the different elements on our stack for those that are not as familiar with it and how they fit together in this kind of vision. TensorFlow Lite is changing names. Each of the big vendors have their own framework. It's, I guess, a way of trying to get a hold of some power on the future. It's a framework which is more oriented towards the edge. That's why we care about that, because this is the kind of hardware I'm focused on. And well, it's coming from a change, and we already mentioned that external delegate. It just gets loaded at runtime, so we can have it properly packaged as well in distros. We are not forking TensorFlow Lite, so we can accelerate on our hardware. And it's expected that we'll be able to run LLMs with some changes that are going on inside TensorFlow Lite, or LiteRT that they call it now. And there will be also important compilation change in which you can compile a model in some other machine, and then you will be deploying that in a different machine. That's quite important, and was a very strong limitation in TensorFlow Lite, because very often you can do quite computatively, quite expensive compilation processes that it's not really appropriate to do in a very small device. So it's better if we can do that in a powerful machine, and then that machine that is going to do the inference can be quite small, and people are trying to do this kind of work on smaller and smaller machines. PyTorch Executorch, similarly, it's a machine learning framework from Meta. Executorch is the latest iteration in their attempt of making PyTorch usable in the edge, in smaller devices. It's looking quite good though this time, so maybe it will stick. And I've been working on a backend for it, which again uses Gallium, so I can use all those hardware-specific drivers that I already have in Mesa. And fortunately, it's more ready than TensorFlow Lite for transformer-based models, which are all these LLMs or some other vision models. They are also much better for text-to-speech, for example. I'll be talking a bit more about this later. So we have this Gallium API, which abstracts differences in the hardware among hardware drivers, so we can have some hardware-independent code on top of that. It's similar to other APIs that are in the kernel. There's no stability warranties. We just change it as we need, and the uses will be all these front ends, Teflon for TensorFlow Lite, Torch for Executorch, and in the future we'll have more, and maybe one day we'll have a Vulkan kind of delegate. We'll see how that works inside Khronos. So what we have currently, we have these callbacks that framework backend can call without knowing still how this model will be executed in that specific hardware. So you basically figure out what the hardware can actually accelerate, and then you pass that can be accelerated to be compiled, and we can serialize to a blob to disk, and then we can load it and invoke it, that file on that blob on the hardware actually, read the output, etc. So it's quite simple. What is not here, these are only the callbacks. The rest of the ML part for Gallium is the model graph of these operations and relationships between them, which are the input tensor or output tensors. It's just a series of structs that just puts that into a format which is not framework specific and is not hardware specific either. Naviv is the first driver for an NPU that we had in a mainline. It was existing and being used for GPUs that Vivante made. Vivante now belongs to Very Silicon, and because they reused the facilities in the hardware to execute commands from the hardware, from the kernel, and ultimately from user space, then we can just use that kernel driver, which basically does that, just pass those commands and synchronize the execution and shared memory. I was able to use it without almost any changes to the kernel, and then I just had to add to user space support for all these new ways of giving commands to the new hardware, which accelerates the machine learning operations. There's also one programmable core, which we don't have support right now because the compiler in Mesa for Enaviv is not mature yet, but there's work going on that, specifically from Igalia, so I hope that they get it done at some point soon. And we can move to the next one. It's called Rocket, and this for the NPUs that you can find in Rockchip SoCs, the recent ones in the latest years. This one has only fixed function units for the convolutions and some manipulation of tensors. There's no programmable core in it. If there's any operation that you need to execute on the tensors and the hardware doesn't support that explicitly, then you run it on the CPU or GPU. That's normally how it's done. It was quite easy to get the driver written because when I started reverse engineering it, I found that it was quite similar to how NVIDIA documented the NVDLA accelerator that they open sourced. So that helped me a lot to move fast on it. And it's pretty performant, not very complete because I haven't had time to work more on that, but the command stream I generated matches that of the proprietary driver, which means that performance is also the same. And so it was a neat project. Hopefully people will be using it more and we will see it grow support for more models and operations and variants of the hardware. On the SoC that I just started working on, it's the Rockchip 3588. There's 3 cores in it, so it was a good use case to test load balancing among these cores. I'm just using DRM GPU scheduler like GPUs do. It's working well in this case, even if a bit complex. Each core has an IMMU, so I can use it to make sure that that clients are isolated and cannot access memory from the other clients. And something, I mean, there are no kernel addresses in the UAPI that we have in mainland, which is not the case for the kernel driver that the Rockchip has, right? So you can just fake an address and cause a page fault inside the kernel, or you can even get information from inside or get some privilege escalation by that. So, well, that's quite important, I think, that we are putting this, trying to use this functionality on the edge, and we are opening a huge security holes. And I don't know if people realize or not, but well, it's a bit sad. We can do that right in mainland, of course. The next driver is EthosU. That's hardware from ARM. They already had open source stack, but it was completely out of tree. So ARM was interested in changing that because of the reasons that we already know, and they just got onto it, and I have been helping them as well. It has only fixed function units. There's no programmable core, which makes it much simpler. Documentation was pretty good. The out of tree stack was also pretty good as well and complete. And the kernel driver wasn't my task. That was done by Rob Herring. So I just focused on user space. And lately, Rob just has been sending patches for adding operations and every models and so on. So hopefully we will see this happen to the other drivers. That is really not that difficult, especially if you have docs. And because of that, quickly I got so much support that we can run several models, which currently we cannot with the other drivers because nobody tried to. But it shouldn't be that bad, especially for those we have documentation for. And the last one, which is still work in progress. It's a driver for a different kind of hardware. It's a DSP. And has extra hardware for accelerating tensor operations, including convolutions with matrix multiplications, the accumulation that I mentioned earlier. And And that's basically because of being a DSP, will have a firmware which is different from the previous ones, but there isn't anything that prevents us running our own firmware, so it was pretty easy to get something that works together with my kernel driver. And I'm just using what we already have. Remote proc, RP message works pretty well. I actually I have to give a shout out to what Belibre did quite a long time ago, which was proposing a dev Axel driver that would be generic enough so you can plug in different firmware mediated MPU drivers that will have some backends on the firmware, on kernel, and also on user space. But if I had tried to go that way, I only have one hardware which I could test with, so I wouldn't really know how to go. So I have gone this way. The firmware is very simple. We get even simpler after some ideas I got from colleagues from Texas Instruments. And basically, I just have to take care of in the firmware about memory isolation, and I have a really simple kernel API that it's extensible, and it makes the kernel driver to be also quite simple. It's written in C with the compiler from TI, and maybe it will be the base for the firmware for other hardware, which also will have its own firmware and has a similar architecture. I will be talking more in depth about Thames because I have been asked a lot yesterday about this, so maybe some of you will be interested as well, and I can give a more the definitive answer. This is what I will be talking now is a bit ahead of what I sent to the mailing list. There have been some evolution going on, and hopefully in a couple of weeks I will be able to send us a next version which matches more closely this, but there isn't that much difference. IPC, just you create a destroy context. There's one context per the client, so when a process opens the device file, we have a context created automatically for that client. So the firmware knows about that because it will need it for doing this memory isolation among clients, because the kernel will be asking it to map in the DSP IOMMU the same virtual addresses for the same physical memory, but it should be mapped only to that specific client, so the other clients cannot access that memory. And then once you have all those BOs mapped, you can submit a job, which is just it's actually another BO which contains the executable code, which is this API, which is basically just one argument, which is an address to a buffer, which has whatever the kernel expects, which is normally a series of integers or another addresses. And of course, you get an interrupt back in the kernel when the job finished. And then we have this API that we have beneath that, as you see, map quite closely what the IPC messages are. That's what I'm telling people who are thinking about upstreaming other firmware-mediated MPUs, which is that make sure that your firmware is as simple as possible, so what it needs from the kernel is also as simple as possible, so the kernel can be as simple as possible, so that user space doesn't have too much trouble when communicating with it, because otherwise, if you make a mistake in the firmware, putting too much stuff there, it's going to make everything explode in complexity. So hopefully we can keep this as simple as it is right now, or at least not that much more complex. So as you can see in the UA API, you just create and destroy BOs like any other DRM device does. You ask it to map, get that offset that people who have programmed those know about. It's very simple, and then submit that kernel that we already compiled in user space. And depending on the hardware, memory might not be coherent, so we can have some prep-fini BOs. This right now has implicit synchronization, which means that if you are trying to read from the BO, the kernel, when you do the BO prep, will wait for any job that is supposed to be writing to it, waiting for that fence. It will block there, and it will also do some cache maintenance if that hardware needs it. This won't be enough if we want to have a Vulkan driver afterwards. I hope that at some point Khronos will come with extensions for Vulkan, so you can express whole models, and the execution module will need explicit synchronization, which means that we expose here the actual fences instead of having them hidden in the BO prep and fini thing. That's something for the future, but to be taken into account. How do we do this memory installation? I already talked a bit before. We have this privileged page table for the firmware itself, which has everything that is needed, which is much more than the actual kernel will need. The actual kernel will just want to take those input tensors, do some compute, and produce those output tensors, right? So we can just give it just mappings for those BOs, and also for whatever is needed, so that when the kernel finishes, we can go back to the firmware page table. But of course, if we are changing the whole page table, then the TLB has to be invalidated, because it's pointing to a memory which is not valid anymore. So that's very slow. But it's also true that with this model, we are supposed to run the payload that we saw being given in that IO, which corresponds to that IPC message, is for a whole network, which is something that you run maybe once every frame, a GPU frame. So you have a 16 milliseconds for that. So it's pretty big. But we can probably take it out completely by using some MMU features that we have in that specific MMU, which is very similar to the one from ARM. How does the kernel driver look like? It belongs to the DRM Axel subsystem, which means that we can use functionality in the DRM subsystem because we are an accelerator, plus something which helps us a bit more, but it's mostly about the place, and most importantly, the fact that it's completely clear in user space what kind of device it is, because it will be in /dev/axel, which sounds like a small thing, but when you have a compositor trying to render with your NPU, then of course you don't get much stuff on the screen. So that's good. I'm also using DRM GPU scheduler. The specific board I'm targeting right now has two DSP cores, which are exactly the same, so I can load balance among them like this, like with Rocket before. GMBOs, like always, some facilities that we already have in the kernel for managing memory. I'm using this in the usual way. And then I can power on off the cores with a remote proc. The right firmware is being loaded. And then I will do this communication with LP message, which uses virtual queues and some interrupts to know that it's done. There's something that needs taking care of. If we move up to user space, then we have this Gallium driver in MISA, and you can access via TensorFlow Lite on executors, as I showed, hopefully with more ways coming in the future. And most of the code there is just taking this model as TensorFlow Lite or executorch describes it, and lowering eventually into the actual instructions that are run into the DSP. Which has a normal ISA, as normal as a DSP can be, plus some instructions that give us access to these accelerators that they have on the site. In this case, it's just a small part of a kernel that takes some of the computed data out from the registers, from the matrix multiplication, and puts it into some registers, and then we load in memory in the right place. As you can see, we have several knobs. That's because I'm not trying to use the pipelining that the SPs are good at, because it will be adding a complexity. I want to get things working first correctly, and they will be optimizing this later. But I need to figure out exactly what how these operations work, so I can do it reliably. It will be quite some work. Well, one of the big advantages of why we do all this is that it's much easier to integrate. I mentioned how complex it can become. We heard yesterday how difficult it can be to use an MPU in your own project. If we have all these pieces in mainline, then we don't have those problems that we heard about yesterday. We can have this common infrastructure in the form of distributions or other projects that help with mainline components. We can reduce costs. We can keep a closer eye in security because of this, how we can upgrade our own software faster if it's in mainline, because there's other people working on integrating and updating the different components. Lately, there's some other considerations, legal, for example, that it's much easier if it's being taken care of in a common place where we can pull effort in places such as Debian, Ubuntu, Yocto, Fedora, etc. It's just not distros, it's organizations in which we can work together with others, so we don't have to do all the work, each of these companies that are using these components. And Yocto already has changes so that the Teflon is built, so you can just choose to use it if your hardware is supported. And then when you build Mesa, Teflon will be built as well. When we have Executorch, same thing, if you want that. And probably the kernel that was built in Yocto for your hardware will already have the kernel driver for the MPU, so you don't have to do anything else. It will just be picked up at the right time when you try to use it. And well, it has also a recipe for TensorFlow Lite, so it will be building automatically if you choose Teflon. So you should have everything that you need to use it on this hardware that we support currently. Debian, similarly, when Mesa is built, Teflon can be built as well, and you can install it afterwards if it's something that gives you something that you need. And we also have TensorFlow Lite, so you don't really need to go with pip, install some random version from internet. It will get something which has been tested to work with Teflon. And of course, the kernel build should have also built the right modules for your MPU hardware. And it's already in Debian, it got into Ubuntu recently as well. So besides integration and this not having to do all the integration for all the hardware that you have for all your products yourself, we have these security benefits, which I think all of them are known by all of you, but anyway, I'm saying it for anybody else. So you can get those security updates as soon as upstream knows about that and gets a fix, then it just trickles through the usual process. And there's a lot of work around that like tracking the vulnerabilities as they are found and reported, and there's quite some tooling nowadays around that we don't have to do ourselves. This will happen in our upstream components, and then will reflect on the bits that we end up putting into our own products. And it's pretty good that we have a UAPI that has been reviewed in the mailing list by people who have been working on this for many years, because when you see the UAPI in many of the kernel drivers from these vendors, I mean, it's full of holes. It can be pretty bad, right? So at least we can know that we have these benefits regarding security because of all this experience that we have pulled in our communities. And the stability warranties also mean that you are not tied to a specific version of the kernel for that given user space, which with all this chain going up and bringing other older versions of the software, which can have their own security problems, among others. And of course, we have a source code, so we can audit, debug it, try to do some offensive penetration testing, for example, and so on, which we cannot as easily with the closed source drivers. And performance. I mean, it often happens that when there's an open source stack and there's also a vendor stack, which is closed source, that the closed source is faster. We have seen this with GPU drivers, for example. The thing is that it can be true that for the benchmarks that the vendor optimized, that the open source version is slower, but the fact that we have the open source code allows us to get even faster performance for the, maybe not as much for the benchmarks, but for the scenario that your product is about. Especially because there's many cases which you don't have an algorithm which will give you the optimal solution every time. You have a heuristic, most of the time is the right thing, but maybe it's not the optimal solution for your own use case. The thing is that the fact that we have the source code means that we can change that if we figure out that we are not having 100% occupancy, for example. Or maybe it's not that you want for maximum performance. Maybe you have some other requirements, like, for example, memory usage, power usage, latency, and we can change the code so it matches better, which is something that you cannot do with the vendor drivers. And there's as well that because the software stack is closed source, you also don't know how the hardware works, so you cannot change your workload, so it makes better use of the hardware. But if we have these open source drivers, we can really see how the sausages are made, and we can figure out that maybe we are trying to do things in one way, which in this kind of hardware cannot be fast. We can make those changes so that we can get our use case running well on this particular hardware with this particular software stack. And then the fact that we are in mainline and we are using all these facilities that are already in the kernel, which is not the case often with the vendor drivers, gives us things like the MA buff, so we encapsulate these BOs and we can pass them safely between processes, so we can have zero copy buffers among processes or within the same process between drivers, right? So it can be a buffer from a video codec that we want to use as an input tensor for the NPU, etc. There's other cases. But of course, we need to know what is in those buffers. With the closed source drivers, we often don't know, but with the open source ones, we really know what is in there, so that makes possible that we can exchange efficiently data among different components in the pipeline, in the system. And there's as well a synchronization. It's not enough to know that the buffer is there, but you need to know when every hardware component has finished writing to it, so it's safe now to start reading and doing the next stage. Trying to move a bit fast, I think we don't have that much time. What hardware do we currently support in mainline? So we have for these Vivante NPUs, like we support those variants in the NXP IMX8 MP SoC, and also the other variant, another one, which is Neam Logic A311D. For Rockchip, we currently support only ERKI 3588, even if there's ongoing work to add support for others, as I will talk a bit more later. EthosU, we support two variants. One is the U65, a bit older, which can be found in the IMX93 SoC, and also have good support, pretty complete support for the U85 in the Alif E8. And for the Texas Instruments, this Thames driver is a work in process, in progress. I have started with the Jacinto 722S, and I have several other boards at home that we'll be dealing with as as I get the basics working. Regarding what supports, we know that Mesa supports because it's tested. All these models are in a test suite for the whole models and also for the individual operations. So we know when something starts failing, we know exactly what, and most of the time it's pretty obvious why. So we don't regress. So we have enabled already use cases like a classification of images. This image, what is in there, which with more models, so we can choose the right model for the use case, depending on how much performance you need or accuracy, etc. Detecting objects in an image, how many objects of what class are there. Similar to the classification, it's good to have more than one model because for every case there's a different trade-offs that are optimal. Event and anomaly detection, like for example, we have some noise or voices and just find the keywords, or you can have a series of measurement. So, and then the post-estimation, okay? So we'll be seeing where are my different parts of the body. How do you use it? I don't have much about that, because you just install it, and then afterwards, because we haven't forked the frameworks, we have tried to use only pluggable interfaces. You just use the documentation, and it should work if it's supported. So I'm moving now fast to the ongoing work. What is coming next? I already mentioned a bit. I'm adding a new backend. It works for one specific model, MobileNet V2. Which is not really that interesting, but I have moved now to running transformer-based models, which is more interesting. Some very interesting models have appeared recently that are also appropriate for using in the edge. So this is enabling this kind of work. It's sponsored by ARM, but will be useful on all these drivers because of the architecture that we have in mainline. These are these transformer-based models. Hopefully, I will have some nice demos in a couple of months from now. Then we have this work on Thames. I got a bit into detail on that, and well, it's that kind of the SP, and the fact that it has a firmware is very interesting because it will be as well a template for other drivers that are coming. Rocket for the AirKey 3576. Somebody's working on that, so we'll be working together in mainline to enable that on the kernel user space. Let's see what needs being changed. Community, we have these spaces where we can work together. These are not new. These are the same that we already had for display and GPU drivers because it's just another accelerator, right? And we are using the same infrastructure, and very often it's the same kind of people, and we're already friends. Kernel patches are sent to the mailing list, and then for user space, we use GitLab. Well, there's my blog, which I haven't been writing very often. Hopefully that will change. And we have an IRC channel if anybody wants to log there. There isn't that much activity. We only talk from time to time. And that's it.
We're a bit over time for questions, so make sure you catch Tommy in the hallway if you have questions for him. So, and then we'll switch to Stefan.
Time flew.
Okay.
Okay, good evening, everybody. I know I'm the last one before the end of the event, before the closing event and everybody, so I will try to speed up. It's a lightning talk, so it shouldn't be that long anyway. So what I want to talk about today is matter over threat, or taking full control of your own gadgets in your IT space for things you want to develop. So we had embedded recipes, so obviously we need to start with a recipe here, right? So what I did here was like putting together things I had lying around for a while. So for example, I undusted my old Raspberry Pi 4. I found like an old random micro SD card to get like a Home Assistant installed on that. I had like 2 or 3 of the older ESP32C6 boards lying around. I bought them like 3 to 4 years ago, never played with them at all, but I had them still in the cupboard. And then I bought a few of the commercial devices running Matter on one of these unavoidable Saturday runs to IKEA with your family if something need to be bought and built. You need a radio for an 802.15.4 that is supported by Home Assistant. I just went with the one that is actually sold by the Home Assistant communities, so that was like a smooth progress from my side. And then you need like your miscellaneous sensors, LEDs, LED stripes, or whatever you have lying around that you actually want to like get into a gadget that is running into your home. Time, it basically can take everything you give it, but then normally it should like just in a few evenings that was like done, the basic concept, and then you can start really toying around and like rinsing and repeating. So talking about that, so what are the steps? So what I did, get Home Assistants installed, obviously, get the radio connected, make sure that you're running in thread mode and not in Zigbee mode for that one. Get your normal off-the-shelf Matter devices onboarded. So that is basically just to make sure that you get a feel for it, like how things are working and so on. Find all the limits that annoy you, which is a normal thing with all the commercial devices you're buying, that you think like, why didn't they do that differently, or why can I just get that adjusted to my own needs? Start with toying around, flashing the ESP SDK, and then the fun really starts. They can just grab all your random stuff that you want to get connected, put it to the hardware, and then basically try things out, put it in your home, and basically rinse and repeat. Okay, so a bit more serious here. So what I want to talk about is, so 2 years ago, I moved into a new house, and I wanted to figure out if something of these smart home stuff is really something for me. I put nothing in, so it was all like later added on, and I have like some ideas of what I wanted to automate and some things that are just random stuff I want to try out. So that was the intention, basically. I had a very strong feeling and opinion on having like local-only communication for these devices. I'm not against like these things talking to the cloud at some point, but in general, I want to be in control of what is happening in this house, especially for things I build myself. I have a strong personal bias towards 802.15.4. I did that in my diploma thesis. I worked with that already, and for the last decade or something, I'm maintaining the 15.4 subsystem in the kernel. So I'm tinkering around with that now and then, and that is actually why I think it's like a good use case for me. It might not be for everybody, but for me, it's very well. And then I wanted to be in a situation where I can run commercial devices next to DIY devices I do myself, have a clear coexistence between the two of them, not one or another, but really make sure that I can just bring stuff in where I need it, but if not, just buy it off the shelf. I wanted to have a FOSS platform, obviously, to like get all the data, make it sure it's stored locally, and that is where I went with Home Assistant. But on the other hand, I also wanted to be have the possibility to run and control it completely for something like Google Home or Apple HomeKit or something. I mean, you know, there's family, they have other platforms, they have other devices and so on. So you want to be open for that part as well. So that was the basic I wanted to work in this environment. So as the title says, Matter over thread, 2 components are really like the ingredients here for this recipe. That is Matter. It's governed by the CSA, the Connectivity Standards Alliance. It was former the Zigbee Alliance, so that's where a lot of like their expertise comes from. The idea basically is to have like an application layer protocol based on IP version 6. And one of the options for the communication is Thread, which is for their low power consumption devices. They also run over Wi-Fi, obviously, and then they run also Ethernet and stuff. The local-only communication is built in by default. So that is like the default option for any Meta communication going on, direct device-to-device communication in the local network or something. You can always go to the cloud if you're a vendor and you want to like enhance that and like bring it back into your backends and so on. But in general, the protocol itself is really focused on local communication, which was very much in line with what I wanted to do. They started in 2022 with version 1.0. I think they're at 1.5 now. Initially, it was like quite a bumpy start, I would say, not a lot like devices being described and so on, but that got better over time. Interesting part here is that this was like an agreement with a lot of like big players coming in. So if you think about like Google, then Apple, Amazon, Philips, and all big players in the space come together and want to do something to actually have like a baseline for their own platforms. That was really interesting to watch, that they actually could agree on something and like roll it out onto their own platforms. And for that, they have this idea of this concept of multi-admin to basically allow a device to be connected to multiple platforms. For example, the light bulb in your home, in your living room, for example, that can be controlled with the whatever HomeKit from your son's device or like Google Home from your wife's device or something like that. So all of that can work together, which obviously opens up the door for something like Home Assistant as well as another platform on that one. And it also opens up the space for smaller players, be it enthusiasts, be it like do-it-yourself, or even smaller companies that can do this kind of devices and then be able to like control them from the bigger ecosystems. You don't need to go through the whole process of like certify for Alexa, certify for HomeKit, certify for whatever, but you can just go with that one and you're set on that level. There's an open source SDK for it. It's still called Connected Home over IP. That's shipped, that's the old name. I think the GitHub project just stuck with it. So, talking about the device types. As I said, initially they didn't have much, so that was like a big struggle in the beginning, like what is actually specified and what not. Over time, that got better and better. And they rely on the Zigbee cluster library to describe the specific properties of all the devices and so on. So that is like in the wild for many, many years already, so they're based on that knowledge that's already available, and it's a good base for your own devices, basically. One particular topic I was interested in is to figure out how I can do like composite devices, having a device with multiple endpoints and multiple clusters on these endpoints and so on. Because often when I looked at all the devices that I would be interested in, I needed several of them for like one use case in one room or something. I was wondering, why can I do that more effectively? Like, why can this device not have an PI sensor for presence? Why does it can control the light stripe and the temperature sensor and. So why is that not possible? Because the products being sold there, they have like a clear product idea, but my idea might be different. So that was something I explored a bit, and that was really interesting for me, that it actually can work easily as composite devices with multiple endpoints on. Some miscellaneous notes here is for Meta device onboarding, you need to have like a specific code to get into your platform, and then all the security onboarding starts. This is normally not a problem. You get the QR code with the off-the-shelf device. For your own device, you need to make sure that you like have a clear matching between what you're developing and the code you're putting into that one. For one or two devices you're playing around with, not a problem, but if you go to like 10 or 20, you need to have some kind of map for yourself. That could be QR codes, it could be like just a setup pin. It could also be NFC if you're fancy. So that could be something you do there. And one thing that I struggled a little bit with was, how would I go with functionality that is not specified yet, something I want to do the device to do additionally on top. There's not a good way to do that in Meta. You can always fall back to go with other mechanisms over the normal IPv6 network. You can just run MQTT or something over that one. It's not really like a streamlined experience at that point, but if you want to have like out-of-band control or out-of-band situations with this device, you can do that. Okay, so I started out, I wanted to go with Sapphire to be independent on the hardware, be like very flexible in these terms, and it initially looked very good. They started to look into integrating the Meta SDK, but that is still in progress right now. So that is going on for quite a couple of years now. And to be fair to the Zephyr project, it's a pain to work with this SDK. They're using a lot of like Google stuff like GN, so Generate Ninja for like the build system, and then they have like Pigweed for like a lot of like the embedded abstraction and so on. It's not fun to work with that. I tried to integrate that into a Yocto build at some point, and it was not fun on Linux at all, and it's definitely no fun on Zephyr either. So, but there are SDKs out there for specific vendors, if you're into that, for T-Link and Nordic that actually have that integrated, so you can run that on Zephyr, but it would be like for their hardware, and at that point it's not really that abstraction anymore. So for me, the easiest way was to just go with the ESP SDK. Again, it's specific to hardware, I know that, but it was like the best experience for me at that point. It was really easy to do. And it might not be as flexible down the line, but I was really pragmatic there at some point. But I mean, things can be changed, it's just software. So that was the meta part. What about the thread part? Why I'm so obsessed with that? So OpenThread, you have here, that is the open source SDK for the thread protocol. It's available for a long time. It's the base for basically all available thread devices. There might be one or two other thread stacks that have been written, but most of the devices I know about really use the OpenThread implementation. As you can see on the list above, they have basically like support for all the available 15.4 radios out in the wild. So that is like well supported. It runs on bare metal. It runs with the vendor hall. They have like a POSIX implementation for the border router side, which can run under Linux, and it's run there. And yeah, so that is like very well covered at that point. Its GitHub repository is available, and then there is full integration and full working setup with OpenThread for modules for Zephyr. I'm very fast here, I know, and I'm touching only like high parts of that. 3 years ago, I did a more in-depth technical talk on the OpenThread or thread side at FOSDEM. So if you want to go more into these details, just look it up. It was in the embedded room. That gives you a bit more like details on that front. So the device types that Thread have. So why is it so interesting for me at least? So you have like 2 different types. You have like the full thread devices. You have the minimal thread devices. Full thread device is basically normally mainline powered, radios on all the time. It can has enough memory to store some packets for some of its children and so on. And it's more like a more capable device altogether. That is basically what forms part of the router in the network, being able to have different children, routing packets between them, storing them for them, and so on, making sure everything runs smoothly. If it's more powered then has an additional external interface for something like Wi-Fi or Ethernet, then it often can act as a border router to go to the other networks to really do an interconnect to other things. And then where it becomes really interesting is the minimal thread devices. These are the devices that have the bare minimum of RAM or storage available. They are normally these tiny things that run on a coin cell battery, hopefully for a couple of years, like a temperature sensor in your attic or something like that. This one really only wakes up periodically, makes sure, is there something for me to talk about, and then fetches the data from the parent, from the router, process that, act on it, and then goes to sleep again. So it tries to be at sleep at all time, if possible. And this is really what brings some of the benefits here, and it's helping. So the routers are the part where they're really helping the mesh network to grow into your whole area and your whole home. And the minimal devices are the ones that could be interesting if you're interested on the battery side. In my own toying around, I'm still using them all on main powered right now. Normally this is just a USB supply, but I'm still planning to go into the battery side as well, but I haven't touched that yet. Yeah, I touched on that already. Basically, the idea is having the routers, having the end devices that are more the capable ones. Border router is the one that actually brokers all the traffic to Wi-Fi or Ethernet or something like that, and then obviously into the wider internet. And then the leader of the thread network basically defines how the whole thing operates, takes the network under control. There could be several border routers and so on. So from a networking perspective, that's quite an interesting protocol. So if you're into that, have a look at that. I can really recommend it. So that brings me to my summary, right? So what I did, I tried out different sensors and so on. I tried in different rooms, and all that worked quite well for me to get it onboarded easily with a Meta device into Home Assistant, and that was working quite well for me. I could use these informations I got there and connect it together. So the whole idea for me to be in control of my smart home was really working out for me. I spent more time on it than I hoped for, but I mean, there was also a learning exercise and so on, and that's just part of the joy, right? So I was able to have like these combination of different devices, composite devices I was setting out for. The setup for the main components is really cheap and easy. I think the ESP32 is like, whatever, $7 or something like that. So that is like an easy base, and that already has like your USB connected and so on. The mesh is quite interesting, so it helps me to extend into the garden, it helps me to extend into the attic and wherever you want to go. And it also helps you to offload all these IoT devices from your Wi-Fi, which is a nice benefit you have, because while it still runs on 2.4 gigahertz, it is not really interfering with all the Wi-Fi stuff you're having. Maybe if you like really have it close to each other and so on, but it helps, it really gives you like freedom on the Wi-Fi networks to not be crowded with like 30, 40 more IoT devices just for the sake of it. My data stays at home, it goes into home system, it stays there. And then also my experience was it was easy to combine it with other commercial devices, especially on the home system side. So that was really like what I was aiming for, searching or like solving some of my own itches I want to scratch, but for the rest, just go off the shelf and be happy with it. Yeah, and I haven't really tried much of the Google Home and so on. I tried it initially to make sure that it keeps working and so on, but since I'm the only one at home that actually uses it, so I don't really have a need for that. But it was good to have that in the back of my pocket in case my wife or my son really wants to play with it as well. And with that, I hope I didn't promise too much and make up time. That's it for me. Thank you.
We can do one question if you want while we set up for the closing game. Anybody have one? No, everybody wants to be. Oh, here we go.
Matter have this notion of certification, so you need to, or you can have device certificates. Did you encourage, and did you have any issues with, because obviously you didn't have your devices certified?
Yeah, no, I didn't do anything. No, that's fine, I can just go. Yeah, I didn't do anything of that. I know that could be a problem if you really want to go like into the commercial space of that as a small spark. Then you need to run through all the hoops and might even pay for it. But yeah, I completely ignored that, to be honest. For the do-it-yourself thing, I didn't want to like get into any trouble with that and like work around that. So yeah, no hints on that. Sorry. Okay, so thanks everybody. Thanks for the organizers, and see you later.
All right, we're going to take a minute here just to get a couple things set up for the closing game. But if you haven't been to an embedded conference in Europe before, there's a long tradition of having closing games, and we're gonna do an embedded recipes twist on the closing game tradition. So bear with us for a second while we get it set up, and we'll be going shortly.
Tiens, juste ça. Je vais le faire là. Hein? Ouais,
All right, so for the prizes for the events, you can see we're collecting some toys here. Thanks to our sponsors, we have a handful of things here. We have the SD Mux made by Pengutronics folks. Here we have the Arduino Uno Q from Qualcomm. We have several Pocket Beagles, Pocket Beagle 2 from TI. We have the Beagle Y AI board from TI. And we have quite a few of the Libre Computer Solitude boards. This is an Amlogic SoC. If you get this, the case just says it's like a carrying case, but there's actually a board in there with an SoC running mainline. But you might be disappointed if you just think it's an active case. But yeah, there's hardware in there, interesting hardware. And then we have from NXP, we have a couple different boards. We have their an MCU Espresso platform. And then we have a few of their IMX9 91S development platforms. So we'll be giving these away as prizes, but the one thing you definitely have to know about embedded closing games is this game is not fair. There's nothing fair about this. So this is the continuing tradition. There will be some right answers and wrong answers, and among the right answers, I'm going to give out prizes, but it's not going to be fair. There'll probably be more of you that have things right, and you may or may not get prizes, but that's okay. That's part of the fun. Sorry, and enjoy. Go ahead, Julian. We're going to change MCs here. Julian's going to be our MC and our chef, and I'm just going to be the prize giver.
All right. Welcome, everyone. So, the kitchen is open. I hope that you still have a bit of CPU cycles left, because I don't really, but anyway, it's going to be okay. Before we start, as Kevin mentioned, I would just like to thank Tim Bird for decades of closing games. So we're going to be everything necessary to honor the tradition. And hello, Tim. I think he's going to be watching the on the live stream. All right, so after 2 days of recipes, what are we going to do now? Let's cook? Cook something? All right, So it's gonna be a 3-course menu. You will be the chef. I'm checking the ingredients. Your job is just to try to find them. Kevin has a stack of pretty good prices from our sponsors. So he will distribute everything. And I have chocolate. As Kevin mentioned, the game is not fair. So who wants some chocolate? All right. So first course, it is called 2 Truths and a Kernel Panic. We've asked 3 of our speakers to provide us with 3 true statements and 1 lie about their presentation. Your job, just find the bad ingredients. Where's Marek? Marek? Kevin, would you like to throw the mic to Marek? Or the catch box, yeah. So Marek is gonna provide you with the 3 statements. You're gonna vote. So there will be three answers. You just have to say 1, 2, or 3, and Marek will tell you which one is a lie.
You have the 3 things?
I have.
Okay,
Do you remember, Marek?
Let's start with the first one. The U-boot pstore command can be used to dump kernel console content from the ramoops buffer.
Hello, wait for the 3 ones.
Oh, what's that?
You mentioned the 3 ones?
I mentioned the first one. I'm
Okay,
not sure
so
what
let's do the 3 and then we vote. Yeah.
Read all 3 and
do
then
the second one, the third one, and we will vote afterwards.
Oh,
Yeah.
I see. Yeah, okay. The second one is the U-boot relocation on ARM32 iterates over REL-10 section entries. And the last one is ARM Cortex-M33 uses MMU to configure memory region attributes. Number 3, well done.
So everyone has a good right answer. So. And it is not fair, so everyone will not have a prize. At least not now. Where is Francesco? Francesco. Marek, can you throw the catch back to Francesco?
What is
From here?
Francesco?
Oh yeah, over there.
Thank you.
Hey, Francesco.
Hi.
So second one is Francesco. You can announce your 3 statements.
Yep. So first one is the FBDev emulation for mode setting drivers is a DRM client. Second one is the DRM panic driver is implemented as a DRM client. Third one is a DRM client able to print kernel messages exists.
Can vote. Oh. This one is not so easy. Here is the answer. Can answer. So who is correct? Maybe that's not a good idea. Kevin, it is not as resistant as the catch box, okay? Okay, the last one, where is Laurent? Over there. Francesco, can you?
Yeah, this is simple.
Thank you.
Thanks, Laurent. 3
So,
statements.
Talking about cameras now, I mentioned during my talk that there were some topics that were candidates for trivia games. So here we go. The first digital long-distance image transmission occurred in 1906. The patch series for Linux Media that took the largest number of iterations went to V28, and V-Fall2 does not specify user-space API for camera sensors. Which one is false?
I have the right answer, but I'm cheating. Okay. Laurent?
So the first long-distance image transmission indeed occurred in 1906, but it was analog and not digital. Very small detail.
Okay. While Kevin is throwing some gifts. So let's go for the second course. It is a main dish. It is called Commit or Bluff. So I'm going to announce to display a commit message, and you'll have to find if it is a real commit or if it is a fake one. So real one, just put your thumb up. False, thumb down. Ready? The first one is easy. So that's a NevDev one. So it is called fixed packet loss on Tuesday. So is it real or is it fake? We should give a prize for someone who failed. All right? No, this is a fake. Oh yeah, sorry. Is everyone able to stand up? Because I forgot to mention that it is a crowd elimination game. So everyone stand up. Now sit down if you have the wrong answer, okay? Only one? Okay, second round. This one is for PWM. We have Uwe, who's probably watching this in a live stream, so hey Uwe. So ensure callbacks exist before calling them. Don't vote yet. Wait. Ready? Okay, come on. Yes, it is real. So wrong answer, you can sit down. Third one, that's a firmware one. I don't know if Craig is still there. Okay, maybe that's good for me. Okay. So this one, that's kind of, okay, changing more than 150 files in the same merge, in the same commit. Okay, can you vote? Okay, great, did it. Oh, it's becoming interesting. Okay, round 4. That's for Open Embedded. Philip, you're here? Yeah, you're here. So, remove a recipe edited by mistake in 2017. Ready to vote? Philip, you cannot be wrong, okay? Let's go. Philip, you can vote. Come on. I'm just waiting for Philip to vote. You're right. Could have been wrong. It could have been real, but not this one. Who's still standing? How many? Okay. Okay, we're mid-course. I think that you deserve a bit of. No. Are we doing this one? No. Let's wait for the end. Yeah.
You can do one more.
Which is it one? Yeah, we can do. We can do this one. So who is still standing? You can get some prizes. Okay. I don't know if the board is supposed to work still after this, but okay. It will be nice on your desk, but okay. All right. So I have a few more rounds until it remains only one or two people. Round 5 on kernel scale. That's yield voluntary when Watchdog is getting impatient. That's from Carles on the Zephyr Ortas side. Can vote. No, that's fake. So we just try to give the Watchdog a bit of personality, but could have been correct. Who's still standing? 1, 2, 5, 6. Okay, let's say. Okay, you're something like 12. Yeah. Round 6. So that's on Alsa side. So fix a spelling mistake between Firefly and Firefly. Okay. This one is true. Wow, still up. Okay. Round 7. So on kbuild, really remove temp file when file check fails. Where is Bartosz? Do you remember this? You reported this. Well, that's true. Did you have the answer, Bartosz? No. So, how many of you? Or okay, last one maybe. On net filter, fix overlap detection for elements that should not exist. This one is fake. Wow, we have some survivals, more than I was expecting, but okay. I have some spare rounds, that's fine. So let's continue. This one, it is a merge for 66 branches in one merge. This one is real. 1, 2, 3, 4, 5, 6, 7. Okay. DT bindings. Okay. Add a vendor prefix. Oh. No. Oh. Yeah. That's the real one. Oh, who's still standing? No one. So no prize, I'm sorry. It is not fair, that's it. Okay, who were standing just before this this commit message? Okay, you did something. We have some spare. Okay. Oh, I have one question. Do you like this? Do you like this, or am I just ridiculous? No? Oh, okay. Okay, no, that's not fair. Okay, so the last course, if it works, yeah. So that's the dessert. I would need 3 volunteers. Okay. Or you will have to fight. Okay. So just, okay, 3 volunteers, Kieran, okay. So I will provide you with a kind of weird or maybe impossible constraint. You will have to find a solution and pitch it in 45 seconds. Just remember that AI assistant is not available today. And you will have some bonus point if you provide us with some creativity and if you have a fun answer. So no wrong answer, just fun, a bit of chaos, everything will be fine. The constraints. So the first one, that's a boot time issue. The boot time on your Android-based unicorn toy is 42 seconds. The target is less than 1 second, of course, and release due is tomorrow. What are your next step? You can pick several people can pick the same one. That's fine. So the second one, your Yocto build has been running for 6 hours. It's at 99%. It has been at 99 for 2 hours. There is no error message. Explain your next move. And the last one should have been for Adrien. Where is it? The next one and the last. You receive a board from RigUp. The schematic says your art is on pin 3 and 4. The board says pin 3 and 4 are for GPIO. The chip datasheet says pin 3 and 4 are for I2C. And the chip on the board is a different one. And you have a soldering iron. Come on. So, Kieran, you'll take A, B, and C. All right, come on.
So the important thing to remember here is correctness is irrelevant. The decision is made by audience cheering, so
yeah.
Ready? Okay. Correctness or feasibility
just
is irrelevant.
take 30 seconds to think about your solution, and then you have 45 seconds to pitch. Oh, yeah?
All right, this is about
come on. Chronometer.
Hello.
Come on.
Right,
Go
this
ahead.
is fast boot, so really quick. The answer is obvious. We strip out Android and replace with Postmarket OS.
Oh, wow. Second one, so it was B? It was C. B, so you're B. Okay.
My pitch is going to be similarly brief, and it's actually something that I did. That is, while waiting for the Yocto build to finish, I bring up a build root build, and it finishes before the Yocto build.
So, the boot time issue?
Okay, that's also easy. So the soldering iron, yeah, it's used to. I always wanted to solder that kit. Oh wait, I also wanted to solder that scope, and also there is Postmarket OS built-in for that chip without the datasheet. And so by the end, we have the scope, we have signal analyzer, we have everything, we have Yocto, we have Android and Postmarket OS, and oh, wait, what's the board?
Thank you, Gabe. So now that's time to vote. So, who's voting for Kieran? All right. I don't remember your name. Can you your first name? Dmitry. So, who's voting for Dmitry?
Our
Arnold. So-
I think the winner is clear. I think the winner. But you all get prizes. But Arnold gets the chef's hat. Yes, he gets the
Okay, I think we're done. And okay, it is not fair, but I think that we got some prizes left. So we have some, yeah. Who wants some chocolate? Just help yourself. Yes, absolutely. So thanks a lot for the prize sponsors. Thanks a lot. So we had TI, Qualcomm, NXP, Pengatronics, Liberal Computer, and Jan. Are you here? Where is Jan? Oh, she's here. She made the awesome posters and illustrations for the embedded recipes. So big thanks for Jan. And we have some posters here. We have collector posters here. Who are the winners? Come back and take a poster if you want. All right, so that's it for the Embedded Recipes 26. Oh. I will leave the final word to Kevin.
So just a couple final words. Anybody who was a speaker, please come to the stage. Right when we finish, we're going to take a quick speaker photo as we wrap up. And take a look at the final sketches from Frank. If you see yourself, the drawing is yours. And if you're in with a couple people, you can figure out who wants to have the drawing. If you signed up for the key signing, the Open PGP key signing, we're going to be doing that just outside where you came in and picked up your badges. We'll be doing that out there. If you have feedback, please feel free to send us your feedback. We're also going to be sending out a survey in the next couple weeks, so there'll be opportunity to do both. But we tend to hear more of stuff that people don't like than what they do like. So that gives us a bad impression, maybe. So if you do like things, please feel free to give us positive feedback as well. And of course, spread the word on social media if that's your thing. And also a big thank you once again to all of our sponsors. And I also wanted to just shout out the program committee. In the past couple years, I've been doing the talk selection mostly myself, and this year I recruited some helpers, so I just wanted to thank Thomas and Jan and Laurent and Andrew and Trevor and Drew for helping out on getting the talk selection. So. And then we have to clean up pretty quickly, so if you're not... If you don't want to clean up, we have to leave the building rather quickly for the security team, but thank you very much. Yeah. And the speakers come here before you leave the building.
C'est à Julien. Je suis à 1% de batterie.
Ah oui.
J'ai eu juste...
Okay.
Please give the everybody loud.
So let's kill this so we don't have a backlight for the...